Ma è poca gente, mi pare, quindi... Ora ho iniziato io adesso la cosa, penso che... Fare tutto a posto. Quelli. Je laisse introduire.
Thank you all for joining these 6 sessions on the advance in remote sensing methods, techniques, and sensors. As you have seen in the program, this session is fully devoted to the SWOT missions, the new missions in flight since 1 year. I know that very few of you have been able to access the data, and we apologize for this, and it will change shortly, but we will have 5 different presentations, all from the SWOT Carval groups, including some science lead, PIs, and project contributions, to provide to you some early results regarding SWOT performances over inland waters. We have, as usual, 20 minutes for the talk, including questions. Including questions, please. We have some seed questions at the end, but this is the 6th session in the row. So some of the seed questions have been already addressed, and we have proposed some, but we welcome any seed question from the room as well. So our first speaker will be our French science lead from the SWOT project missions, Jean-François Créteau, who will present early results from the calibration validation of SWOT measurements over the lakes ESA-ESRIN.
Thank you, Nicolas. Good morning, everyone. So I'm quite happy also to present some first results. So they are very preliminary. They are based on the Calval phase that are reprocessed now. So you will see the results are still not definitive, but they are quite interesting. So my presentation is about the Calval over the lake ESA-ESRIN, but we had planned for a long time before the launch several Calval activities on rivers, on lakes in several parts of the world, mostly over the North American continent and Europe, and also Brazil and South America. And ESA-ESRIN Lake is a site which we have where we have done a lot of activities since about 20 years for the Calval of nadir altimeter. So we use it also for SWOT. First of all, because we have a lot of facility there, and also because this lake is right below the one-day SWOT of the SWOT satellite. So a short reminder of what is SWOT. SWOT is carries two main instruments: the carrying instrument, which is a radar interferometer in Ka band, and a nadir also Ku band altimeter. I guess you will see that it has been shown already first day, and we will have results on different activities by Roger and other person, but so you know that. But SWOT, the science phase started in July. So we had the first 6 months of Calval activities. Then we had the nominal orbit, which has started in July. We are providing level 2 data on lakes, on rivers also, but on lakes, there are geolocated water surface elevation, water surface area, and storage change. We also provide a polygon defining the shape of the water bodies. We also provide aggregated pixel cloud measurement into the water bodies. And for all lakes in the prior lake database, the PLD, the water features not in the PLD. And two products, we have a single pass products and per cycle. For hydrology, we have many expectations that are shown here, but it's not necessary to say that now. But for all of this, and it's different than satellite altimeters that we usually where we usually do Calval activities, because there are a lot of different measurements, different problems, etc. So the Calval works covering small to large lakes in different regions is really necessary before the data can be released to the users. So the Lake Isikul is located in Central Asia, and we had two approach in the first step of this work: comparison to external in situ measurement, the water height from fixed and moving station, and also comparison to an external mean lake surface. I will explain what it is. And in order to map the SWOT sigma node, phase noise, and WCE, which is the water surface elevation, and the dependency on the distance to the nadir. It is one of the main points. So we want to calibrate the absolute height, the assessment of the random error and rolling error across the SWATs with the pixel cloud vector, atmospheric correction using GNSS ground network that we have deployed during the campaigns, validation of high resolution and low resolution simultaneously. And also we wanted to intercompare the GNSS data processing that we have done, because we were three teams on the ground, the GFZ from Germany, Lagos from Toulouse, and also our Kyrgyz colleagues. So we have an existing permanent network of radar, weather station, GPS permanent, and also temporary station. We have done daily navigation across the SWATs with two boats simultaneously. It was a very novel experiment for us. We had two boats with a lot of instruments on the boats, and we tried to do it in coordination. And we use also the mean lake surface as the truth, as I said. So just a point on the roll and random error. In fact, for SWOT, the observation the error on the observation are really correlated to the distance to the nadir. It is expressed by this small equation here. And so the cross-stack, so there is a cross-stack linear signature of this roll error, which is well observed over the ocean. And in order to correct that over the ocean, we are doing what we call the crossover calibration, but it's done over the ocean. And then it's interpolated over the land, because we don't have crossover, of course, over the land. And here there are two maps that has been provided by Gérald Dibarbour from CNES, where we see the projection of the errors. So it was before the launch on the continents in winter and in summer. Why in winter it's more noisy? Simply because the crossover in the northern hemisphere, where you have sea ice, are not used. So you see that there is a projection of error that are not negligible. And what is interesting is that with large lakes, we may improve that, because large lake can be considered also as crossover point if we have the mean lake surface of the large lake. So we have calculate several mean lake surface. I will show how we do that. And it can be used for this calibration. And you have a nice poster of Maxime Vert also, which shows the results on that. So now the campaign that we have done. So we have done 15 days of campaign with the two boats, or with instrument on the two boats. And the first, so you have here all the planning cruise that we have done with the two boats. What we try to do is to be sometimes, some days parallel to the along track of the satellite, sometimes in parallel to the cross track direction. And when one boat were going there, the other boat were going there, etc., in order to try to see what happened on the measurements. And the first day, what we did, and you have the results here, is to have the two boats very close together, one and the other one behind the first one, in order to see if our instruments are well correlated and consistent. So this is the first day GNSS vertical profile along these lakes. And you see that with the two instruments and with two different data processing, and you can see that it fits well. So that's how we did. And so then I'm coming to some first results. So here, for example, one day with the two boats, one is going like this or like this. The second one is going on the other direction, but parallel to the first one. So we have the results here. So the red is individual SWOT measurements. And you have the GNSS from the two boats, from one here, from one boat here and one boat here. We have the GNSS profile. And you can see that when it's parallel, we don't have any, of course, we don't have any cross-track error because it's parallel and it works quite well for the two boats. So this is the first point. Second point, so we did it also. So this is a SWOT HR data. You have lot of noise. As I said, we use the first processed data. So in the future, we hopefully there will be no noise like this. But on some parts, it was quite nice. Here again, a parallel cruise to the long track, where you have the noise here, the comparison between the GNSS and the. So this is the difference between the GNSS and the SWOT measurements interpolate along this track. And here on this side, we have a pass that with a boat, which was in fact in the cross-track direction, where you can see, first of all, that you have an increasing noise when you are to the far range, to here in this area, and also you have a trend, which means that in fact it's the errors are increasing with the. So this case were done without any cross-calibration, a priori cross-calibration from the what we call the X-car. Another example, here we compare the LR and the HR data. So you can see a SWOT, so it's on a day, I don't remember. So it was a measurement done in June, so not during our campaign, because during our campaign we had a lot of problems still with the SWOT data. Because of cross-calibration. But here the data are quite nice. You can see the LR data. So we have two passes, one passes here cross-track, one passes here along track. You can see again the differences between the SWOT and the how to say the GNSS profile. And here it's with the HR. We have exactly, or not exactly, but we have the same. We have the same observations. So now comparison with mean lake surface. What is a mean lake surface? We have done this work for many lakes, 22 big lakes in the world. And it's interesting because it's just a kind of, it's not the real geoid surface, but it's more or less parallel to the geoid surface, at least at the precision that we need. So we selected track with at least one crossover. So we use ISAT2, mostly ISAT2 and all the Nadir altimeters. We have 20 years of GNSS field campaign. So in fact, you have all the tracks here that has been used to calculate this surface. We smooth by moving average the vertical geometric height and filter all the outliers. This is an example with ISAT2 of the measurements along the track of ISAT2. You can see it. And then we use in situ water level because the altimetry that was used and also the GPS that was used at different periods. So the water level of the lake was changing. So we had to tie everything at the same date. We intercompare again the crossover point and filter all the tracks. And at least at the end, we interpolate the mean lake surface, which is shown here, and which is quite different from the geoid surface, the geoid from the model that has errors of 50, 60, even sometimes 1 meters of errors on such lakes. And then we compare what we did. We compare the SWOT data with this mean lake surface. And so here you have simply, so it's for, I think it's for LR and HR data. We have just, because the point clouds are marked with some labels. that say that you are water, or you are no water, or you are dark water, or you are water close to the land, etc. So we select only the pixel with which are classified as water pixel. So there are some problem, of course, still, because it's very preliminary, but we can see it was enough. At least it was enough to make the calculation. And here what you have is, in fact, the distribution of the differences between, so we have all average to 0, but it's the differences between the SWOT measurement and the mean lake surface, depending on the distance. And after that, we so here no xcal was applied. We used the data before the xcal, so it's date before the xcal was applied. And here we simply adjusted this equation. We calculated the alpha here in order to recalculate the differences. And you can see that it's really depending on the distance to the nadir, and on this cycle, this one. And this is a map of the SWOT measurements. The difference between SWOT and the mean lake surface before the xcal was done. So you can see that there is a big errors that can be corrected. Another example here, but here it was what we treat to see is if the xcal apply, so the xcal L3 here, so I'm not going to detail on that, but it was here before the xcal was applied, here after the xcal was applied, and of course, what we observed, so we adjust it, but the readjustment was exactly the same than what xcal from the project gave to us. So which means that after this xcal L3 has been applied, it matched very well with the mean lake surface. So it's really two independent data sets. And so this means that the xcal, which is a plan for the future, works very well on for these lakes and probably for other lakes. So these are the resulting. And the RMS, so what we see is that the RMS is, the distribution or the dispersion of the differences increase with the distance also, which is probably problematic. And we have seen average RMS of 19 centimeters for when we are close to the nadir, and 13 centimeters, sorry. And when it's part to the nadir, it's more. So this is a work done by Maxime Ver from CLS, which used pixel cloud high resolution. So he maps the sigma 0, which decrease with cross-track distance by a few dB per 10 kilometers. It's shown here. So you have different cases here. And also the SWOT pixel cloud high resolution phase noise. So here it's the sigma 0, here is the phase noise, which standard deviation with respect to the cross-track distance, and it presents the expected shape. We say the smile shape or something like that. And you can see here, depending on the distance, the phase noise. So where it's the lowest is at the middle of the track. Conclusion. So it's what I've shown is a very still preliminary, but it gives interesting first results that show us that we are on the good way. But many works remain to be done. So I didn't show, but we have installed a lot of instruments around the lakes since many years, and GFZ, the German colleagues, also have permanent station. So we have in the future we will compare when the reprocessed data will be provided. We will compare the mean lake surface, not the mean lake surface, the water height variation with what gives to us SWOT. We will intercompare also the HR and LR with respect to the GNSS data collected, again with the reprocessed data. All what has done here, what has been shown here is without the reprocessed data. We will validate the onboard processing, because you know that on SWOT you have onboard processing for oceanography mostly, but it works also on the continent. And on such lake, probably the large lake, we can say that we will probably not need, at least for hydrology, the HR data, because the low resolution data will be already very good. We will also estimate the through in situ network of a weather station and GNSS station, wet and dry tropospheric correction around the lake, and compare to what is given in the data product. We also so this is from the campaign that we have done, and during the nominal science orbit, we will continue the CalVal. CalVal is a continuous process, like we do with satellite altimetry. We will organize new CalVal international campaign next year and hopefully in 2025 in order to check how the instrument is working. And calculate also, it's also an objective, even if it's less important, but anyway, calculate the absolute bias of the nadir altimeter. Nadir altimeter on the one-day orbit, we are not going over the lake, so we couldn't do anything during the one-day orbit, but now we have several tracks, several passes during the cycle, so we will calibrate the bias. And also, we hope to make a routine validation of the SWOT water surface elevation using the operational in situ gauges around the lake that has been installed by GFZ and DEGO. So you have some example here in different sites. This is on the east coast of the lake. This is in the north coast. We have also in situ gauges on the south coast and on the west coast. That's it. Thank you very much for your attention.
Merci Jean-François, you are perfectly on time. So we have time for one or two questions from the room, if any. Yes, Pierre-Olivier.
Yeah, thank you, Jeff. You said you can use the lakes for validation, cross-track validation, but what is the minimum size of the lake you need to be able to do that? Is it you need to see a large part of the swath?
Yeah. Yes, sorry. So there is no threshold, I would say, of a minimum size. What we did, we calculate the mean lake surface of the 22 biggest lakes in the world, trying to have on different continents, in North America, of course, the Great Lakes of North America, in Africa, in Asia, in South America. South America, there are less. And so now we are checking with CLS in particular if really it helps. If maybe it's not necessary to add all of them, maybe it's necessary to add some of them, but at least we need to have the whole swaths. Otherwise, it's not, and at least from the cross-track correction, it's necessary.
Cedric?
Jean-François, please pardon my ignorance. When you're showing the profile of the lake, it has this bowl shape, right? And I suspect that has something to do with the geoid, but I don't understand why. I mean, I would expect the lake to maybe be flowing towards the direction of downstream, but so why is it like this?
You mean the mean surface?
Mm-hmm.
Yes. It's simply the effect of the geoid. So you have of the gravity. So the differences between for these lakes, difference between the center of the lake and the shoreline is more than 2 meters in the north-south direction and more than 4 meters in the east-west direction. So, and the models, actually we use models to correct for that because we have to calculate the water elevation above the geoid. But models in such lakes, even ESA-ESRIN is not the worst. The errors are at the level of 1 meter sometimes. In lake in Africa, like Tanganyika or the Baikal Lake, we have errors that are even more than 1 meter in the geoid model, even the best geoid model like the EGM or IGEN or etc. So this has to be correct. And this will be a problem with SWOT when we will have several passes at different time on different side, different part of the lakes, because if we use model, and if we calculate the per pass measurements, not per cycle, average per cycle, but you will have on one side of the lake, on the other side of the lake, the SWOT measurements. And if you correct with the geoid model, that it will be done because we cannot do, you will have like one measurement like this, one measurement like this, one measurement like this. So you have to correct afterward. And you cannot correct with such a mean lake surface.
One last question from Remco.
Yeah, my question was more or less already answered in the previous answer. But yeah, the dip in the lake is the same as you see in the ocean. You see the seamounts on the as well as the trenches. It's just geoid that looks like that, and it's surprising indeed, as you say, that it can be so deep, like 2 meters over relatively.
But it's even 4 meters on Lake ESA-ESRIN.
4 meters.
4 meters from the west part, even more than 4 meters. On the west part to the center, you have more than 4 meters.
So we need to move on. Our next speaker will be Roger Furchow from CNES and we'll present the SWOT early results of the rivers. As Claire Potier was not able to make it today, Roger will also do the third presentation on the lakes, and we will do the questions after the third presentation. So Roger will do the two presentations in the row.
Yes, good morning, everybody. So this first talk will be mainly on rivers, and then there is a second talk mainly on lakes, but I will actually walk you through all the different SWOT HR products. And I will also want to acknowledge the contributions of my co-authors that are listed here, but actually of the entire algorithm development team, which is a joint JPL-CNES team, and also the members of the HR Kalbal team, which includes industrial partners and also members of the science team. So with SWOT, altimetry becomes imagery. So I wanted to show you first here a SWOT HR image of the place where we are now. So this is the coastal area near Lisbon, which is here. And what you can see here is that we are actually imaging all the way from nadir. So this bright line that you see here is actually the nadir return. And then in the very beginning of the SWOT, things are a little bit distorted because we are so close to nadir, but then quite rapidly it starts to look more like the conventional SAR images that many of you already know, except of course that water is brighter than land because we are close to nadir. And then the SWOT goes on until about 60 to 80 kilometers from nadir. And zooming in here, we can see the two bridges here, for instance, and we should be somewhere here right now. So this is the level of detail that we have, and this is the level of detail that we work on when we retrieve heights. So before I show more images, I just wanted to recall the ambition level. What are the requirements, especially for rivers? And the requirement is that we want to monitor rivers down to a width of 100 meters. And then there is a goal to go down to 50 meters if possible. And for these rivers that are more than 100 meters wide, we should have an error in the water mass that is below 15%. Concerning the water surface elevation errors, it should be below 10 centimeter on over 1 square kilometer. So it basically means a 100-meter wide river after averaging of 10 kilometers, a reach of 10 kilometers. And at this same scale, we should have a slope error that is below 1.7 kilometers. So concerning the processing and the products, we start out with what we call the raw images. So this is basically the complex returns from that we have recorded from the two antennas of CARIN. And then we do SAR processing, and we go from kilometer resolution down to a few meters of resolution. And then we combine these two complex images by basically multiplying them to obtain what we call an interferogram. So here we have a power image, and we have a phase image with interferometric phase, and we also have something that we call the coherence that I will explain in a few slides. And it's on these images that we do much of the processing, the most difficult parts of the processing. We need to detect where there is water, and then for the water pixels, do all the interferometric processing to obtain geolocated heights. And then when we have done that, we create the first level 2 product, which is actually a point cloud, or we call it a pixel cloud because the points are pixels. So this is a sparse representation where we have basically thrown out all the land pixels, or most of the land pixels, so we keep only water pixels and a buffer around them. And here we have geolocated heights, various corrections, flags, and so on that I will detail later. Once we have the pixel cloud, we create vector products that are specific for rivers on one side based on center lines. And then we create also lake products where the vectors are polygons. Again, we have water surface elevation, slope for the rivers, area. For rivers, we also compute discharge, and for lakes, storage change. And then while we are producing these products here, we also compute something that we call the height-constrained geolocations. And of course, we establish the link between each pixel and the various rivers and lakes that we have in our prior databases. So we create this companion product to the Pixel Cloud, which is the PixieWEC product. And then we also create a raster product, which as opposed to these Pixel Cloud products, it's on a regular grid, but the resolution is slightly degraded to 100 meter or 250 meter pixels. That's an easy to use product if you don't need that very high resolution. And then in the very end, when we acquire data for a year or two or more, then we hope to combine all these variations in extent and height to create a partial bathymetry between the observed minimum and maximum levels. So so now I go through the products up to river products here, and then in the next presentation, I will start with lakes and also very briefly present the other products. So one of the very first images that we got in January last year was this one over New Jersey, and it was really a very good surprise to us to see the level of detail that we can observe in this image, because, I mean, we wanted to go down to rivers that are 100 meter wide or possibly 50, but we observe here actually structures that are much narrower than that, down to 10 to 20 meter width. And we also saw that our algorithm to detect water managed to identify these much narrower structures quite accurately. Here I show you the different components of the interferogram. So here we are really at full resolution, but I have downsampled the image, but it's representative in terms of noise levels. So we see here again on the left the power image, that's where we do the water detection. And then here we have the interferometric phase, that is modulo 2 pi. And this is where we get the height information from. So basically we see here that water pixels are mostly yellow here, and then we have other colors for the land surfaces. But this is where we get the height from. But we see from in the very beginning, it's something that is very noisy. So we need to average over spatially. And then we have this coherence image, which is a self-contained, which is a quality indicator that is given directly by the interferogram itself. It's between 0 and 1, where 1 is perfect. And we had coherence values over water, typically around 0.9 or even 0.95, which is very good and also indicates that we should be able to extract heights very precisely with SWOT. Of course, this was perhaps a favorable case because we have a wind speed of around 3 meters per second, which is ideal in terms of roughness to have a lot of signal. So you have already seen this image over Toulouse from March 16th, where we see a lot of detail and very small water bodies like the Canal du Midi, and even smaller rivers that we see here, and then of course a bigger river like the Garonne and the Ariège River. But what I want to show you here is an animated series of images, because during this Kalbal phase we had images every day. And what you can see here is that for some of the dates, we miss some of the lakes or gravel pits and also parts of the river. And this is what we call dark water. When there is absolutely no wind, no swirl, then the water is perfectly smooth and basically acts as a mirror, meaning that we don't get any return back to the radar. And when we don't get any signal, we cannot retrieve height either. it should be noted that if we observe part of a lake or part of a river, we can still use it and get meaningful heights over a lake or slopes for a river. So we have a certain robustness to this effect, but when it's all dark, then we can't do anything. And this happens from time to time. We can also have problems in the other direction. So here you see the Willamette River in the United States. And for this image, you see that we have quite bright structures around it also. And these are actually agricultural fields. And we see here in the detected water mask also that we detect the river, most of the river, but we have also these things around it that looks like lakes in a way, but actually they are agricultural fields. And this is because it had been raining really heavily, so it looked like this on the ground. So it was really, really wet, and this gave a very strong backscattering. So such situations can be detected as water. Here it is probably not desirable, but we can have similar return also for wetlands. And we can have also intermediate, quite high levels from ice on lakes and rivers. I don't have time to show you that, but we also have many examples of that. One other worry that we could have about SWOT and Karin is that we are very close to nadir, so we could fear having issues with layover. Layover is this effect where different surfaces that are at the same distance from the radar are mixed into one pixel. So we could fear having, pollution from the riverbanks and nearby forests in these examples that pollute the water signal and then also the height. So here I will show you an example from an area in New Zealand, which is quite hilly or even mountainous, where we could fear this effect. And when we take a look at the coherent power image, we see that we actually distinguish quite well the lakes and even quite narrow rivers, despite this layover effect. And we also managed to detect automatically the rivers and lakes very well in this case. And then, of course, the remaining question is to assess the impact on water height. So this is still under investigation, and it requires very precise reference data. So now I move into the Pixel Cloud products, which is the first level 2 product. So it could look something like this. This is for a lake in Canada. So you see that we basically have water pixels, but we also keep some land pixels. For instance, the ones that you see here in blue. So this is, we keep a buffer of land pixels around the water pixels. And then the water pixels, there are several categories of water pixels. Most of them are green here. You see, this is what we call open water. And then we also have water near land and some other categories. And you see that we also have a category that is dark water. So this is not pixels that are not detected as water, but if, for instance, we detect half of a lake because the other half is in dark water, we use the Peckel mask to expand what we detect. So then we complete the water mask with these dark water flagged pixels, where there is no height information, but they are important to assess area. So here is an example of a river, a very big one. So we have the classification here on the left. Now we have thrown out the land pixels here, so we only have the water pixels. So we see the Rhine River and also some lakes next to it. And here we see the heights given with respect to the VGS84 ellipsoid, and we see that we have bluish color over the river, and then different heights for the surrounding water bodies. We see that we also have some pseudo-random variations within the river. And now I'll show you another example, which is impressive and also a little bit sad, because this is what we observed when the Kharkovka Dam was destroyed in Ukraine. So we see that all of a sudden, when the dam is destroyed, the water level raises from something like 22, 24 meters to, it raises by about 8 meters from one day to the other. And we also see how the water expands, goes up this river and also expands into the city that is situated down here. And this is the pixel cloud. So this is a very quite noisy product, but we see that when we study it at a meter level, it is already very homogeneous at this scale. Of course, if we zoom down to the 10 centimeter scale, then we will see variations. But at this scale, it is already quite homogeneous. And it should be noted that this was done without crossover calibration. So in these images here, we can still have meter level calibration errors. So the river products actually, the lake level 2 HR river SP, which is the single pass product, contains two shapefiles. So we have a reach level shapefile and a node level shapefile. So all this is based on the prior river database, which is called SWORD, and which has center lines for a big number of rivers worldwide. And then every point, there are points every 30 meters or so along the river. And then we have what we call nodes, which are spaced by about 200 meters. And then we have these, the reaches that are in the order of 10 kilometers. So we aggregate data to the node level and to the reach level in these products. I will show you here an example over the Tsiri-Bihin River in Madagascar. So you see here the river, which actually are in both the right and the left SWOT. Here we see. So it goes something like this. So this is a river that is in the order of 200 to 300 meters wide. And here we see the coherent power. So this is what the power images looks like, and we see how it changes over time, especially for the nearby lakes with the dark water effects and so on. And then if we take a look at the pixel cloud for the two SWOTs for one of the dates, we see here that we have this evolution of the heights along the river, as we see it here. So these are pixels that are 20 meters apart or something like that. And then we can aggregate it to the node level. As we see it here, it's not quite the same extract, but we see also here this evolution of the heights along the river. And we see some anomalies here, which is actually nadir. What we see in red is the nominal tile boundaries, and the orbit is a little bit shifted. So looking at on the same thing as a graph, we see here again that we have this evolution of the height along the river, and then we see here that close to nadir we have a lot more noise. So the science requirements actually only apply to the nominal SWOT, which is between 10 to 60 kilometers from nadir. And we see that very close to nadir, we have a lot of noise, so this data cannot really be used. But we see also that we can probably go a little bit below 10 kilometers and still have good performance. Of course, the next step is to compare all this with...
Roger, you're close to
yeah, okay.
20 minutes, so you should go to the conclusion or shorten your second presentation.
Okay. Yes, so this is just to illustrate all the in situ activities that are done to, of course, assess the heights and slopes, and then there is also a lot of activities to access area based on satellite imagery. So yeah, and here is just an example on the Rhine River, where we have both pixel cloud data, we have also river SP data, and we have in situ data. And we see again that we have a good agreement at this scale, at least, when we're looking at it. So I don't have time to go into a lot of detail on this. We have some outliers, mainly due to assignment errors, when we don't assign pixels correctly. But you can refer to poster 56 to have more information about this. And we see here just the last slide with some details. This is for a few 3 gorges where we have that are very precisely leveled and where we have also SWOT data. And we see that we have a very good correspondence between SWOT data, even at the node level, which was expected to be quite noisy, and what we measure in situ. So I will just skip my outlook and perspectives because I have the same ones for in the next presentation. Should I switch directly, or?
Yeah, you switch directly to the third presentation, and we'll take the question after the third.
Okay.
But try to shorten the second presentation if possible.
Okay. Yes. So again, I would like to acknowledge the contributions of all the people that have been contributing to this. Yeah, the science requirements for lakes are basically the same as for rivers, or very close to it. So here we want to go down to lakes that are 250 by 250 meters, if possible 100 by 100 meters. And again, we have this for water surface elevation, we want to have high errors that are below 10 centimeters for lakes that are more than 1 square kilometers big, and then less than 25 centimeters for the smaller ones, down to 250 by 250 meters. So what we have in the lake products are actually different kinds of water bodies. We have connected lakes, that is to say lakes that are both present in the lake data prior database and also in the river database, SWORD, like the one that you see here. We have disconnected lakes. So these are lakes that are not connected to the river network represented in SWORD. And then we have these unassigned water features. So these can be lakes that are not present yet in the lake database, but it can also be false detections. So this is a little bit risky category. It can be water bodies, but it can also be other things. So the way the lake product is organized is that we have 3 shape files. So if we consider this example here up here, the solid lines are here, the water bodies observed by SWOT. And the dashed lines are the lakes or the polygons of the prior lake database. And then in this first shapefile, which is the observation-oriented shapefile, we basically have very directly what SWOT has observed as soon as these water bodies intersect a polygon in the lake prior lake database. And then we have this prior file, which contains very much the same information, except that it is split. Things are split or merged according to the lakes in the prior lake database. And this is the only one that includes storage change. And then we have this unassigned file where we put all the things that remain in the end. So the lake database plays a very important role. You see, it's important to use it to link SWOT observation to known lakes, and also this is necessary to follow things over time. The current version is mainly based on the circa 2015 database made by Yongwei Sheng. And then there are some additional lakes that have been put in. But it will also be updated based on SWOT data and the user feedback. So you can play an important role here. But you see that we have almost 6 million lakes in the database. So now I'll walk you very rapidly through the different steps showing how we produce the lake products. So here you see the pixel cloud. In this case, we have the Garonne River, then we have a reservoir that is on the Garonne River, and then we also have small lakes next to it. So the first thing we do is that we take out the pixels that have been already assigned by the river processing to regular river reaches. That is to say, everything except the pixels that are reservoirs, connected lake, which are present in both databases and that we will keep, of course, also for the lake processing. And then we identify the separate water regions. As of today, we take out things that are smaller than 1 hectare. And then we compute the different lake features, boundaries, area, elevation. And then we dispatch this data into the different output shapefiles. So to the observational-oriented shapefile, to the prior one, and then also to this unassigned category. While we are doing this processing, we do something that is called height-constrained geolocation. And we also make the link between each pixel and the different rivers and lakes. So this is what goes into this PixieVec product, companion product to the Pixel Cloud products. And it is based on these improved geolocations that we make the lake polygons. So here we have an example where we see all 3 products here for a lake in Canada, which is called the Aylmer Lake. We see here first the pixel cloud varying from date to date with the water pixels in blue, the detected water pixels in blue here we see. And then here we have the PixieVec product where we have this more regular spacing and also very strongly regularized heights. And we see also a river here, for instance. So this is computed only for the rivers and lakes that we have linked to the databases. And then here to the right, you see the lake prior product where we have this varying geometry, this polygon that varies over time, and also the color of the polygon represents the height. So we see that we have also some height variations or perhaps height noise over time. This is the same lake, and here we see how the water surface elevation varies over time, and also the water surface area. And we see that we have some anomalies here, which are actually due to some bug that was discovered in the low-level processing, and that has now been corrected, and that will be okay in the reprocessed products. Here is another example. This is on the Gérardmer Lake in France, where again we see how the polygon changes from day to day, and also the heights. And again we have these anomalies that have now been fixed. And we see here also we have reference data. So we have in situ citizen science gauge, and we can see that we are quite consistent with the in situ data. There are more details on this in poster 53, so take a look at that one to have more information and figures. Concerning the water surface area on the same lake, here you see an illustration of what we do. So we create reference masks over time based on Sentinel-2 data. And sometimes we also have higher resolution satellite imagery. And then we compare what SWOT observes and what the other imagery observes. And we can see that we are quite good, but biased a little bit high with the SWOT data. Perhaps here the Sentinel-2 water mask is also biased slightly below, but you see that in these cases that we see here, we are actually within the requirements of having less than 15% error. So just very quickly, so this is an illustration of the raster product. So this downs our resampled versions of the Pixel Cloud and the PixieVec to a 100-meter grid or 250-meter grid, where you have height information, water fraction, and so on, a lot of interesting information. So if you don't need 20-meter resolution, you can go to 100-meter resolution, and this product is very easy to use. And then we have this ambition to build a partial bathymetry that I already mentioned based on this Butterbrink approach. we have barely started looking at real SWOT data for this. So what you see here is really based on simulated data. So I reached my outlook and recommendation slide, which is common to both rivers and lakes. So you have seen that we have excellent results for SWOT over continental water surfaces. Of course, algorithms, auxiliary data, and products are still being improved, which means that they are not perfect. And I think a major step forward is that we are now delivering new versions of all processors for an upcoming global reprocessing campaign. We have already released to the science team some pre-validated products, and these will become publicly available from PODAC or from HydroWeb Next shortly, and here we are talking about days. And then products from the forward processing worldwide will become available in January 2024. So this is data that will be produced or made public with a 3-day latency approximately, and we will produce about 20 terabytes of data per day. As you see, the validation of the SWOT HR products with into-reference data is still going on, and the global performance assessment will be presented at the science validation meeting in late spring, early summer 2024. And also, beyond hydrology and oceanography, there are many opportunities for secondary science with SWOT data. So my recommendations are that you explore and enjoy the SWOT HR data that are now becoming available, and that you should identify the products that best suits your application, find out how to handle the data volume. If you are working on time series over large areas, it will be a whole lot of data. Very important, download and read the product description documents, because the products are quite complex with a whole lot of data in them, and there are some subtleties and some pitfalls. So read the documents, and very important, take the quality flags and uncertainties into account. If you use all pixels, all nodes, or all data, some of them will not be good. So it's very important that you look at these flags and uncertainties. And also something that is very important, if your favorite river or lake is not in the prior databases and then not in the products, or if they are not well represented, you should propose improvements to the databases. So this is something that is already available for SWOT through SWOT Explorer. And it is something that will be available very shortly also for the lake database. Thank you.
Thanks a lot, Roger, for the 2 nice presentations that show us how much we can do or we will do with SWOT. We have 3-4 minutes time for questions, so let's go.
Thank you very much. I mean, it's extremely impressive. We've been waiting for this for 25 years or more. I would like to ask you about the recommendations. For instance, could you add something like use SWOT in synergy with fully focused SAR from Sentinel-6 and see if 1 + 1 = 3?
Jerome, will be part of our seed questions.
Part of the seed question.
Yeah.
Very good. Okay. I see these recommendations that are very good to extend them to synergy with other sensors, including high resolution optical sensors, commercial images, and I just have a small question to understand the kind of noise. On your slide 15, you have this variation on the Rhine River from white to blue. Can you show us? Oh, no, it was the other talk. Yeah. Okay, forget it. Yeah. And so what kind of residual noise, and can that be reduced because this is not the final step or something like that? Or smooth or average?
Yeah, you should know each pixel, which its averages at around 50-meter resolution. But they have some overlap also. So I mean, you have random variations from pixel to pixel, but then you have actually you are averaging over a window. So there is some correlation. So actually, I think it is mainly random noise at this level, just that it looks correlated because we are averaging over windows.
Yeah.
So I think, I mean, when we planned, when we prepared SWOT, we told everybody you will have to average a lot. You have to average over reaches. That is to say, in the order of 1 square kilometer to beat down the noise and so on. Now we see that we have quite good data already at the node level. I mean, every 200 meters along a river, for instance. Of course, if you go below that, down to the individual pixels of the pixel cloud, then you will have random variations like the one we saw in this example.
Okay, just for my old ears, you said 60, 60 or 16?
I'm sorry.
The number you said it's 60, 60 or 16, the jitter that you have on the Rhine River?
No, I don't think I mentioned a number, but yeah, I mean, you have random variations for the individual pixels of the pixel cloud.
But what's the amplitude of that randomness?
Or that could be in the order of 1 meter or 50 centimeters and so on.
Centimeter, okay.
You should not use individual pixels. I mean, you have to average over, or go to the node products, node river products at least, or if you need really noise-free data, look at reach level or lake level.
Okay, and for me to understand your pixel cloud, the dot seems to be a bit distributed randomly.
Yes.
Don't they come in some kind of a grid from the measurement?
No, so that's this random. I mean, it's quite irregular in the Pixel Cloud product. And then we have this Pixel Cloud companion product where we have regularized them. So then they are much more regular, but it's still not a fixed grid. And then we have this raster product, and that's a fixed grid from day to day. So then you can also make time series and so on, but then you have gone from 20-meter pixels to 100-meter pixels.
Thank you.
Second question from the room.
Okay, thank you. Very interesting presentation. You mentioned that river discharge is being calculated. I wonder if you could tell me how it's being calculated and for how many locations?
Yeah, there is a river discharge working group that have been working for many years. And I think there are 5 or 6 different discharge algorithms that are computed. So, I mean, there are things we observe. I mean, we basically observe the width and the height and slope, but there are many things that we don't. Yeah, so there need to be hypotheses about bathymetry and so on. So there are. I'm not a specialist on that. Perhaps could ask to somebody like Kevin Larnier or some other people in the room. So, but there is an attempt to compute discharge globally. But there is not a requirement on the precision for that. So it's as good as possible, but it's not quite clear as of today how precise it can be.
So we need to move on. Pierre-Olivier Malater and Kevin Larnier are in the room, and you should come back to her and to them for the discharge approach. Thank you, Roger. The next talk will be given by Julien Renaud from CLS on the validation using in-situ networks on in-flight nadir altimeter missions.
Hi, everyone. So I'm Julien Renaud from CLS, and I'm going to show you today the work that we have done with Maxime Bayer, also from CLS, about the preliminary results of the Calval HR SWOT product using both in-situ networks and altimetric in-flight missions. So this work has been done in collaboration with Roger Fjørtoft and Nicolas Picot from CNES. So I'm going to be fast on that one on this slide because since the beginning of the week, we spoke about SWOT mission for hydrology. So you know now that we have a radar interferometer and this radar provides unprecedented 2D observations over inland water bodies and gives such variables like water surface elevation, so WAC. You are going to hear this word a lot today. Water stock estimates and discharges. So there is a high rate mode of carried, providing hydrology dedicated product. And there is also a low rate mode providing ocean dedicated LR SWOT product. So today you are going to see first results on the first phase of the mission, which is the CalVal phase. And the particularity of this CalVal phase is the one-day repeat orbit. And this one-day repeat orbit is very interesting because we are part of the CalVal team, so we know that we are going to have measurements every day on given site, even if the spatial coverage is sparse, as you can see on the map here. Okay, so I'm going also to summarize the main products that we have seen so far. So there are three main L2 HR products providing WSE and height. So the main one, the lowest L2 product, Roger speak about it, and this is the Pixel Cloud Pixie product. So you have two examples of variables that we can observe when we look at the Pixie file. So on the left, you have a dynamic animation of over the Lake Geneva in Switzerland, where we represent the sigma naught. So there is a clear contrast here between the lake and the land around the shoreline. And we can also represent the Pixie classification. So that's on the right part of the slide. So this is over the large Swiss lakes. And we represent the water pixel in blue and the other classes in green. And you can see the clear correlation between the optical images behind and the SWOT product. Okay, so this slide summarizes all the main products, L2 products that we have analyzed so far. So you have the Pixie file. So this is one value of elevation per pixel. So you have an example on the western part of the Lake Geneva, here, the Pixie file. Then there is the Lake SP. So this is only one value over that lake of WSE. And you have the similar observation for river. So I take an example on the same part of Switzerland. So you can see here, that's the river Rhone in Switzerland, where I isolate in the river mask the Pixie product and the river SP node. In that case, this is one value of elevation every 200 meters. So those products have to respect some science requirements. So again, Roger speaks about those requirements. So in that case, for WSE error, it has to be lower than 10 centimeters at 1 sigma for surface water bodies higher than 1 kilometer square. Okay, but so to meet those requirements, some correction have to be applied on given components of the total error budget. So you see this graph is not mine. It's a graph from a study of Gérald Debarbour et al. In 2022. So that's basically the scheme of all the components of the total error budget. So I'm not going to speak about most of them, but I'm going to speak today only on the systematic errors. So we know that those systematic errors, they are the main source of error for hydrology. So if you have to keep in mind a number, it's around 7.5 centimeter of RMS only for this error for a total requirement of 10 centimeters. So that's an introduction. Jean-François, sorry, speak about this crossover calibration correction. So to remove these systematic errors, we have to apply this crossover calibration correction called XCal. Okay, so it's developed on ocean product, so over crossover over ocean, and then it's interpolated to provide global correction on both low resolution, so hydrology, and low resolution ocean, sorry, and high resolution hydrology product. So the objectives of our study is to assess first the impact of those errors, the systematic errors, and the application of the cross-cal correction before assessing SWOT measurements with respect to the science requirements. Okay, so that's the quick slide for the overview. So we will assess the cross-cal correction on large Swiss lakes based on the analysis of Pixie. Then we will show the implication for the preliminary assessment of lake and river SP using in situ networks. And we will have example over the Swiss lakes and the river Loire in France. And finally, we will show you also the contribution that can have the current in-flight missions for the preliminary assessments of the SWOT product. Okay, so that's a slide showing what are those systematic errors. So I show you an example here of one Pixie file over the Lake Geneva again, but the eastern part. And then when we look at the WSE evolution, there is a clear constant slope. So this slope comes from the Roll and the phase error. So they are subcomponents of the systematic errors. And we know analytically that they have a clear linear signature in the cross-track direction. So it's even clearer when we look at the plot at the bottom. So that's the evolution of WSE as a function of the cross-track distance. If we fit a linear curve, we obtain a slope of 2 centimeters per kilometer. And we know that this slope is not physical. So we have to remove it from the data. And if we compare with an in-situ station, in that example, we see that there is 50 centimeters of bias. So the idea of the cross-cal correction is to remove those corrections to reduce the cross-track slope and the difference between the in-situ measurements. So that's the same graph now at the top, but with the cross-cal correction. And you can see that there is no slope anymore, and we are much closer to the in-situ station. So we apply this approach over 4 large lakes in Switzerland. So the idea is to quantify the residual cross-track slope over lakes during the calval phase, so for 1 month of data that we have, to assess the cross-cal performance. So we apply a cross-cal called the research F3 cross-cal during the calval phase, and we have 1 month of data. So every day we will have one value of WSE over those 4 lakes. And they are in a limited along track distance. It means that in that case, the errors and the combined cross-cal correction are expected to be similar. And they are, of course, in situ station to quantify the effect of the cross-cal. Okay, so that's one graph for each lake. So that's basically a time series. So you have time or cycle number, and in the y-axis you have the cross-track slope. So there is a color code. So the red crosses are the cross-track slope before the cross-cal correction, so in red. And in orange, that's the cross-track slope after the application of the cross-cal. So the first observation, if we look at only the red crosses, we see that there is a similar evolution of the phase and error, of the roll and phase error, sorry. So that's in agreement with the theoretical part. And then when we look at the orange crosses now, we are pretty happy because the absolute value of those slope after the cross-cal correction is systematically closer to 0, suggesting that globally the cross-cal correction is efficient. So that's the kind of more global application that we show, but that Jean-François already shown for the lake is equal. Okay, and if we zoom in one given lake, and we now look at the correlation between the difference between WSE from the lake SP, so one value over the lake, and WSE from in-situ station, and we correlate this variable with the residual slope, so the orange crosses, we obtain this graph. We compute the correlation, there is a correlation. So the coefficient correlation is around 0.7. So the meaning of this is that for relatively high absolute value of residual slope, so when the cross-cal is not well applied, then delta WSE is high, the accuracy of the SWOT product is not that good, and the systematic errors strongly affect the total error budget. But now if we stay in a given range of residual cross-track slope, so when the cross-cal is efficiently applied, there is no correlation anymore. It means that in that case, cross-cal is efficiently applied, the systematic errors are not seen anymore or not hugely seen, and you can see other error sources that are more visible. So we see that when we apply the cross-cal correction, it's efficient globally over the 1 month of the calval phase here. So the idea now is to see if the performance for those studies, those cases, are in agreement with the science requirements. So the idea is to check if we can respect these requirements, which is a WSE error of lower than 10 centimeters at 1 sigma for surface water bodies higher than 1 kilometer square. So again, we chose those 4 lakes in Switzerland. They have a large area, and but they have diverse sizes. Okay, so it's again a time series for each of those lakes. So the idea is to compute the difference of elevation between the in-situ station, so the blue crosses, and the elevation from the lake SP, so the orange crosses. And then we have a time series. We compare those 2 time series, and we compute the WSE error. So that's a pretty simple computation to make. So that's basically the average of the absolute difference of the absolute value of delta WAC for the number of observations that we have over time. So it's around 30 days. So if you look at the label for each graph, you have a number, and that's the number of, that's the WAC error, basically. So we are pretty happy because it's between 4 and 6 centimeters. So we are well below, at least for that cases, at least for that legs, given legs, we are below the science requirements, which is 10 centimeters. Okay, so we are speaking about lake, but we can do the same analysis over river. So we select a nice case because we are lucky in France to have a dense in situ station. So it's called in situ station network, sorry. It's called the Chapi or Vigicru. So we select an area here in the western part of France. So you are between Nantes and Angers over the river Loire. And there is a section of 60 kilometers of river with 7 in situ stations. So if we look at one station, and now we look at the river SP node product. So you have a zoom here, a map, and we select the closest river node SP product to the in situ station. And again, we compute the difference between the elevation of the in situ station and the SWOT product. And we obtain an error at 1 sigma of less than 4 centimeters. So that's pretty good results, and I suppose that you will see this kind of good results also for during the next presentation over the Garonne River, close to Toulouse. Okay, and then a last comparison with the in situ, but now that's a dynamic plot. So we can go to the lowest L2 product, so the PIXI file, and the idea is to select all those PIXI in an area of 1 kilometer square, and to select only pixel classified as water, to weighted average them, and then to compare to the in situ data. That's an interesting case here because you can see that over the first 2 weeks, there is a decrease of the elevation of around 1 meter seen by the in situ station. And when we look at the weighted average value of the PIXI, there is a clear agreement, meaning that SWOT is seeing this decrease of water surface elevation. Okay, so now I'm done about the comparison with in situ station, but we can also use current in-flight mission to make some comparison with respect to SWOT data. For example, you probably know the database Hydroweb. So that's a worldwide database of lakes and river WAC derived from altimetric measurements, so Sentinel-3, Sentinel-6. There is a lot of lakes, more than 200 lakes, and more than 20,000 rivers. So there is a huge potential for future comparison. So that's a nice slide made by Maxime, but he showed 2 examples of comparison between Hydroweb and the SWOT lake SP product over the lake Isigul, so you know the lake Isigul now in Asia, and the lake Vänern in the southern part of Sweden. Computation again of the error at 1 sigma, and we are below 10 centimeters. So that's again a proof that the quality of the preliminary assessment, at least, of the SWOT product seems promising. There is Hydroweb, but there is also ISAT2. ISAT2 is a LiDAR WAC estimate, gives a LiDAR WAC estimate since 2018. And there are potentially tens of thousands of future comparison of water bodies that are observed both by ISAT2, but also by SWOT. So we represent, we've done some preliminary analysis. So you can see the histogram here. That's the difference of elevation between SWOT product and between ISAT2. So basically, to have the WAC error here, you just have to compute the standard deviation of this histogram. So there is no bias. That's the first good news. And the standard deviation of this histogram is around 9 centimeters. So the good news is we are always below 10 centimeters. Okay, so as a conclusions and outlook and recommendation, so we've done the validation of the crossover calibration, at least over 1 month of the Calval phase. We see that globally there is a reduction of the impact of the systematic errors. When this cross-cal is well applied, the lake and river SP products are within the science requirements, at least for the cases that we have studied. But then there is also a potential of using the current in-flight missions, so Sentinel-3, Sentinel-6, ISAT-2. They are of key interest because they can produce a very large number of comparison over water bodies. So in terms of outlook and recommendations, so we know that we will do an equivalent approach soon when we will have the reprocessing of the full CalVal dataset with another type of cross-cal. So it will be like during the year 2024. And then with this kind of promising results, we can think about a potential integration of the SWOT project into Copernicus services and HydroWeb. And that's all for me. Thank you.
Thank you, Julien. Again, very interesting and promising result from SWOT over different surfaces. One question from Jérôme, short one, please.
Very short. Excellent. Excellent work. It's mind-blowing. I just want you to add
Short, Jérôme, short.
CRYSAT-2 because you have similar sub-cycle of CRYSAT-2 than SWOT. And you can probably find somewhere in the SWOT some CRYSAT-2 data. Pretty dense network.
I will add about it.
Certainly, yes. Another question from the room? So I guess that many people are eager to have the authorization to play with SWOT data. We will move to the next talk. That will begin by not Jean-Christophe Poisson, but Elliot from the Vortex IO team on the similar analysis, but on the specific cases over the Garonne River. Again, 18 minutes for the talk and 2 minutes for the questions.
Okay. Thanks, Nicolas. I'm very pleased to be here to present, to share with you the results found at Vortex about the SWOT mission. As a reminder, as a presentation of what we did at Vortex. So we have two different main missions. So the most obvious one was to check the mission requirements and understand the source of uncertainty. So to do that, we have a network of in situ data. We have many sensors deployed in France and other countries, and we used to get the 8 level in many rivers. We have also moving sensors to have a precise height levels, and many tools to check U values and to have a very precise location of stations to have an uniformization of the levels around the place we studied for SWOT. So the first mission was to have a reference height, to have something comparable to SWOT and give to SWOT a grand truth height level. So it's exactly the same mean absolute error that we try to reach d centimeters 1 sigma MAE. And also understand the source of uncertainty. We try to reconstruct to start from the PIXI and and process the data to try to find height values the easy way as possible and find and evaluate the origin of noise and the lack of accuracy. I need to warn you that this presentation contains some conclusion, but we definitely not can jump to any conclusion with this content about SWOT performance. So just quickly the Garonne River in France. So we have the position on a raw PIXI and on a map. This is a pretty complicated place because the Garonne has a behavior very non-monotonous, and we have two specific zones, and we are focused on the downstream Garonne. So downstream Garonne is illustrated here with a PIXI of cycle 560. We have a very lot of sensors on this place. So we have many data to compare with SWOT and gives to SWOT some ground truth height. We have a lot of sensors, and it's going to be and then will be maintained. About the moving sensors, this is just to allows you to see what those moving sensors looks like. We have the airborne lidar, which allows a very fast acquisition, so it's pretty comparable to SWOT. And the drones, sometimes the drones are concatenated from several drone flights, and we have a very detailed height on the river. Now, just a little presentation of how we think the dark water can degrade the measure. Sometimes the dark water points are not evenly distributed. As a consequence, since we take the median of for example, a reach selection point, it can shift the median point and it gives to us an error. So it's illustrated here. This is the heart of this presentation, because here is the process we did at Vortex. So we focused on one of our microstation network, and we have two main parts. On the first part, we start from the pixie, and we try to analyze the pixie. In fact, to see the potential of the pixie. So we have step one, which is very simple. We take a reach-like, so it's 1 kilometer square selection on the ground, centered on the microstation, and we compare without any additional correction the height from the microstation and this median taken from this 1 kilometer squared selected points from the pixie. Step two, we do exactly the same, but we had a slope correction. These slope corrections can be from a simple linear regression or from moving sensors data. And finally, step three, we do the same, but on a very small area in order to make the noise and the slope the most negligible as possible. And as a consequence, it allows us to check the value found at step one and step two. And finally, we take a look at the Hydrospace product. So we take at step four, excuse me, take our microstation, and we compare. It's very simple. We compare to the nearest SWORD node. So it's a first very simple comparison. And for step 5, we take a look at the whole Garonne downstream area. So we use, for this step 5, we use airborne lidar to have a comparison of every cycles available for this part. Step 6 is not presented here, but it's going to be our next mission. It's doing the same, but for reaches, but it's not going to be presented here. Here it is the result for step 1. To be clear, the blue curve is the value, the height from Vortex. We took three different microstations: Couture-sur-Garonne, Marmande, Le Mas d'Agenais. And the dots, the blue dots, represent the SWOT measurement. So for step 1, as a reminder, it's the 1 kilometer squared around the microstations. And we take the median. The color represents the proportion of dark water as an information, additional information. What is very, very interesting is that at Marmande, we already meet the requirement because we have 5.2 centimeters MAE, 1 sigma MAE. So it's very, very impressive. But for Couture-sur-Garonne and Le Mas d'Agenais, we have finally a normal offset, an expected offset. And have a look now if we correct the slope. So Le Mas d'Agenais is now pretty good because we fall off. We go under the 10 centimeters of 1 sigma MAE. Marmande is even better, and Couture is still offset. So for Le Mas d'Agenais, the fact that correct the slope correction, correct the slope, make the results very good. So now for the step 3. So step 3 is to check the height for step 1 and step 2. Here we have hold the light to green. So it's very impressive because I remind you that this is only Pixie, and we meet the requirements for those 3 stations. So we can conclude that the noise and the slopes can occur the offset we saw just before. Now have a look at the river SP. We have at Marmande, in fact, it works for any product we saw, and we have some bias at the 2 other stations. We have some points that are pretty near the curve. For example, the Mas d'Agenais, we have points which match the curve, and other ones which are very far to the curve. This is just a synthesis of the numbers I saw just before. What is very important to see on this table is the fact that at step 3 everything is green. So from the Pixie we can already meet the requirements. So it's very promising. And now this is probably the main graph of this presentation. Step 5. So we take every cycles available on the database, and we compute the MAE for each point. As a reminder, it's compared to airborne LiDAR from Vortex data, and we can have this curve. What this is very important to see is that the MAE seems to be pretty continuous along the river. We have some places which is better than others, but it seems to be constant along the time. For example, at some places there is for example along Saint-Pardoux-du-Breuil we have places which is maybe noisy or affected by the dark water. As a conclusion, in fact, as I saw in the table, for example, at Marmande, in fact, the target accuracy from Pixies can be reached very easily in the major part of cycles in the location we work. The signal is pretty less noisy than expected. It remains some bias, but what is very important maybe is that maybe the SWOT data can raise more accurate data than expected. And in my mind, dark water is really the most important thing that we had to consider. And finally, we already see that river ops, so for the river SP, for example, at Marmande, allows prevent noise and dark water at some point to affect the measure. Finally, so as you can see, those data are very encouraging. I repeat that this conclusion is a very, very early results, so it cannot be used as a final conclusion. Something very, very important is also that moving sensor data is very important, at least for us, because it allows us to draw the impressive curve of step 5. And the homogeneous of the data is very, very important also. And we are pleased to install as much station as possible to help SWOT Calval. And as a conclusion, the SWOT data is very, very prometheus, and be patient because SWOT data arrives. Thank you.
Thank you, Elliot. We have time for some questions from the room, if any.
I have one question for you. I have one. Thank you very much for your presentation. It's interesting because you show that even without the reprocessed data, we already have some good results, but there are some problems still that you have shown and well illustrated. I just have a question which is related to the Calval. So you did the Calval right now, mostly for the water height, but Calval is also can also be done over river for the water mask. And we know that we have a lot of dark water, still dark water. And using the drones that you have, is there also a possibility to simply make maps of the bank of the rivers and to compare to what SWOT is measuring in order maybe to reduce or to understand better the errors on the height due to the dark water?
Nowadays, I would say that it should help, but in fact, those locations of dark water are pretty misunderstanding yet. So not sure the drone might help, but to understand. But I'm not sure to.
But is there simply a camera on the drones?
Yes. Yes. Not sure to kind of give an answer to this question, but it might help.
There is also camera on the microstation as well. On the microstation,
Yes.
provide you directly the width of the river, indeed,
Yes.
which is a very valuable.
It should help.
No, it shall not help. It is of tremendous interest to help the size of the rivers, and it also provides the river not discharge, but the river speed at the surface, as illustrated 2 days ago by the other teams. So your system is of interest not only for the height, but as well for the width and potentially for the discharge.
Thank you for your presentation. I have 2 small questions. One, for the institute stations you are installing, it will be available in HydroWeb or in some or VGCrew somewhere. So it's my first question. To access to the data in the future, you say it will be maintained. My second question, if I understood correctly, you show the RMSO you got on the Pixel Cloud with the step number 3, where you are this one, where it's quite good, step 3. But then when you look at the river SP product, it's not as good. So it means the treatment you are doing from the Pixel Cloud is better than what is doing with river ops at the moment?
Not exactly, but in fact, it's not pretty comparable because it's not exactly the same construction. In fact, what this table says, it's that we can produce more accurate data with, I mean, less error, because we have only 200 meters around the station, and as a consequence, we are less affected from the noise and the slope. This is, I think, the main message of this table.
Roger will complement the reply for the second question.
Yes, I mean, this can be a little bit confusing, of course. What is important to note is that we have been talking about dark water, and the places where we have bad results is often places where we have dark water. But then we don't use the dark water pixels to retrieve height. So why are they creating problems? And it's because in the areas where we have a lot of dark water, we actually detect some pixels as water. And often we've seen it's on the river banks, actually. So we have almost no data, but the few pixels that we have are perhaps on the river banks. And then they give us big errors in these places. So it means that there are still things to refine in the river processing with respect to that. But then also river processing already includes some robustness in the sense that it should eliminate biases that comes from the fact that perhaps some parts of the river is missing. But if, I mean, the upper 1/3 of a river reach is missing, the river processing will take that into account and extrapolate. So there already is some robustness to that. But I mean, there are still things to be refined in the river processing. And what's important to note also is that sometimes you see here figures that are obtained at a smaller scale, at nodes or over a smaller area, whereas the requirements actually apply at the reach scale, which is 10 kilometers or 1 square kilometer lakes. So that's also one of the explanations. But yeah, it only shows that there are still things to refine in the river processing.
And as usual, it's quite complex to refine a processing that is not supposed, but shall process the whole world. So river ops is done whole world, globally. And it's quite complex to implement a method that is suitable to all cases. Here we are doing adequate or a priori appropriate processing suitable to Galwan sites.
Yes, just to complement, yes, the data from the microstation will be available on Hydro next for the Calval mission. And to answer you, Jean-François, yes, with the drone camera, we can perform orthophotos and see the riverbanks, so maybe it could help, hopefully. And with the microstation, we have also a camera on board that can look at the surface roughness, and maybe we have to work on this specific topic to see if we can have a surface roughness estimation or indicator in order to make the coherence with dark water locations.
So thank you. Thanks again, Elliot. Now we will move to the seat questions, hoping that we will have some interesting debates in the room.
Thank you.
So 6 sessions in the row to address some seat questions. So there is obviously some overlaps between the different sessions. And with Jean-François, we have proposed to focus on SWOT, on the complementary with what we could say the altimetry or heights informations. So what we propose to discuss before the coffee break will be, how do you envisage the combination of SWOT data on other satellite altimetry data, providing 8 informations, so including ISAT2. And Jérôme has kindly reminded us cryosat mission as well, which was not yet looked at as part of the Calval phase for different reasons. But this is quite, I would say, challenging questions, and maybe quite challenging issues, because we are looking at very different sensors, but we welcome your inputs on that first questions, if any. Nobody in the room, even on CLS side?
Cédric?
Julien, you have certainly some thoughts to share.
Cédric, you can do.
Julien, after.
Hey, perhaps not directly related to Crystal Sentinel-9 and ISAT-2, but I think there's been some suggestions this morning that looking at the historical measurements of nadir altimetry, we already have 20,000 sites around the world with historical height observations. And now that we have a little more confidence on what SWOT might provide, and it'll give us more than just height, right? Width and maybe even discharge at some point. I'm optimistic to think that we can look back in time as much as we're looking forward with new measurements. And I think this seems to be a low-hanging fruit of something to be done, which would be combining SWOT data with historical nadir altimetry missions and go back to the future. I'll stop here.
Thank you. Julien, maybe.
Just because I have no choice, but yep. So there is definitely something nice to do. When we look at the performance of Sentinel-6, so during the presentation of Nicolas yesterday, but also during the presentation of François at the first day of the meeting, and soon the presentation of Jean-Alexis. So there is equivalent performance. There is also the off-nadir approach that can be on the Sentinel-6 that could be validated using SWOT data, or the other way around. So, but there is definitely very good comparison to make, and of course to continue with the proposition of the comparison with the Cryosat-2. We can use the fact that it's a derived orbit. So there is a potential for computation of slope, not only computation of WAC. So we are already thinking, I speak as part of the CalVal team, we are already thinking of this combination, not only comparison, but also combination to improve the accuracy of the product that we provide.
Thank you, Julien. Nicolas? Just to complement the remarks from GPL team. Indeed, we have, I would say, quite good metrics now, recently, on Sentinel-6 performances over inland waters. But if we look at LRM data, like JSON-3, we actually do not know yet what will be the accuracy and precision of those LRM data in the past. And I think that SWOT missions can help us better understanding the error budget of the so-called LRM JSON-3 or equivalent data acquisition worldwide, not only looking at the sites where we have in situ data, but where with a SWOT capacity to observe worldwide the rivers, including some complex cases with potentially I would say, ice on the rivers as well, will make a giant step forward in the better understanding of the altimeter performances for all past missions as well.
So to complement this answer, I will focus my answer from the downstream services Copernicus site. Indeed, SWOT will bring us a global view of all slopes, all those information over the world, and those are very useful to exploit and to better exploit the nadir constellation we're having now. So we saw that yesterday in my presentation. So I think there is a real complementarity in both, to develop the downstream services. And as we also saw in François Boy's talk, nadir altimetry is still very present. It has really great performances on very small rivers. So I think the combination of both views will really be efficient from downstream applications.
Yes, but the important the term is combinations. Today, up to now, you mentioned most comparison or CalVal. We have a sensor that is providing a grid or a river, I would say, slope along the rivers, and we have a sensor which is providing a point, virtual stations, with a moving ground track. How do you envisage the combination of the moving sensors like Sentinel-3 on the SWOT which provide imagery of the rivers?
Again, I think a way to really combine is to address the question of the slope of the river between two virtual stations done by two different altimeters. So it has been solved partially, actually, by with some people that calculated the slope of the river, but slope of the river is also changing in time. So maybe there is the possibility to combine SWOT, which provide the instantaneous slope of the river, and also variability of the slope of the river all along the rivers with the virtual station, and to combine them for the future.
So yeah, to address also the first point. So we had some really good result by combining all the nadir emissions along a reach of the river to densify the time series. So given now that with SWOT we will have very good spatial resolution, so adding that on top of the nadir altimeters, I think we'll be able to really densify the time series and achieve much better resolutions by combining the two products.
Thank you. Next one.
Hello. For sure, SWOT give unprecedented spatial resolution for hydrology. But one thing, it's unfortunately the accuracy of SWOT will be limited by geoid model. And for floodplains and estuaries, the zones of backwater effect, it's probably SWOT cannot achieve the good flow direction for the water. And maybe it's good to try to make some connection for improvement of geoid models, for test another geoid models, because for sure, like Jeff showed, 2 meters or 3 meters of error on geoid model for flat zones would be really critical thing for SWOT. It's just
So a practical way would be the first would be to think to put the altimeter in the nodes of SWOT. Perhaps
The altimeter in the
node of SWOT. So we have this node along in the product where we have a value every 200 meter. So we could try to put the nadir altimeter in this point, but we will have to decide if we put this time series all in the same or in different. This is a practical problem. I don't know if someone thought about this.
Thank you, Luciana.
On very concrete applications and downstream services. So we use a lot of our drone solution to deploy during flood events, because we need to have the water height all along the different flooded areas. So we are working a lot with emergency services and local authorities to provide these maps. But definitely, if there is SWOT that can perform these measurements at a wider scale, if we have the chance to have another pass of SWOT in the flooded area, it will be very, very useful for us. So definitely we will use SWOT data during flooding events.
Thank you, Jean-Christophe. Roger?
So we have been talking a lot about water surface elevation. Of course, we see that for SWOT, the water surface area or the water mask, it's a challenge also. And I think there is a lot of things that could be done combining SWOT data with water mask from Sentinel-2, Sentinel-1, also the upcoming NISAR mission. I think there will be also independently of SWOT, there will be services coming where watermarks are computed dynamically and worldwide with an update rate that is quite high, and that is also something I think is very interesting in the perspective of Sentinel-2 NG, where the resolution will perhaps be lower and where it will be even more important to work on several sensors simultaneously.
Thank you, Roger, and thank you for the room from your contributions. We will move to the second questions. What would be the characteristic of the best complementary missions that we should wish for the futures to complement SWOT on the current constellation of satellite data. On the related question, have you already heard about SWOT SMASH concept mission that was proposed years ago by French? And I have a flyer in my hand from a French company that is trying to launch the same initiative again.
In answer to your third point, yes. Hey, listen, but along those lines, I think as we celebrate the success of some of the optimism we can have on the SWOT mission, we have to recognize that temporal sampling is still a challenge. And we expect SWOT to be able to see about half of the world's floods in its mission during the mission duration. But there are, and by that we mean see a flood once. We may not see the inception of the flood. We may not see the death of the flood. So we're not going to know anything about event duration. And then there is the other 50% that we're not going to see. So I think my opinion on best complementary would be making a full temporal resolution. And that brings back to your third point, which is a nice concept for helping with that.
Thank you, David. So if you are not aware about SMASH, I have plenty of SMASH flyer available on the desk. And there is a poster as well.
I agree with Cedric, but then it becomes also complicated because in terms of, okay, if you have a SMASH or with a daily mission, it will be very, very interesting, but it will be only on a few points. So in terms of discharge, what we do with SWOT, in fact, of the official discharge product, we will compute the discharge at the time instant of the satellite. And if you, on a river, on a large river, if you look at Amazon or Congo, if you have one observation every 5 days or 6 days, maybe it's a slow dynamic, so maybe it's enough. But on most of the rivers, even medium-sized river, in a few days, you can have lots of events. So then if you want to propagate, to use the information with a SMASH mission, for example, to all the reaches, then you would have to use models, either hydrological models or hydraulic models, unless you have a huge constellations with lots of satellites. So then it becomes more tricky in terms of global application with models and this type of stuff. So, but it's a very interesting challenge, and certainly my answer would be the same as the one of Cedric: higher frequency, daily frequency.
Thank you, Pierre-Louis.
I have the same argument because for the classic altimetry data, it's not every time and not everywhere. And now with SWOT, we have not every time, but everywhere. So
not everywhere with good quality.
Yes, but for me, we will have a best photography of hydraulic and hydrology for 3 or 5 years, and we can make a lot of correction between place, perhaps between this time, and after the point will be effective to have a better frequency acquisition. So I go in the same way than the previous.
So everybody, at least 3 of you are wishing to have a better frequency revisit time. Any other input from the room?
Regarding the instrumentation of the SMASH, with better frequency and small satellites, what will be the altimeter instrument? Is it the same quality?
No, it's definitely not the same quality than the one embarked on Sentinel-6 or even Sentinel-3. It's a low-cost instrument to be able to have constellations. So we have to perform some choice. At industry levels, we are not capable of flying a constellation of SWOT, neither a constellation of Crystal or Sentinel-6 in terms of instrument. It's much too costly. So the concept was a very simple radar inherited from SAHAL, 8 Ka band, which provide quite good metrics in terms of performances. And we expect to be able to have 10 centimeters accuracy over most rivers and lakes observed by this constellation. As said by Pierre-Olivier and Cédric David, it is nadir only, so it's not full observations, but it could provide complementary data over many rivers where we are today blind in terms of observations at this frequency.
Similar to Saral, Arctic?
No, it's a different height as well.
Thanks.
Yeah, I revisit. So the first step is to demonstrate the concept. So we have to make this first step at agency level, I think. And we are debating about these concepts in maybe 5 years. And we have not taken the chance to find a small amount of money. It's a small amount of money. The SMASH concept is roughly $30 million. 30 million only in front of the $1 billion for the SWOT missions. Just to demonstrate that this is working, flying, promising. We didn't succeed yet to find this small amount of money, small for a CNES agency, not small for the research, I apologize, but small for, I would say, a satellite program.
I wanted to make a small clarification. I think, so in your seed question, excellent seed questions, by the way, the word complement, I think is really important. If we, fly SWAT and we're hoping it's going to be a decade or more, right? But it takes time to design a new mission. And even if we're optimistic and maybe the SMASH concept or something similar would fly down the road, it would be really nice to have both at the same time.
Sure.
Some kind of white swath and some kind of nadir with enhanced frequency. I think we would learn so much from having both together, and it would be unfortunate to miss the opportunity.
Sure. 5 years ago, we wished to have SMASH flying during the SWOT one-day orbit. Unfortunately, this was not done. Not done yet. It will not be done. But thanks to the SWOT one-day orbit, we also have observed what we observed thanks to the one-day revisit time. And the Adrien Paris and several teams have illustrated the importance of the high frequency in terms of observation, in terms of data screening, in terms of data selections. It's much more easy to select the right virtual station accuracy. Is much more stringent or direct when you have a one-day revisit time compared to a 27 days. Within 27 days, you just not know what has changed on the rivers or on the lakes. Within 1 day, it's much more simple. But we have to make this demonstration in flight. And yes, Cedric, we hope that it will be possible to fly SMASH concept during SWOT being in orbit. But some decisions have to be done.
It's not too late, in fact, because SWOT is supposed to, so it was designed for a 3.5 year of mission, but of course, we still hope that it will, and we hope, and we strongly hope that it will be much longer, at least 2-3 years more, maybe. And SMASH, of course, still not have any of the satellite from the constellation, but it will not need 10 years or 15 years of development, since it is based on a very well done and technology that we know how to and in a simple way with microsatellites, so not too expensive, as said by Nicolas. So I don't think I think we can push as a community that the space agencies they develop very quickly this SMASH mission.
If somebody put 30 million on the table today, SMASH will fly in 2 years.
I believe the most important complementary mission would be one that gives us water speed.
Will be the?
One that gives us water speed for rivers?
Water speed.
How fast the water is moving in the river? Yeah, I mean, I don't know what the technology is going to be, but I think that's our challenge. We've demonstrated we can do it in certain conditions with optical imagery, as I presented yesterday, but it's by no means a solution that's going to work everywhere all the time. So I think we really need to work on that, because the speed of the flow is such a critical parameter for river discharge for water resources, but particularly for flood impacts.
Yeah, I think that Tandemix has done some demonstration as well in the past about the capacity of the radar interferometry to measure the river speed on some rivers. And I know that as part of SWOT 2, because there is a SWOT 2 with a not initiative, but already discussion between NASA and CNES, they are thinking of some interferometry project which could have this kind of capacity to measure the Doppler at the surface. Merci, Jérôme.
Actually, it's brilliant that you say this because I was telling Nick that somebody at DLR TandemX has done it, but I cannot remember who, but it was presented at a meeting a long time ago. Do you have a reference for?
I will find it back.
Thank you, because I cannot. Thank you.
So I think that we are done for the seed questions. Thanks for your contribution. Again, if you want to have some information regarding SMASH concept, take a peek. I have several, and it would be wise to push on your side regarding these concept missions.
Nicolas, I have a question which goes a little bit beyond hydrospace. The rivers usually get into estuaries, and then they get into the coastal ocean. And I'm very fond of the coastal altimetry workshop. I organized 12 of them in the past. When you have a tidal bore, you know, in French, mascaret, in Brazilian, I think, pororoca for the Amazon River. So you have a series of waves that surfers will ride for about 20 kilometers. They really enjoy it. And so SWOT will maybe see these waves in which we could even see the wavelength and so on. And it comes to my mind that SWOT was supposed to not work at all in rough seas where there's big waves. So at some point, the measurement will be degraded and then will maybe disappear. So does that mean that
No.
Let me ask a question.
Yeah, go on. But regarding significant wave height, we have demonstrated some months ago that we are not sensitive at all. SWOT performances over swell up to 8 meters are much better than the currently flying altimeters.
Yeah,
much better.
So does that mean that by following the evolution of the performance of the SWOT data, can we infer a lot of things about waves?
Sure.
And we have in the room a wave specialist, Sonia Ponce de Leon, who was a visiting scientist at ESRIN. And she's really interested in supplying high-resolution modeling to the estuaries, to the coastal zone around the estuaries. And so can she exploit SWOT data for her wave work?
Sure. I think there is plenty of people working with Sentinel-2 or Pleiad imageries to infer the swell characteristic as a relationship to the bathymetry. With SWOT, you see the same. And we have HR data close to the coast, and we have some illustration provided by CNES already that illustrates the capacity. And over the oceans, SWOT see very, very well the internal tides. If it sees the internal tides, it will see the mascaret, for sure.
Thank you. And we have to organize the 14th
workshop. Take your SMASH flyer before going out to the room.
The SMASH poster is the first poster on the first floor. It's a copy of the flyer. And you have flyers all over because Nicolas made copies.
And thanks again for the presentation and for your time during this session, and have a good coffee break.
Let me just add that we'd like to really thank the chairman for the seat question, the discussion. We also would like to make sure that you have a red dot on your badge that allows you to board the bus and also enter the restaurant if you're coming from downtown. And if you don't have a red dot and you change your mind, if you want to change your future in the next 12 hours, then go to the reception desk and get a red dot.
Okay, good afternoon, everybody. We can start this session 1.7 entitled Advanced in Remote Sensing Methods, Techniques and Products. My name is Marco Restal and I'm co-chairing this session with Jiaming Chen. We will have 5 talks and we start with Jean-Alexis Dagouzet from CLS with this presentation entitled Using Image Processing Technique to Detect Rivers in Sentinel-6 Fully Focused Radiograms and Improve Water Surface Height Retrieval. Thanks.
Okay, thank you. Hi, everyone. Thank you for having me. I'm very glad to be able to present to you some work we are doing at CLS with the support of CNES to improve the water level retrieval over inland water. And in particular, using the fully focused R data with Sentinel-6. So a bit of a context, of course. As you know, in the last decades, we in the community have spent many efforts trying to improve the water level retrieval from the complex areas that are the inland waters, and in particular over rivers. So here I will focus on Sentinel-6 data with the fully focused R processing. And we intend to exploit this data for nadir, but not only, also off-nadir water level retrieval. And we will see how we try to use image processing techniques to help us to do that. So as you know, the fully focused R improve a lot the on-track resolution here. So there is a simple sketch here illustrating this in comparison to the low resolution mode. In the rectangle here, green rectangle here, you have the SAR footprint, and in red, even more smaller in the on-track resolution, you have the EFF-SAR, which would improve a lot the resolution in the on-track direction only. I'm going to present you some perspective here on of one case study, which is the Creuse River in France. I very interesting in this situation because you can see that there is a Sentinel-6 track that is flying over the river for a long time, and you have also some 2 main rivers that you may see a little bit of nadir here, which are the Gartempe and the Anglin. So also there is some bifurcation here that may be interesting to see. As you see here in the shadow, blue shadow, you expect maybe to see them also in the radar, since the footprints should eliminate the 3 rivers. So here is my basic configuration here. I processed the 11.1a data from Sentinel-6 to produce the usual waveform, multi-loc waveform, using a sampling rate of 140 Hertz, which is about 60 meters along the track. So basically you have one waveform every 60 meters along the track. So my data set is about a bit less than 700 waveform. And I use the SMAP processor here. So if you want to check out what it is, you can check the GitHub website here. We just adapted it to Sentinel-6. So if you pick up some waveform, for example, here at the crossing point, you might find some classical waveform, peaky, very nice to retrieve the information of the water level. Those are specular returns that you like, but this is not always the case, and sometimes you can find multi-peak waveform coming from multiple backscattering seen in addition of the noise, of course. So sometimes can be a mess. So by stacking the waveform in the unitrack direction, you can see more like an image, and then it becomes more clear for your mind. As you can see here, the rivers appears as bright curve into the pseudo image. So this is very interesting, and we want to try to exploit this information, and it's not done for now for the Niger altimetry. So this is the starting point, seeing this as an image and what we can learn from that and how we can use it. Also, just to mention that we have some artifacts here coming from the fully focused R processing. I'm not going into much details, but you can find those parabolas that can also that are very here well known, and you can see that it can disturb your signal. So when you just look at individual waveform, you can be trapped by those signals. So it is very interesting to see this as two-dimensional image. Okay, so question one, how to use image processing to isolate not only the nadir, but I mean the entire scene, the entire signal from all the rivers, not only the coast, but the three main rivers we don't identify in the map. So we spend a lot of time trying different techniques. I'm just going to present a sequence of steps we perform here to produce actually our binary mask, because one of the steps is to isolate the river to produce a binary mask that you can use then afterwards for the retracking. So we perform some image processing techniques like contrast stretching that can improve based on the histogram, basically improve your image brightness, for example. On the step 3, actually this is the main filtering step here, which is quite simple to use. Actually, it's pretty fast. It's performing a Sato filtering that is very suited for this illness-like detection, as you can see here. So it's very well used for medical imagery, for example. So I thought it was kind of interesting to see what it can do over those FFR images. So this is a Sato filtering image on which we can perform thresholding. So maybe not simple thresholding, since we use the information of your Sato image here of different levels. You can see you have some different high region and low regions. So perform hysteresis thresholding that can help us to connect those regions. Okay, then you can keep the segments that are detected, combine it to produce a binary mask. So this is what we want. We want the binary mask here. Here we have the contour. And if you just overlay both of the binary and the original image, you can see that you kind of select mostly the river signal here. So not only the cruise one, which is the brightest one, but
Excuse me.
also
If you're using the mouse to point on the slide,
Oh, yeah.
make sure that the cursor is on the screen. So move it outside on the right, and it will appear.
Oh yeah,
here.
sorry.
Yes.
Okay.
Okay. Thanks.
Okay, thanks. So yeah, okay, you can see basically that you can catch the off-nether signal here in addition to the cruise river that was more in the Nardi part here. So it's very interesting. So let's say you are happy with the segmentation here, which I am for the moment. Question 2 is because you are still blind, but this can help you to have sub-waveform, basically coming to the individual waveform for the tracking, but how to connect the reverse IDs, how to know to separate the information. Because you have some different interval candidate for one waveform, so how to separate. So this is question 2. To do so, we use the external database, which is Cartage or Topage. This is the same. That is built of a contour in shapefile format containing elevation. So this is all static, but very interesting to perform simple simulation. So here you have a simulated radiogram, and the color is the river coming from the ID information. So this is very interesting because it with the eyes match the real data here, and you can also separate the different return depending on the rivers, thanks to this external database. So this is not a perfect match. So the next step would be to align both. So to align the simulation to the real data. So what we do here is we use the what is called the optical flow algorithm. We use one of them, the Farnbach, and that allow us to register the simulation into the mask. I call it the target mask coming from the segmentation. So when you do that, you apply a watershed technique to fill in the mask with the appropriate IDs. So this is the final output here, a kind of a smarter binary mask containing IDs information that can help you then to perform a tracking. Okay, just to summarize the process here. So we have the waveform. You perform image segmentation. In parallel, you have the simulation. You combine both with registration techniques, water body identification with the ID, and then you have your final output, which is just a prior knowledge for the retracking then. So question 3, how to retrieve the water level. So this is the retracking part. So as I said, for then each individual lines, this is individual waveform, you have interval candidates that you can perform retracking within these intervals. So you are basically for the retracking two information, the center line here, the interval, which is the width here of the binary mask for each interval. And then you can perform retracking for the sub-waveforms. Okay, so let's go to the result directly. Here you have the profile of the river obtained by retracking the cruise signal all along the transect using a sin-square model for the retracking. So a very simple one that can be very suited for specular waveform. Since we saw the return was mainly specular, we made this assumption for now. So this is very interesting. You see hydrological features here. So you may think, okay, is this mistakes or whatever, how to check. So we made basic checks to see if the jumps were actually real steps or dams. So yeah, actually it is. This is very interesting to see here. So you just with one transect here, actually you can see slope variability just for one condition, just one track. But this is still very interesting and kind of a change of paradigm for nadir altimetry, which used the notion and definition of just virtual station. Okay, so we still made a comparison. We had the chance to have an in-situ station here, which is from Chappie, and we computed the absolute bias here by selecting measures around the station and adjusting it from the slope correction, which is derived from ISA2. So this is very interesting results. We have not yet RMSE. We should produce more transect for time series, of course. So the idea is not only do the Creuse River, but also to try to retract as many bodies as possible. So we focused only on the three main rivers in this case. So we output the Angler and the Gartemp data also. So this is interesting. We start to see some mistake we can do with the methodology here. So maybe there is some wrong assignment, ID assignment, coming from the segmentation issue, or maybe coming from the database also, the Carthage database. Okay, so looking at the map we projected each water elevation here on the map, and you see here the real interest of trying to do that, revisiting the notion of virtual stations, since we are able to retract not only one body, one river, but as many as we want to do. It has to be assessed, but this is a very cool example, I think. Just with one track, we can retrieve all the long here, all the transect, the water elevation of three main rivers. We have a missing data here, area. Yeah, just because actually the signal is too weak and the process is not robust enough for now to be able to retrieve this part of the radiogram, but still this is improvement, I guess. So we need to investigate on how to do better. Maybe just final example, just with the FSR images, since I try to look at different good configuration here. You have already saw maybe the Tonins and Marmande example from the previous session. I just show here the time series of image here. So this is the time series of the FSR transect as an image. This is very interesting to see how the signal is breathing within the range the range domain. This is a combination of the drift of the tracks and of course the elevation of the different water bodies. But still this is very interesting. And we could do the same technique to retrieve the ground signal and here the step coming from the canal. And you see here that the signal is good enough up to 4, maybe 5 kilometers from the nadir. So this is kind of cool. You see sometimes that replicas appears and disappears. So we also have to mitigate those artifacts at some point and still working on it. And finally, another cool example of near the Gironde estuary of the same track. This is very cool to see that actually you can see many features also in this image. The rivers, the rivers, but not only. You can see also some structures here that should be interpreted as noise when looking at the individual waveform. And looking at the two-dimensional, you can actually sometimes see that it's sometimes irrigation or some crops. This is, I think, amazing looking at this data from nadir altimetry. I know this is not SWOT, but yeah, I believe this is still very cool.
3 minutes left.
Okay.
Okay.
Yeah. Jumping to the conclusion. So we try to perform a new method here, considering the two-dimensional radiogram actually. So to consider the waveform by stacking them as an image and to process them to extract a very smart binary mask to retract within it and to estimate water level for many different water bodies you might detect. Because it was done only for one track, but you want to do for more data, more cases, as I showed just before. And there is a lot of room of improvement, as I said, about the segmentation, registration, ID assignment, and the retracking itself, of course. Since we use only a single square, we can think about using more sophisticated model, a more physical approach. Like this is actually done for legs in the leg processing prototype. That is presented actually by Kness in a poster that you can find upstairs. So yeah, we want to work more on this to exploit more FFSR data, which appears to be very impressive in my opinion. And maybe also we have to revisit the definition of virtual station. So yeah, how much we have to define, how many kilometers between the transect. So yeah, I think Nadir altimetry, as we said this morning, is not dead at all, and we have to work on this. Sentinel-6 is providing amazing results, and using FFSR data, we should look into it more and more. So thank you very much for your attention.
Okay, any questions?
Hi, thank you for the very nice presentation. I have two questions about two limitations. First, is the off-track or off-nadir threshold 16 kilometers exactly, or is it a little bit wider? That's the first question. And second, does this method apply only to Sentinel-6 because of this fully focused SAR, or is it possible to some extent to do a similar study on the Sentinel-3 SAR? Because I'm working on the other river, on the Polish-German border. We have two great transects which are very parallel to the river, but it's Sentinel-3. So the question is if it's possible with this satellite. Thanks.
Okay, maybe the last one first. About Sentinel-3, you know that the closed burst mode is not very suited for applying fully focused SAR. So this is the biggest limitation doing this for Sentinel-3. And I mean, you still can do it, but you know that you should probably have the artifacts coming from these limitations. That's why we are focusing on Sentinel-6 actually. But why not? I mean, depends on the needs actually, and why not trying to look at it closely? I'm not sure about the threshold you were mentioning.
Yeah, because the footprint is of 16 kilometers size, yeah? And do you can make use of the full distance of it, or only like a couple of kilometers of nadir?
Actually, maybe you saw on the waveform are kind of cut by half because of the RMC mode. So this is everywhere now. And the good question is how far we can go using raw data. So maybe that's something to check. Yeah. And maybe this is also a recommendation to have raw data everywhere. That I don't know. This has to be checked. Yeah, of course. Yeah, we see sometimes that the signal just cut off nadir, and we still have some very good SNR. So I don't know. Yeah.
Thank you very much.
Thank you.
Okay, I think we can move to the next speaker, who is Jaming.
Okay, then I can start. Good afternoon, everyone. And today I'm going to share something about our recently task. It's about the river water level and discharge estimation from altimetry with free focus SAR technique. And my co-author is Luciana and Jürgen. And continue, yeah.
Jamil, can you speak closer to the microphone, please?
Okay, yeah.
Okay.
Okay, it's better. First, we introduced about the outline of the study area, and we focusing about these images, and we can see that first is about Chinese River, and I need to discuss something about the status of the gorges in China, because until now that there's a few gorges are available due to some policy, yeah. And also some river may just only have one or two gorges, such as the Brahmaputras in China's part. And some gorges maybe has lots of gorges, such as Yangtze River and the Yellow River. But to be honest, some of them maybe only its water levels or just maybe only discharge. So it's necessary that for us to choose in some other ways to to produce the data set of water surface elevation and discharge. And here that we mentioned about previous studies about John's papers, they show that Sentinel-3 in Chinese River has a little high accuracy, because the accuracy is from 0.12 meters to 3 meters. It's, to be honest, is very huge. So we want to understanding what kinds of problems in here. And our goal of the projects is about providing the data set for the water surface elevation discharge in Chinese River. And here's examples for Sentinel-6. We are going to choosing these several world stations to process. But going back to this today, and we are mainly focusing on these two parts. First, for an analysis here. And our processing chain is about free focus, is using omega kappa logarithms, and this is compiled by our self in home place. And here we want to thank for Ulrich spot. For our case, it's much quicker for processing the data. And for the free focus configurations, we choose in the processing rate is 560 Hertz because we want to get maybe around 15 meters to get 1 point along check, and 0 patterns equal to 2. And for the rechecking models for L2, we are going to use Samosa Plus, and we change a little for it for make it possible to suitable for the high processing rate. And for analysis is about the L1B signals, and L2 we about the gauges. We also take in the geophysical corrections from the L2 product, and from offset here. Okay, then let's begin about the first. We starting from the checking points. We can see that in here. Yes, this should be a very good example in here, and the checks is perpendicular with the rivers, and the signals it's very strong here, and we can see that the recheckings in this part is perfect. It's very good. But going back to the right place of these two things, we can see that it was trapped in some other place. After we understanding this part, because the signals coming from this part in the downstream of the visual station and the upstream of the visual station, the signals in some occasionally that the signals come in the same times, making this part very strong, and this should be the off nadirs. It's not the nadir signals very strong, so nearly all the rechecking points are trapped in here. And going back, see here, it's a similar situations. Actually, both of these two is because the weak signals in the nadir. So if we want to generate a product, we want to make a clean water surface elevation time series or discharge. So two options. One option is that we recheck in again. And another way is just throw away if not so many, just throw away, yeah. And here we want to considering one ways to distinguish this point being trapped. And go back to the main questions. It's shall we only remove those checking points being trapped? Because we don't want to lose other points. We just want to distinguish which points are belongs to the of nadirs. And the second question is, except for the high resolutions, can free focus providing more information could be useful for discharge? And seeing these images, and first ideas in here is that we want to consider in the different cycles in the same checks, because at least in many parts of the checks of the cycles, the rechecking points should be inside the nadir, and the signals itself should be very, very strong. So if we can consider in that combine different cycles together, then we can very easily got a reference point to distinguish. And in here, that is a very famous figure, yeah, Mona Lisa here. And to be honest, we see that the images registrations is already very, very good now, and we can very easy to compare to combine these two together and to find where is it. So going back here for the radiograms, the free focus of Sentinel-6 is already very good and very beautiful. And why not just taking these images as this radiogram as an images? Then we can also use in the same ways as we do in optical images. Then after we do this, because you know that the shift, there will be a shift in the checks in here, in some case in the left, in some case in the right, and the signals will be changed a little because of the check-in model. So after we using the image registration shift, and we can making all of this to stack and in the same level. After we having this one, it looks, because we see that maybe not so much clear, but we can see the signals of the strong scenes in here. That is already aligned in the same levels in here. That, but this is not from the nadir. The nadir is in here. Yeah, this one is something else from nearby. There's a small lakes, very, very small. Maybe not a lakes, is a ponder in here. And after we we have this one. This is another case. We can see this may be much more difficult because you see that there is two parts of nadirs in here. This is one part from the beginning, from this part. And for this part, it belongs to another part. But you see that in some radiograms, the signals coming from this part and this part, these two of nadirs is very strong because the weakness of the weak signals coming from nadir, and from our understanding that this is related to the low water. Yeah, because sometimes low waters, the signals coming from here is very, very weak. And after we have this, we can do the multiply for all the stack for all the stack radiogram because we has already inside the same levels. It's already aligned this all of it, and then we can got product waveforms here. These waveforms, obviously, that we can see that this is what we want actually. The radar, the signals in the nadir after we using a shape files in here to finding where is it. So this could be as a reference gate, and then we can use in this reference gate to compare with previous already aligned, because we have already recheckings using some more plus, so we have already got the rechecking points, rechecking positions in each radiograms. Then we compare with these two, finding which part is we don't want. And coming back here, we can see that it's very clear that some of nadirs is the recheckings is trapped in some of nadir part, such as this part. It was being trapped in this nadir, this of nadirs in this part, and for this one, it belongs to this one. Yeah. So. But yeah, anyway, that both of this one belongs to the of nadirs itself, but using these ways could be very easy to distinguish. So we just need to throw away these three things here, And we see that we do the validations here. We can, before removing the rechecking points here, that the accuracy is very high and is around 1 meters. And because we also want to keep this one. You see that after using the methods, some points are be thrown away, and we got a very good result in here. The correlation is 0.99, but the standard deviations may be a little higher. It's 0.23 because this is as I just said, that there's a few gauges available in China. So we only compare with gauges in here, so it's a little far away, maybe around long check is about 9 kilometers in here. So it should be had some slopes in there. And this is another areas in here that is the same situations, because you see that before remove the point, and we got a 1.66 meters accuracy. But after that, we can got a good result. Result is 0.25 meters. So this is what we want. We want a clean time series here. But we should be focusing that here in this point. I think that this should also be removed, but it's not. When we're going back to see why this is happening, is because of the signals in this part is too much weak. We're still trying to understand why this is happening, but the signals is too much weak, making the whole things, the whole radiograms cannot be very good to do the comparison. Yeah. So this cannot be removed, but but anyway, we keep this one. Yeah. Still, because we still have already got 25 centimeters. And then we compare with different gauges, and for in different radio stations, we're taking 8 radio stations from past 1 and past 12. The radio stations are located in different rivers, in Yangtze River, in Yellow River, and in Pearl River. And in here, we can see obviously that before removing the points, it's the medians of the standard deviation is 1.1 meters, and after that we got 25 centimeters, and the correlation is a little higher. Yeah, it's much higher, and we got 0.98 medians. And as we see that we want to remove this point, but we want to keep much more point, and we see the medians. We keep 92% points, so it's for our case is already enough for generating a time series. And for the second questions is that from the radiograms, is there any possible to get some other informations could be helpful for the discharge? And we see that these 2 good examples in here, yeah, it's again the same place in Yangtze River place, in the Yangtze River basin. And we can see the sigma 0. Yeah, the left one is sigma 0, and the right one is uncorrected height from Samosa Plus. And we can see very clear that the sigma 0s in this part is very, very strong. But so we are considering that is that possible to using the sigma 0s along check to get the informations of the cross section. Yeah, maybe just the coarse cross sections we cannot get accuracy. Yeah, and come here, we see this is several different sigma 0 along check, and the along check is latitude, and we can see the sigma 0s in this part is very, very, it go up very quick, and in here it's go down very quick. So we can use in these 2 ways to distinguish which one is the one that we want to use, and using the standard deviation or the sigma 0 difference in alternate beams and the sigma 0 difference in consecutive beams in here. So we can got 2 parameters, and using these 2 parameters, we can finding rectangles here. And then we can got the points, the nearby points in here. And we can assume this one belongs to the river bank. And comparison with together with the water surface elevation coming from the recheckings, and we can see that something here, that in this place is the Xinjiang River. in Yangtze Basin. In here, we can see that the point is in this place and is nearby, is very nearby in the river bank. And after we see that we transform the distance between the center line of in here, and we can got some kinds of cross-section lines in here. Yeah, but you know that this is just a coarse cross-section. I was not hoping that we can got some such as the river width in here, because I think the accuracy is still not enough, but we can got shapes. We can assume that this in this place is at least is a rectangle shapes of the cross-sections in here. And going back to next one, we can see that is also the same situations is nearby. Yeah, although it's sometimes there will be some problems, but it doesn't matter. We just want a coarse shapes. We want to find it belongs to which part of the cross-section. We see that this one should be a near trapezoid shapes in here. So after we have these coarse cross-sections in here, we can got what? First, we use the many equations here for the first one. This one is the one that we assume is rectangle cross-sections. So from many to from many to here, that is obviously that we can calibrate. Yeah, we can just use a little discharge and water discharge from gauges to calibrate some parameters. And after that, we can got the two figures. The two figures is about, the first one is about I don't remove any point from water surface elevation. The second one is using the methods from us to remove some points. And we can see that discharge, the accuracy is much better now. And although the Nash-Sat efficiency is 0.76, and the second one is now we got 0.88. So is at least is a very good performance improvement. And then we also considering another way that is maybe a simple equations, just like it from this paper here. And discharge can be using this formula, simple formulas to estimate. And because we are using rectangle cross sections here, so we can just make in just like rating curves here. And then we can also get similar result. It's again that 0.87 here. And coming back another area, this may be different, yeah, because it's not the rectangles now, it's trapezoid cross sections here. Because we're using many again in here that we can see that discharge, if we don't remove any points, just taking the time series coming from the altimetries, and we can see that the accuracy is still very low, and we got around 0.34, and it's underestimate of the discharge of this part, but after we remove the point, we can got 0.85 in here, and we see that it's very good in the high flow, yeah, in the high flow discharge in here. And to be honest, we see that these two parts, this part and this part, unfortunately, we don't have the gauges for 2023, so we cannot validate in this part, but we can see from here that because the discharge in 2023, July, is high, and also in 2021, near July is also very high, so we can assume that at least this should be reasonable for our case in here.
2 minutes left.
And in here that we see the Xinjiang rivers again is about the simple equations in here, and so it's similar way that before removing the point and after remove the point, the accuracy get very high, yeah. And this is what we are considering, that why some maybe previous some result of previous in Chinese river, maybe the accuracy are not so nice, because it's very hard to remove some points along the time series. You cannot generate a very clean time series here. So maybe sometimes the validations will be a little high. And now it's about the conclusions. The first one is about the imagery registrations could be used to distinguish those cycles. Recheckers being trapped on the off nadirs. The second one is the standard deviation of the surface elevations coming from between the altimetries and the gauges can have a decrease in numbers from 1 meters to 0.25 meters. And we also considering the sigma zeros along check. And to be honest, it's hopeful that considering is for the perpendicular when the river is perpendicular with the checks, and we can got a course at least is shapes of the cross sections. And finally, one is about discharge estimation is possible only using fully focus, as we just saying that we don't use the river widths coming from maybe optical images in here. Finally, it's about taking home message that yeah, just something. Yeah, the use of imaging processing technique applied to the radiograms looks promising. Yeah, and this is all I want to share. Thank you. Thank you for your time.
Thanks for the nice presentation. Any questions?
Thanks for a very nice talk. I have a question, why you need to apply an image processing technique to align the radiograms? In principle, you have the latitude, and in beam direction, you have the tracker. So everything is aligned. Why you need to do the feature matching?
Because yeah, I understand. Because we want to get an automatically ways to finding the points itself, as we see that also in the last presentation that the nadir's part, the signals will be shift not only in along check, also in crossing check. It will be a little shift, maybe not too much, but if we want to just find a reference gate, then we need to do this to at least in the same levels, because it's a shift. The signals will be different if we check in with the radiograms itself. Yeah.
Okay.
Yeah. Thanks.
Thanks for the nice presentation. When you say you can estimate discharge with only fully focused SAR, as I understand, you still need in situ discharge, right, to calibrate your Manning's equation? So that's my first question. And then the second one is it the same discharge that you then used to estimate discharge that you validate against?
No. I would just, maybe I don't explain too much. I just calibrate first just in 1 year and then validation again. Yeah.
And the validation only the other?
Yeah, another year. Yeah.
But you still need in situ discharge?
Yes, it's still need, at least because we need to calibrate the N, yeah, the Manning efficient. Yeah.
Thank you.
Yeah, thank you.
Okay, we can move to our next speaker, who is Ferran Guibert from ESA-ESRIN.
Then we need to just
wait.
Yeah, you can check.
Good afternoon. My name is Ferran Gibert from ESA-ESRIN, and I will present you the results of a study that we did using fully focused SAR and Sentinel-6 data over inland targets. These are the members of the team that are involved with hydrology, let's say, in our company. Amongst all them, I would like to highlight Robert Molina, which was a student that was with us and was doing most of the processing that I will be presenting now. So the overview of this presentation is quite classic. So we will introduce the processor, the algorithms, the targets, the collections. Then we will explain how we are analyzing them, showing results, and then moving quickly to conclusions. So all this work is part of the Valeria project, which stands by validation algorithms levels 1A and 2 in every river area, which was proposed as an activity for the Sentinel-6 team validation team to demonstrate the capabilities of the processor. So here we want to see how far we can go with the processor, not with sensors maybe, over inland waters. Two topics were addressed in these projects. The first of them is the water surface height, which is the one that we are going to analyze now and to present now. But there were also efforts on the water extent measurement capabilities with Sentinel-6, so with radar altimetry. And there is a poster on this topic by Adriaco Mezolive, and that you can check well, if you have not yet done that. So also part of this work was developed within the Hydrocoastal project as a case study. So why fully focused SAR with Sentinel-6 over inland targets? So first, because fully focused SAR provides enhanced along track resolution, in theory down to 0 to half meter along track resolution, which is much more with respect to delayed Doppler. As you will see, of course, this has a logic benefit. That means we have more points. This number of more independent points is not useful in inland waters because we have more sampling, but because we can also better select the good ones. So as you will see, we will put some effort not only on the retracking, but on the waveform selection to get to our best measurements. Also, as it has already been said in this session, Sentinel-6 is the only SAR radar altimeter to operate with interleaved mode. That means where there is a continuous transmission reception chain of pulses, so there is a very reduced impact of along track replicas. I mean very reduced, not zero, because it's not perfectly continuous. There are some calibration pulses, that means some calibration gaps, but are small, and the replicas are not do not have a strong impact to our measurements here. So the area of the study of this project is the Ebre River Basin in the Iberian Peninsula. That was actually the initial scope of the project. Then we enhanced. We included more. We wanted to include more targets, and we took also. So the Ebre River Basin is here, close to the Pyrenees. But then we included some more targets that we found them interesting. That we were very careful with when selecting the in situ data providers, because that was a key part in the validation. So the focus was set on a collection of small to medium-sized reservoirs. I will present them in the next slide. And what we did is to download 1 year of data, so from August 21 to August 22, and analyze as a block. So those are the 6 reservoirs, ESA, Toys, Garibaldi, Fernandina, Puente Nuevo, and Mequinensa. But actually, we have 8 measurements, because for the case of Mequinensa, we have kind of 3 passes, and which were also useful to test how consistent was the algorithm over the same target. So we have one for this case where the pass crosses twice the reservoir. We can actually consider these as 2 independent measurements with the same in situ value. So the methodology that you can see it here. So we start with the L1A files. We apply a fully focused SAR algorithm with the L1B product that we obtained from that. We need to correct for geophysical corrections. Then we go to the algorithm to retrieve the water surface height. And after that, we compare with in situ data and we analyze the results. So this is a typical radiogram over a reservoir. So in this case, this is ESA, Aragon, and we cross it. And as you see, the typical shapes that we observe after that in nadir altimetry is that the target is kind of folded because of the fact that we cannot distinguish on both sides of from the scatters at both sides of the ground track. Regarding the processor and the configuration used, we use the fully focused SAR processor that we have in DARSAT, which is a Sentinel-6 GPP. It's based on the back projection algorithm, and it has already been validated with transponders and corner reflectors. So we are quite confident on the processor. And in terms of configuration, we take a 3-second integration time. We select a single look spacing of almost half a meter, though we work with multi-look spacing. We kind of average in groups with values ranging from 5 to 10 meters. first, what we do after we get the radiograms is to apply a retracker. Since our idea was that the complexity and the errors were coming not for the retracker itself, because the signals are really peaky, are really kind of specular. We were and we were more worried about the post-processing. We said, okay, let's go for a very simple, let's say, retracker. So we just took we just do a Gaussian fit over the waveform maximum. That's it in terms of retracking. We did some analysis on which was the minimum number of points, and at the end, the best cases resulted in just selecting the points with highest power and just fit and take the maximum. Then the efforts, as you will see, is in the selection. So as already mentioned, I think it was on Monday by François Boy, we have so many points that it's worth treating them as a collection, as a population, so within the same target, and then we can study, we can observe which are the features that look like of nadir scatters, and we can apply some kind of algorithms and filters to select and to define what is our final measurement. So first, regarding of nadir scatters removal, as you already see, so this is here we have the surface of the target in this case, and we can see very bright scatters of nadir. So, and in this case, they actually higher than the surface. So we cannot just take the first echo that comes up. So we in this case we should take the one below. No? So we need to take into account this, and we need to remove. We are not actually selecting these ones here, we're actually discarding. So since we have this enhanced long track resolution, we have so many points that we can say, okay, let's just discard, because we assume that the waveforms affected by a strong of nadir scatters may have the measurement distorted. So basically, we can afford removing them, as you can see here. Next to that, peakness. We also observed that some waveforms were not kind of symmetric in terms of peakness, or were not just dominated by a strong scatters coming from nadir. And we also filtered the ones with high peakness with respect to the ones that were not that one. So we also removed some waveforms using this criteria. And apart from that, the mask, so which is the length, the transect length that we need to use. Just recalling that those are reservoirs, so they are really go up and down during the season. This is just for the case of one of them. I think it's ESA. So as you see, the available sizes depend on the season. So as it goes down, so we have less points, and that's it. So we really, in this case, we really did a kind of an adaptive approach to that. Just to take as much good points as possible depending on the pass. So there is no fixed mask here. We are just adapting it. Okay, so before going to the validation, we can already see how stable we are with a series of measurements, that are left after such a strong waveform filtering. And what we can see is that the intra-target measurement stability, that it's just the standard deviation of all the measurements within one single pass, but in this case, the average of all single passes classified per each target. So we are already at values close to 4 centimeters in average. Then we're moving now to the validation with in situ data. We take the data from the Confederación Hidrográfica del Ebro for the basin case and for similar entities for the non-Ebro basin case. And well, this is just the matching points, and we are going into more detail on now because we are interested on the error, on the differences of them. So, but a first test that we can see is that we didn't see any kind of strength dependence as a function of the height. So that was kind of maybe the first sanity check to do. So those are the functions left for each target after subtracting by the in situ values. And then moving now to the analysis in terms of bias, we observe very low bias, especially for the Ebra basin case. That is the group until here, let's say. That maybe they are more accurate in terms of correcting for the geoids or when they provide the data, they may be really adjusting the values, and because the ones that are not on that basin, the numbers are really go to a different level. We think we can attribute these differences to the data providers. A first nice check that we can do here is that we see similar bias in the both passes at the same day over the same target, which actually says, okay, the consistency is dominated by the the issue, the bias may be dominated more than to geoid point of view, more than the coastal issues or of native scatters. So in terms of standard deviation, these are the standard deviation of the residual errors, taking into account 1 year of data for each over each target, and the values are already close to 4 centimeters, which is more or less the numbers that have been presented these days. So it's consistent from this point of view, and there are no major differences between the different targets. Even they are quite different in size. So for instance, in Itoiz, that case here, this is a target that is 130 meters. That's a very small one, the crossing of the satellite over the target, while in other cases we get up to 2 kilometers. So more or less, it's stable, the measurement that we do over these targets. In addition to that, we always try to go as down as possible in standard deviation, but how far can we go, or how we can expect that can be achieved? Because I think that the threshold in SWOT was 10 centimeters, for instance, but actually we should expect a limitation at more or less 1 centimeter, which is the uncertainty in the estimation of the wet tropospheric delay. So we expect that at some point we will be limited by this. So still we have we can expect some margin of improvement maybe in our algorithms to get these values lower. So this 1 centimeter uncertainty is actually what we observed when we do a similar analysis, but over point targets such as corner reflectors or transponders. So where the coordinates are really known, and we are just repeating the same during 1 year, 2 years, and we are actually around 1 centimeter in standard deviation. As part of the coastal project, we are comparing these results for the Ebra basin only case with what is normally obtained with delayed Doppler products. And as we see, the improvement is strong. So in terms of standard deviation, for instance, we are now to the close to these 4 or 5 centimeters, while we used to have values 1 order of magnitude higher than that. So in terms of improvement, it's strong what we are achieving as average values here with fully focused R. We can actually try to apply the method developed here in fully focused R to L1B delayed Doppler data in order to be more fair in this analysis, and this is actually shown here. So when we apply the same retracker and filtering to delayed Doppler data, this can be done in the big targets such as this ESA-ESRIN, which is almost 2 kilometers. So we have already many points on the delayed Doppler side. Then there is also an improvement in terms of retracking. So then it's no longer this 10, 20, 30 centimeters standard deviation, but it's already 6 to 7. So at the end, the benefit may be not related. It's related more to the number of points available. And at the end, the application point maybe is the really small targets where you just have few points and you have to live with that in order to extract one measurement. That was this is a short comparison with previous studies as of this summer, maybe, because now that should be enhanced. I was happy to see that there are other efforts on that. There is also a poster on one of these targets already there, which is not from us. So this list and this intercomparison with other people, other groups, or other analyses, now it's likely to be growing this year. In that case, we were just comparing comparing here with a paper on 3-4 years ago with Sentinel-3, where the standard deviations were not better than 15. So we are already factor 3 at least compared to that. And also there is a paper over the different kind of targets in the Netherlands by Marcel Klein-Herembring, where there were some values were already low. That was cryosat, sorry. This is fully focused over cryosat, and in some cases, in some small targets, very good improvements could be already be appreciated. Still, a cryosat, as you know, is not an interlift. So part of the differences between this study and what we can get now with Sentinel-6 may be attributed, is attributed to this, to the interlift mode, to the different operation in terms of sequence of pulses. So now, just already to in the Outlook slide, we can say that the fully focused SAR processor has been tested and results have been successful over a selection of reservoirs. Size is 100.1 kilometers to 2 kilometers. This is the size considered, and the residual uncertainty, the average, which is more or less the same values, plus minus 1 centimeter, equals of 5 centimeters in the error series. That means that after subtracting the bias, let's say, and which is good, much better than what we used to get. And basically, the message is that the fully focused SAR enhanced along track resolution allows to remove off-nadir scatters without losing a significant number of good independent measurements. That's why to us, it has been more worth spending the effort on filtering rather than on getting moving to very complex retracking methods. So as a recommendation, we can say that please keep or ensure that the interlift mode over inland areas in future missions is used in order to get measurements as clean as possible over small targets, which are limited, which are normally very affected by coastal, near coast features. And that's it. Thank you very much for your attention.
Thanks a lot for the interesting talk. Any questions?
Considering this filtering, so you particularly filter looking at the waveform, which is the percentage of point that you eliminate?
That I think that depends on the target and on the size of the target. I don't have the values here, but I have maybe the plot. So you see, we still get a higher amount. I mean, I would say that we keep more than half. I don't have the numbers. That's a good parameter to track, actually. Since if the target is 1 kilometer, you have more than 1,000 points, so you really have lots of independent measurements.
Okay.
I have a small question. Maybe I see that your result is for free focus is higher than L2 for ocean and OCLG, because we know that the L2 product is 20 Hertz. And for free focus, maybe in here is a little high, it's a very high position rate here. So what's your opinion? Is the difference is related to the position rate itself, or is related to the retrackings? Because we know that actually for Sentinel-6, the unfocus can also get 140 Hertz, but just we don't have, we need to generate ourselves.
Here I think the message is that when you have more independent measurements, the more independent measurements you make, the higher are the chances to remove the off-nadir scatters. That, I mean, over the coast, over the reservoirs, there are urban areas, there are swimming pools, there are many things. If you improve the number, the sampling, then you can easily remove these. With delay Doppler, you have few points and you're getting all these off-nadir scatters with you, so it's difficult to get rid. So I would say that most of the difference is because of that. Because if you use delay Doppler over targets that are big enough, then you see that these values of 10, 20, 50 centimeters of standard deviation, they can really go down. I mean, that maybe over big targets, delay Doppler is already good, for this kind of measurements, but over small targets, you really need to start cleaning and classifying a little bit.
Thank you. Yeah. Did anyone have a question? If not, maybe we need to move to the next one speaker. We welcome to Shahin for his presentations about the fault-tolerant approach to regenerate L1B star altimetry waveforms for enhancing L2 recheckers performance.
Yeah, thanks for the introduction. I'm not Shahin, I'm Mohammed Turian. Shahin is a PhD student at our institute who could not make this travel because he was waiting for his visa for a year to come to work on a DFG project. But while warming up for the DFG project he's going to work, he managed to do this nice job, which I present. The problem statement is quite known to many of us. So altimetry, due to known problems of wide antenna pattern and so to say, reflections from the neighboring topography problems in general, and also the known problem of reflected power in antenna's main lobe and so on. So you always get some noisy waveforms, which you would not like to have in principle. This is one just example over the Itaparica reservoir. So 14 measurements from down to top. So, and the corresponding level 2 waveforms of each. And if you have such a waveform in principle, so if you have such a waveform, I mean, these two are probably okay to some sense. But if you have such a waveform and you want to start analyzing or extracting water level out of it, then you always have problem. I mean, the water level that you extract from such a waveform would be erroneous. So if you want to categorize these waveforms, then I would say, yeah, probably only 2 out of these whole set of 14 level 2 waveforms would be okay. The rest would be noisy, or if you want to actually use for the calculation of water level, then you have to have a very clever retracking algorithm. So that's a problem I think many of us are dealing with. And of course, if you blindly apply any retracking algorithm on these noisy waveforms, but you probably get such a time series for water level, which which we all have seen in our life, and we typically start to remove outliers and deal only with those that are meaningful for water level measurement. So here our approach was, so let's do something with this level 2 waveform. Let's actually go back to the SAR processing, and then let's see if we can improve them. Let's see if we can actually correct them. So that's what we did. So that means in our approach, first of all, so we have a 2-step. So first of all, we want to detect all noisy waveforms, and that detection involves, so to say, extracting some features from the waveform itself and extracting some features from instrumental information, based of which we could identify if one waveform is noisy or not. And then once we have identified the noisy waveform, then we want to go back to the level 1A, perform the level 1B processing, and then while we are actually getting the beam looks, then we want to exclude the beams, the beam look that are actually erroneous. That's what we did. So, and then in the end, you get a level 2 waveform, then we do the retracking and do the calculation of water level. So our case studies are these 5 lakes, quite distributed with different size even, and the data are both Sentinel-3A and Sentinel-3B. So for Lake Tahoe, for instance, we have used Sentinel-3B, and for Itaparica, Sentinel-3A. So our data, the data is level 1A, and of course the level 2. So our steps for the detecting the noisy waveform is to extract some features. So these are the features that we extract at the moment from the satellite-related features. So the tracker range itself, the AGC and the calibration values, and also the satellite orientation. And then we extract also some features from the shape of the waveform itself. So like kurtosis and the skewness of the waveform, the number of peaks, the power of the maximum peak, the thermal noise, and where the maximum peak is located, and where the first peak is located. So these are the features. So we feed into kind of unsupervised machine learning, where it in principle works on the fact that what we expect from these features, how a normal clean waveform should look like. And by doing that, then we can actually label label waveforms as clean or noisy. So we have performed that kind of detection, anomalous detection. So that's the result over these 5 case studies. Of course, there's a labeling involved. That's why we have these true positive, false positive, and false negative numbers. So for instance, we knew that the number of noisy waveforms for a case of Itaparica was 110. So we could detect with our methodology 102 of them. So in that respect, we are kind of confident about the so to say, success of this detection procedure. So assume now we have an algorithm which automatically identifies all noisy waveform. Now it's time to actually go back to the processing. So our approach is actually, first of all, generate a reference waveform, because we know where we are, where that noisy waveform is generated. So you generate a reference waveform, either depending whether it's you expect the specular reflection, you can also consider sync too, or you can use Samosa. So that's we have used interchangeably. So you generate a reference waveform, and then you start to actually, and then we actually experimented with both unfocused SAR and fully focused SAR, so to the both processing chain. And then, of course, you get the beam looks, and then we started to correlate this reference waveform with the beam look, with each individual beam look. So we extracted correlation and the lag, and based on how the reference waveform is correlated with each single beam look, then we decide if that is a noisy beam look or not. So our threshold was 0.6 for a correlation, and the lag of 2 bin was actually what we decided for this work. And then when we have that, then the residual is something also that we calculate the residual between the reference waveform and the beam look. And then that residual, so depending on how deviates from the reference waveform, that would be used as the weight, which we would use later on when we want to actually do the beam stacking. Yeah, so we exclude all the anomalous beam looks, and then basically compute the waveform using weighted beam look. And this weight, as I said, comes from the residual between the reference. So that means the more closer to the reference, then gets more weight, and then yeah. So that's with that chain, then we can. So again, is represented here. So basically, we get the level 2. We do the anomaly detection. If it's noisy, then we go to a regenerating waveform, and yeah, with the reference, and then exclude them, and then we go back to the anomaly detection. So we do it, we give a second chance to our anomaly detection algorithm to see if it's now passes the detection, and then and then finally we do the retracking and calculate the water height. Yeah, I jumped to the time series result. So here is only demonstrated for Itaparica, I suppose. Yeah. So and left, you see the water surface height retract on the level 2 waveform by Semosa Plus and the level 2 by OCOG. So that means all the procedure is performed. Now we are at the level 2. So in red, you see in situ. In blue, you see the so to say, the original FFSR waveform. And the black is actually the enhanced one. So that means what the black one is the one that comes from out, so from our processing chain. So if you compare the blue statistic with the black statistic, you see the improvement. So we from the RMSE of 0.8, we reduced down to 0.5, and we improved the NSE and also the correlation. And the same story. Also, I mean, of course, we know that at level 2, depending on the retracker you choose, the final result would be different. So in the OCOG scenario, we see that, for instance, the classical FFSR with OCOG is not as good as the Semosa Plus, but still we could actually get the improved results. So all in all, in the general statistic, that's a bit boring to follow this table, but please be patient with me so that you could compare all these numbers. So the top row, or actually for each cases, we have now the level 2 retracker, so one Semosa Plus and one OCOG. And then everywhere you get the original waveform versus the enhanced waveform. And then here you see the statistics. And ultimately, you see the improvement in percent and in RMSE. So for instance, for Itaparica, we are improving the water level time series by 40%. And that same holds for Lake Tahoe and for Lake Boca. Not as much as Itaparica. But in general, if you follow all these numbers, it means the algorithm works. And final, that I come to the conclusion. So basically, the conclusion is there are noisy waveforms. You can do something with that. You don't have to throw that measurement out. So that's probably the main message of this presentation. It might be a bit costly to run the entire processing for every individual waveform, but for many cases with small lakes, small rivers, that would worth to do that. Otherwise, you lose that information. So in that respect, that's the main message. So that's so I wouldn't repeat what I said in last 5 minutes. With that, I would like to thank you for your attention and open the room for questions.
Thank you for the nice presentation. Is there anyone have a question?
Thanks for the presentation. I have a question actually. So if you had to choose between Semosa Plus and sync function, when you have a noisy waveform, would you do your choice based on size of lakes, for example?
Yeah, exactly. So based on for instance, for Itaparica, basically because of the size and because of the topography around, we expected that should be like sync 2. But when we go to bigger lakes, then Semosa would be a better choice.
Okay, but I suppose that you don't have yet a kind of a threshold.
No, that was not. Yeah, that was not so automatic to decide. Yeah.
Okay, thank you.
Just in addition to this, in a project we had named FFSR for coastal, we used the FFSR processor and used the OCOG and another tracker named NWAP, developed by DTU which looks for persistent peaks in consecutive waveforms. And it performed very well, better than sinks for estuaries and canals we were studying. So probably you want to have a look at these outputs because all the data sets are available. This could be also an option as it is empirical and very fast. And in other papers for SAR, the results were quite close to Samosa Plus. Okay, could be another addition.
Can I? Yeah, Mohammed, very good. Can you switch back because there were lots of numbers, but I would like to see some of those numbers.
Yeah.
So yeah, as lots of people are showing, the RMSE that you can get with the various retrackers, but Sentinel-6 in particular, it looks all very, very nice on around 10 or better. But just also relating to the question that was just, don't forget that Samosa Plus was developed for oceans, which of course works for a big lake as well, because a big lake looks like a sea.
It's not entirely correct, you know that, because Samosa 2 was developed for the ocean. Samosa Plus was developed for the coastal and inland water, most popular surfaces.
Yes, but at least for bodies, for significant bodies where you have a significant amount of water. So indeed, small bodies, small bodies, you should not use Samosa because that would violate the original idea behind Samosa Plus. It started with an ocean retracker and then was adapted for
calmer environments, calmer waters, but footprint full of water.
Yes, a footprint full of water. Let's say it like that. It was meant for a footprint full of water. And OCOG would be indeed more appropriate for very small lakes and rivers. But you've already pointed it out, and Sync Squared sort of falls in the middle. But I would all invite you to exercise those retrackers and to learn about it, share your results and your findings, because obviously each of them have their advantages.
Yes, in hydrocoastal, we succeeded in selecting the NWAP tracker I was citing before for the estuaries and inland water. This could be also another alternative to compare to OCOG. And I think this was made also in the project, not Karina? And just a question about the posting rates you use for fully focused SAR. Which posting rate did you select for this?
That's, if I'm not mistaken, I have to check with Shine, but I think it's 40 Hertz.
40 Hertz?
Yeah.
Fully focused SAR, 40 Hertz?
Yeah.
Okay. Any other questions?
Okay. Then we move to the next speaker. We welcome Malik about his presentation, Logarithm for Radar Altimetry Rechecking on Specular Waveforms, a new rechecking methods based on physical model for nadir low-resolution model altimetry over inland waters.
Okay, hello everyone. I'm Malik Boussarak from Hydromatters. And today I will present you some of the work we are doing to develop a method based on physical tracker for altimetry over inland water. So let's start with a brief reminder of some of the challenges we face for inland altimetry. For example, a frequent challenge is that the radar altimeter might keep focus on the surrounding topography. So here you have a transect analysis under the Sentinel-6 path over the Arkansas River. And in some cases, in closed loop operating mode, the tracker can focus on the surrounding hills and lots of signal coming from the river. Also, as we already as we've seen in the previous presentation, the surrounding water bodies also interfere in the radar echoes. And that can lead to the presence of multi-peaks in the waveforms. So in the case of the Garonne, here we have also the canal, pond in green, wetlands around, and human constructions. We also have to take into account the fact that the river is not always crossed at the same point by the satellite because of the satellite drift. If the virtual station was placed effectively under the theoretical track here, because of the satellite drift, which is moving over and over the theoretical track represented in the continuous line, this could lead to different measurement position between the two different observation dates. So for example, sometimes here and sometimes here. And also, the water body itself position can move because of unexpected event, a really strong event like the last flood in Pakistan. So the scientific community has provided some of the solution for some of this problem. For example, the use of open loop tracking command here, or also star processing, but there are still some problems remaining. Hopefully, the most recent missions are an excellent opportunity to better understand the physical phenomenon involved in the signal acquisition of inland water. So, for example, Sentinel-6 is providing a unique dataset with both low resolution and SAR mode. It is the same idea for SWOT, where the one-day repeater orbit can bring a lot of new information. These recent missions should help us to better understand the physics of measurement and eventually lead to new process, to optimize the process, to use the 20-year plus of LRM altimetry over inland water. So like François Boy said, low resolution mode is not dead, but maybe also he said that nadir altimetry is not dead, but maybe also the case for low resolution mode. Something important to know is that for open ocean, the Brown model describes perfectly the backscattered waveforms. We can identify here for the JSON-free waveform all the components of a theoretical waveform shape with a leading edge, the corresponding epoch position, and the trailing edge. But unfortunately, there is still not clear equivalent model for inland water. Instead, here you can see a typical echo that we have seen often today over inland water, so for a river seen by Sentinel-3. And on the right, you can also see the sync function, so which can look pretty similar to the previous echo. So if we have a sync echo, it's because the satellite path and river intersection act as a punctual reflector, and the backtrack signal is equivalent to a Dirac. Moreover, with this model, we can also take into account clipped echoes. So here is an example of JSON-free waveform, typical waveform for over river. And we frequently, this type of clipped echoes are frequently seen with Poseidon altimeter from the JSON family. So it is also the case with SWOT Nadir altimeter. And also, as Nicolas said yesterday, with Sentinel-6. So we can take into account the missing part here of the theoretical signal. And instead, OCOG cannot properly process this type of signal. So if it cannot find the epoch, so in extreme case like this one with 8 clipped points, this can lead to a mistake in the retract epoch by OCOG, and the difference between ours and the OCOG one greater than 2.5 meters. So we did classification of the waveform shapes, and we divide it into 5 groups. So the first one in the green box are the picky echoes. So they are with a shape really similar to the sync squared model. We have also a group of picky echoes, but including a trailing edge. Another part includes multi-peaks, so when we are the same peaks shape than the first group, but they are present several times in the same waveform. And then we have also sometimes echoes over inland water. So we perform an analysis over a lot of different basins, so for example, Amazon, Mississippi, and so on. And for different missions, JSON-3 mainly, Sentinel-3E, Sentinel-3B. So here is a zoom for JSON-free free data and the waveform over rivers. And the most important point is that at least 75% of the echoes are suitable for processing with sync retracker. So we have peak echo close to sync square signal in 75% of the time. So we implemented this model in an automatic processing chain to be able to create water level time series everywhere. So it needs as an input data the river center line. So for example, provided by Sword for the case of Garonne here, and also the position of the virtual station, and of course the waveforms in the product, contained in the product. For this case, specific case, it's a case for Sentinel-3 over Garonne. It can be a complicated one because here in the white line you have the retract epoch by OCOG. So it's a little bit messy with erratic epoch. And we will briefly describe our process for this this waveform and this virtual station. So the idea is to analyze every successive waveform close to the river and looking for peaks among them. So when we identify peaks, we try to fit the model, and we are doing this for every peaks we found, not only the first one or the big one. Here is a zoom on the last one. So we can find in green dots the waveform contained as contained in the product, and the blue line are the best fitted sync echoes. The orange dots only represent the same echoes, same theoretical sync echoes, but with the same sampling rate than the product. So finally, if we do it for every available cycles, we can find the corresponding supposed position of the water elevation and create complete time series, allowing also the case of multiple peak and so multiple water level value. So it is for these two, they are corresponding to the two peaks we found here. So also we can handle clip signal as I showed before. So we wanted to compare the global performances with Hydroweb, which is also providing automatic process over with a global coverage. So we set comparison sites when we both produce time series close to in-situ gauges. So for example, here we are over the Mississippi Basin. So we use the USGS gauge, and we compare when we have that in-situ data closer than 10 kilometers of the virtual station. Something important to note is that we are not a lot of JSON-free time series in Hydroweb, so we only focus on the comparison on Sentinel-3E and Sentinel-3B. So we look, as a comparison variable, we only look for and count the number of good time series. So a good time series is defined by a correlation index bigger than 0.9 with in-situ data, and also NBS RMSE lower than 30 centimeters. So with these two criteria, we can find that approximately 25% of the time series shows very good results for these basins, and on the comparison points with Hydroweb. From the Hydroweb side, they also have the same time series, so they have good performances, the same performances with the same amount of very good time series than our process. But we also wanted to check our performances over every available virtual station of the entire basin, and so also on the time series that are not available on Hydroweb. So we can bring 40 more virtual stations which have a really good result like this one. But there is a little bit decreasing of the rate that we had the success rate that we had before. We did the same for Amazon Basin using ANA GOGIS data. With at the global scale of the entire basin also something close to 20% of good results, but really good results. And we also did it for a smaller basin like the Garonne one with 20% of good results again. But maybe something, the most interesting thing happens when we checked the global performances of the JSON3 on the whole basin again. So at the scale of the basin, we found the same rate, success rate than with JSON3 than we had for the SAR data. So it means that LLM altimeter and with this process that take into account the possibility of multiple peaks and clipping, that can reach some really good performance over a narrow river. So to sum up a little bit this process, so we were able to put in place a new fully automatic retaking chain with a global coverage that involved the use of a potential physical model for specular echo, and which also able to process clip signal. Here you have a clip signal for SWOT Nadir data and the fitted equivalent signal. This method provides really good 20% of really good time series, so it's on par with the current performance available on HydroWeb. And that process works for Sentinel-3 mission, but also for the entire JSON altimeter family. So it's a good tool to process extended time series with the same methodology. In the case, for example, of climatic studies. So here is a combined time series using the Oro tracker of a river in Guyana, French Guyana. And we now wanted to look at the top exposé hidden and JSON6 data. So this will lead to the redaction of a scientific paper the next month. And I want to conclude with a big thanks to Dodi Blumstein. We did a lot for this project at the beginning. So thank you for your attention. And I can answer now every question that we could have.
Any questions?
Thank you for the presentation. I'm wondering how many waveforms, clipped waveforms, you are able to recover? Every, or there is some limits for this?
We can take any type of waveform that are clipped, but you want to know some rate of the percentage of clipped waveform.
Any, even if it is clipped at half of
so
potential.
Here you have 4 points. I showed earlier a case with 8 points, but sometimes there are more than 10 points also clipped, and the quality of fit is good.
Sync is capable to recover all.
Yeah.
Okay. Yeah.
So it could be hard only if the signal is close to the extreme waveform gates. So from the beginning of the end, because we only have one part of the signal, and we could not know how many points are really involved in the clipped effect.
Okay, thank you.
Other questions? Okay, thank you. I think we can move to the discussion of the seed questions. Okay, so together with Jiaming, we prepared a few seed questions. I have to admit many of the presentations already covered and also suggest how we should behave in this in relation to the questions. So there are quite a few, 2 slides. I will just have you having a look at this. Point A is about the exploitation of artificial intelligence in the interpretation of A1B and A1BS data for SA. So the idea is, can we exploit artificial intelligence to understand the waveforms, understand the stack, clean the stack, and then later have a better, a more successful tracker recovering more points for inland water scenarios. And would this also be useful for the ground segment in the sense that at the ground segment we process the data from level 0 to level 2, so we could inject at that point the data information into neural networks. And so would you advise in the future to have ground segment systems take into account these possibilities of using artificial intelligence to maybe process the data and also introduce new flags, new quality flags to filter the data at a later stage. Then the point B and C are about the connection of SAR altimetry, fully focused SAR altimetry, but also LRM altimetry to SWOT mission. So in which way SWOT can help us and in which way we can as a researcher of Sentinel-3, Cryosat-2, and Sentinel-6 data, support the improvement of SWOT data by allowing a researcher of SWOT data to overcome limitations and so supporting them in this sense. Then there were a few talks about the exploitation of drones and micro river gauge station data. So how we can improve these systems. We recently ended, as I said before, the FFSAR for Coastal project that used drones and micro river gauge station data very successfully. And so we, as ESA, we are looking forward to further use this data and also to maybe stimulate the production of improved systems. Regarding the point 2, this is about the standard or thematic inland water land products like the Cryotempo, the Sentinel-3 land products, but also the Sentinel-6 inland water products in SAR mode, so the official baselines, let's say, which are, we know, all very good, but maybe could be further improved. So this point is about how we can improve the trackers, the geophysical corrections, auxiliary field, and maybe if we want to place a recommendation to improve the posting rate from 20 years to 8 years to allow the investigation on narrow rivers in case of SAR. And this is the first slide. For the second one, this is about the fully focused SAR processing. And especially as this is, I can directly relate to the presentation you made in this session. So we have seen at least 4 talks in which fully focused SAR was used. And I noted that the processing options were very different in terms of posting rate, for instance. So in case in the future we would like having a thematic product based on fully focused SAR for Sentinel-6, just an hypothesis. We need to fix at that point a posting rate, no? Because we can, I know, I can understand it cannot be perfectly shaped for each inland water body, but if we have to select a value, do we need at this point an investigation to select the correct posting rate, the best trackers in this sense, having a round-robin exercise with the sync, with the Samosa Plus, with the Unwapper tracker, with the OCOG, and see if we can tackle the issue and probably stimulate the production of a thematic product tailored according to these specifications. Then the second question is about the mitigation of the grating lobes, which have been also discussed during the questions time. I understand it's probably a question for a workshop which is focused on altimetry. I probably know that CLS has been working on this in another contract with ESA-ESRIN, so I don't know if the results are now pointing at some solution in this sense. And the third point is about the usage of GPUs, graphical cards, so parallel processing essentially to speed up the processors. As you know, for instance, array trackers are very good, the analytical ones, but they require a significant time to replicate this scenario point by point, recreate the stack of looks to create the model waveforms. And so it would be interesting to understand if it's needed now, at least for the very established processors like Samosa 2 or those used in ground segment, to think about the conversion of the code to GPUs in order to speed up the production of the data and also later the reprocessing of the data once we improve the baselines. The point 4 is probably will be discussed with more people at the final session of this workshop when we will reconvene all together in the same room. And it's about proposing something like something that we already have by the ESA side at Coastal Altimetry Workshop, which is a training session lasting 1 day for early career scientists, students, but also open to all of you, in order to review the sensors orbiting in situ and the processing strategies, the modeling, and all the rest that can be useful to be aligned before the starting of the workshop and also support the preparation of students, early career scientists, and so on. So would you agree on this? I think from the faces, I think yes. Okay. Okay, so this is tackled. And now it's your turn. So I think they are pretty much aligned with what we have seen today. So please let me know your points, your comments. And as I'm supporting the technical office of ESA led by Jerome in shaping future activities, it's important for us to understand, by your point of view, which should be the focus of new research projects. So if anything is missing, I assume so, please just stand up and tell us what you want to see in future activities or what's missing or the limitations of current products and all these things. Thanks.
Can you come back to the first slide?
Sure.
So first point, A, I think that was already done. On the CNES side, at least, by Denis Blumstein years ago. He tried to use the AI to invert over inland waters the waveforms acquired by satellite data, and he get very promising results at that time. It was a student that performed the task, and I think that Malik indeed take the role to take back those. Okay, so I'm sure we did this years ago with promising results with Denis Blumstein, and this is certainly a way to look at a new way to process the data, and I agree.
Okay, so for instance, checking also the stacks, try to clean the waveforms, and then try to remulti-look would be an idea.
Okay. You look at that point on taking into account the echoes coming from the terrain, on the fact that there is some time non-variable part in the waveforms. And I said by François Boy 2 days ago, we should process not one single waveforms, but as done by several speakers today, a stack of waveforms or a data cube of waveforms to account for the sums of signals and to try to discover what is coming from the waters. Maybe Fernando, you can comment on that point as well.
Well, yes, it was a study I made with Denis and Clément Cogiola, which is now at CNES. We did a publication of that about 1 year ago. And it was indeed taking into account a waveform analysis of using deep learning, and it worked quite well. Yeah. The major drawback was the availability of the measurements, which worked well if the waveforms were effectively linked to a water body. That is the main drawback of but it's the same for any tracking algorithm. But it was indeed very promising. The only thing that it was very computation heavy, and it's still the case for many deep learning techniques. So I do approve your suggestion of using some GPU-based processing capabilities.
Yeah, and that's why probably we should move to GPUs based if it's possible, because at least on images, convolutional networks seems to be pretty good in performance and in speeding up the processing.
Yes, exactly.
So would be an idea. Okay.
Yep. So just a remark between AI and L1 and L2. So in the frame of the MPC and CryoSat 2, so for Sentinel-3 and CryoSat 2, in the frame of the CryoTempo, sorry, project, we use a waveform classification.
Yeah.
Based on the neural network.
Yes, that I know, yeah.
And that's something that, at least for Sentinel-3, that we would like to, so we add it in the roadmap. So probably, maybe not next year, but maybe in 2025, that's the plan to provide to the users in the L2 project of Sentinel-3, inland water project now, thematic project, this kind of information, classification of waveforms. So that's something that we are working on.
Okay, thanks. So it's clear we should include this also in future activities. Thanks.
Yeah. The waveform classification was done blindly. We don't know the surface. Regarding to your point 1, point B.
Yeah.
So what we provide to you, what you need to understand what is bright in the altimeter footprint for the first time. It's K-bound, it's not nadir, but for the first time we have both the sigma node, or reflectivity, or the backscattering on the altitude within a very high resolution. So we can mimic, understand, and we have a priori knowledge of the waters, both rivers and lakes, thanks to SWOT quality. And we will be in the position to make large use of SWOT for first simulating, and both to support the AI or neural network classification, to improve what we have done blindly in the past with our knowledge. Pickiness is one criteria, among many others. We have multi-peak. But why we have multi-peaks and what is coming in the multi-peak?
Yeah, that's the point. Another point will be to use what data is possible to simulate, ultimately waveforms coming from that specific scenario.
Yeah, we did all. A lot of exercise to simulate the data. But when you simulate waveforms, even over the oceans, it does not comply with what you observe because you don't know the surface. The surface is changing, and the surface is so complex over inland waters that you were not yet in the position to simulate accurately what the instrument is measuring. We had a presentation from Sophie Legac on the first day. They tried to simulate. The waveforms with a very high accurate models, but without any a priori information on the sigma node. So it was very difficult to match between simulation and the actual signal observed by Sentinel-6. But whatever the satellite. With SWOT, we can do it. We need to pay some attention to the SWOT capability to better understand what is required by the old-fashioned, but currently flying nadir altimeter data.
Okay, thank you.
I had a little bit different story. So not processing and retracking, but more geometry of the measurements. I'm impressed with the presentations about fully focused SAR and the resolution which we can get now. And this means we can get more exactly the location of the measurement on the river, and the accuracy is higher. And the problem still to be solved is the drift of the satellite. On lakes it doesn't have a problem, but rivers have a slope. So it would be nice to correct it. And previously, we made such a study with Christian Schwartke on the Oder River, and we obtained 25% RMS improvement on mean without having such a good fully focused SAR or good slope products. Now we have global slope data sets easily accessible and such a great resolution presented today. I think this is still a correction, the slope correction, which can give us some good improvements. And with the global slope data set, it's really easy to...
So you will suggest an activity considering this global slope data set to correct the measurements over rivers?
Yeah, because a measurement on the virtual side, because of the drift, is taken on different locations.
Yes, that's clear. Yes.
Okay,
thank you.
And to complement to what you said, and I fully concur regarding the slope, in fact, we have also the backscattering. We believe we are measuring nadir. We are not. We are trapped by the backscattering. And we have seen during the street art project, we have some experience where we illustrated that indeed we are not measuring at the nadir point. It depends on the roughness on the surface. And you can be trapped very offside, off nadir, and you don't correct for it. But with the fully focused SAR, you know where the point is coming from. We have some early results from François Beau in the street art public documents that are available. We need to pursue this kind of approach.
Okay, so I'll check the outputs of the project.
And again, with SWOT, you know the roughness. So you know when you have a quite collocated observation by where the signal is coming from. And we have observed, even over big lakes, very spurious waveforms. Years ago, we don't understand. And we are now in the position to better understand what the altimeter, the NADI altimeter system is looking for. Is not looking for, is tracking by.
Yeah.
Just a small comment, a bit sarcastic in the sense that we have the SWOT and now we see the two-dimensional field that is reflecting and so on. And that what we had before is just like a one-dimensional waveform, you know, with time. And we had a peak and another peak and another peak. So we tried a lot of things like multi-peak or persistent peak retrackers and so on. And what really has always bothered me is that we have this beautiful waveform and we apply the OCOG retracker, which is just like putting everything into one number. And it's exactly going in the wrong direction compared to, you know, going from a waveform to a two-dimensional map from SWOT.
You know, I agree, and I was saying this also before during the session, but also with reference to maybe the development of an FFSR inline water product, but not only FFSR. We should try to have a random robin exercise considering OCOG, the WOPR tracker, the SAMOSA tracker, the sync, and see the best performing one. And find the right recipe for the FFSR because from what we have seen from the presentation, the authors use different posting rates. So there is not a consensus on this. And another point, don't know if you agree, but ESA2 data now, of course, are very important, very precise for the slope determination. But in the FFSR coastal project, we use them also to just acquire a confidence band, so the minimum water stage and the maximum water stage for a water body, in order to later select the altimetry measurements, and those who drifted from this confidence band were excluded. So ESA2 data, when present, can be very useful for selecting SAR and FSR data in complex scenarios.
Correct on the, but it can be complemented by the 0.1.d that you have on the table. We have a large network of existing networks in France, in Switzerland, but we have demonstrated that in some cases we have a very large, with a network of Garonne rivers in France. And those kind of very dense local networks prove to be very valuable to better understand and to better assess the quality of the altimeter data. So this is, I would say, like Senetosa Ocean's calibration site. It's quite a super site. It's quite heavy to install and to maintain, but it's very valuable to better assess the performances of the satellites and to give to the users confidence in the data. So again, the approach proposed by 3TART project, I think it's very valuable, and we should work with a 3TART. I'm part of 3TART.
Yes, no, I followed the project
quite,
a few
quite
minutes.
easy to make some advertisement of the project. But
no, it's not, because we can start from the outputs like Hydrocoastal and try to converge. And
we have provided or proposed some methods on even Jupyter Notebook, open tools to assess the quality of any altimeter data flying over different situations. I think we should have a round-robin exercise, as you said, using those methods and tentatively pushing the approach that we have proposed so far, and complementing the networks of observations in different situations. We have very few. We have one in France, one over the Rhines, one in Po, several in Germany, but we are missing many more.
Yeah. Okay. Any other consideration, Jean-Christophe, for instance, about the future of drones and micro river gauge? Thanks.
Yes, concerning drones, I think it is very useful for validation because we can deploy at the exact location where the satellite crosses the river, so it can be interesting, and to have also the slope, the river profile. And so we are working on autonomous drone solution that can be deployed each time the satellite overflies the river, so without all the logistics, the complicated logistics of having a pilot and so on. So that can be very useful. And concerning microgauge data, I think we are improving the system in order to have as much as possible solution and parameters on the surface. So having images to get back to retrieve the surface roughness can be very interesting.
And also the flow velocity, as we've seen yesterday in this presentation.
Exactly. So we are working on different parameters, also the precipitation and what is going on in the atmosphere with the wet repose correction with the GNSS that Bruno Picard presented yesterday. So I think there is many improvements that can be made, and definitely could be very valuable data for Calval and for more understanding deeper the waveform.
Okay, thanks. I think we discussed almost everything. Just about this.
Maybe just one.
Sure, sorry. Yeah.
Yes, drone and micro reverse gauges are mandatory for Calval, but they are also very valuable for validation applications. We all know the limitation of the satellite data. We are not there to say that satellite data will fill all observation systems. But maybe tomorrow, when we have to develop some digital twin of the Earth, we have obviously to merge satellite data with other sensors. And having a dense network of sensors where we know the accuracy, which are reliable, will be of interest for us to propose methods merging satellite data with in situ sensors or dedicated sensors to perform this digital twin demonstration.
Okay, good, thanks. So regarding point 2A, would you recommend to have thematic in-water products at 80 Hz instead of 20 Hz for SA, especially for SA, of course, for narrow rivers, because now at 20 Hz in more complex cases or narrow rivers, we have just a few measurements.
We could do it, but I don't think this is, I would say, of tremendous interest today. Maybe it's of interest to ease the use of the data to the user. It has been required years ago as part of the coastal altimetry workshop and the inland waters workshop. And it's a matter of only product size, so we should go for it, obviously. But just to rephrase Paolo Cipolloni, I think that we need more studies. More studies are required to better understand the retracking and the accuracy before proposing evolution on the inland thematic product.
Okay,
to me.
Perfect. Okay, I think we covered mostly all points. If you want to add anything, please do.
Can you show? You're going to the next slide?
We already discussed a bit the second slide, but it's okay.
Okay. So on point 2, the 80 Hertz or the 20 Hertz in unfocused SAR doesn't change much. You still have a 30-meter resolution.
Just because
you can have the point where you synthesize exactly where you want it, meaning in the middle of the river. If you have a 300-meter river, you might have a point on the bank, another point on the bank with the 20 Hertz. And if you do 80 Hertz, you might have the point you want. So that's a lot of points. But if you're not doing very small rivers and so on, you won't need. And so the question on your point 2 is standard. Do we need standard products? In the sense that, we've been developing level 2 products from the agency, and it's frozen, and it takes 3 years to change one thing, and then we reprocess and so on. And so with this point 2, I think we should do some pitch for the ESA Altimetry Virtual Lab, where you can decide on the spot what you want. If you want 80 Hertz, if you want to apply Hamming filter, if you want to customize depending on what you're doing, your target. So I think it will be difficult, especially in the hydrology world, where everybody has a different geomorphology, different river, different basin, different size, different scale, different temporal, different variability. And I think we should recommend that we sustain a self-service system where you can go and have the product you want. Of course, you have to be a little bit trained to understand, what are these 60 different options that you can choose from, or use the default menu and target your domain. So advances in products, it's also advances in the capability to serve the community with data that we can call products at some point. And that means sustain the Altimetry Virtual Lab, because the Altimetry Lab is not funded. And it could be funded if a lot of people pay for the CPU plus the overhead to maintain it. Or we could insist that, an agency like ESA should continue funding a self-service system where you can do 80 hertz or 160 or 500 hertz if you want it. All you have to do is make sure you select the right parameter in the interface. And if a parameter that you're working on is not in the interface, you can also add that the AVL is updated and add another parameter in the interface. So maybe a little pitch to see if we could fund the AVL, because it's pretty costly. And in the end, they tell us, no, too many users, and we cannot fund these users, But we're funding, when we do a massive reprocessing, it costs a massive amount of money as well. So standard product or self-service product.
Yeah, thematic products are also not delivered from the AVL in the end, because when we have the coastal deal and profiles, it's what we do essentially. But I just wanted to get into this at the end. This AVL is the Altimetry Virtual Lab from ESA on the Earth Console platform, which allows you to process Sentinel-3, Sentinel-6, and Curiosat-2 data, fully focused SAR and SAR, applying several options at L1B and at level 2. Now we are trying to enhance the AVL by including these trackers I was citing, like KDM WOP and others, from research activities we had, like Hydrocoastal, FSR Coastal, in order to have the service aligned. And this should work as a middle entity between, let's say, the research and then the ground segment, which offers official products. So the idea is to create these data sets for the community, or in the frame of visa research contracts, in order to provide the best possible products with the most recent trackers or methodologies for processing in terms of L1B processing options, for instance, DMing, for instance, the zero padding, but also other. And so it's very important, as Jerome said, to have this properly founded and properly looped inside let's say, the research environment in order to stimulate the usage of these products and stimulate at the same point the further development of the Altimetry Virtual Lab. And there is a poster upstairs, one of the first posters you have in front of you, a smaller one, A1 format, in which you have more information about the Altimetry Virtual Lab. Regarding the 80 Hz processing, I fully agree, and there are also papers in which it is clearly stated that also over the ocean and over the coastal zone, it allows you to reduce the noise in a time series of measurements. And so the 80 Hz should truly be something that should not be recommended, but should be considered already, probably at ground segment level, not only for thematic products for the inland water, but also for coastal and if not also for the open ocean products. Okay, so I think we can, please, Shoshana?
I still have a point about the 20 and 80 Hz. I agree that we can ask to process the data again, it would be nice. But for me, it's clear that we cannot work in Riva with 20 Hz. It was clear also from the presentation, no one used, I think, used 20 Hz to reprocess the data. Okay. So if we have a 300-meter bright river, we just have eventually 1 point.
Yes.
Yeah. So it was also discussed at the OSST 2 weeks ago that I don't know how much it costs to produce at least 80 Hz. 80 Hz would be very nice. 40, I'm not sure, but 80 Hz data, everybody will be able to use the data if they are standard.
Okay. No, I agree with you, you know that, yes, thanks. Okay, any other comments? Okay, then I thank you for attending this session, and we can close it and go to the coffee break. Well deserved. Thanks a lot.
Okay, so good afternoon, everybody. We are a bit late, but we all needed a real break. And we are now ready to start the first session on advances in the use of Earth observation for land surface and hydrological modeling. And for the first talk, we welcome Rodolfo Nobrega, who will present, who has a presentation entitled Using Optimality Principles to Couple Terrestrial Carbon and Water Cycles in Remote Sensing Hydrological Models.
Hello, everyone. So thanks a lot for the introduction. Good afternoon. So, so this work here, I'm going to show very different things. So if you get confused, it's my fault, okay? So just ask afterwards. And what I would like to start with is by saying that I'm a hydrologist. And in the last years, I had the opportunity to work with vegetation modelers. And one thing I realized with vegetation modelers is that they do modeling in a very different way than hydrologists. In a sense that we hydrologists, we always think about calibration, validation. So I have the data here, I use this for calibration, validation. And because of these, we have like so many parameters. So many that sometimes when you see models with 10 or 15 parameters to calibrate, we call parsimonious. And in vegetation modeling, it's quite different. We have parameters, but they're fixed. And most of the time, and you don't have this validation, calibration, you have more like you compare with observations in a sense that we don't waste data that we use to develop the model. And what I see, for example, in this quote here from this paper from a few years ago, is that we are missing, I think in hydrology, we're missing opportunities to use this amazing portfolio of data that we have now, satellites, to break a bit this paradigm and go into model development from another perspective. So what I'm going to show today is a bit of what we can learn looking at remote sensing evapotranspiration and how we can use optimality principles to improve our understanding of ET partitioning and soil water stress in a very simple way, and how we can, for example, use these concepts then to apply in hydrological models. This is a paper, so we published a few years ago, 2 years ago, and what we did, we take observations from several flux stations in South America, and we run these algorithms using the terrestrial data, so as driving data. And we try to see these algorithms that normally use remote sensing data, which one is performing better. And as you can see, there's stations from different land covers and different areas in South America. So it's a thing that was not really fully evaluated at the time that these algorithms were published. And what we start seeing is, to summarize, is that all models are fairly good. So you use remote sensing, you use or use data from the field. They give valuable results. And as you can see here, some models are better in one kind of ecosystem than the other one. But overall, they're all quite good. But what we are evaluating here is evapotranspiration. And I like this quote here, which is basically from the same author of the other one. But I kind of agree. So I think it's time now that we start looking at evapotranspiration as one single component and see how this is separated in different ones. And one proof of this is that the same paper later on shows this graphic. And as you can see, different models, even though they agree quite well with the evapotranspiration, they disagree how these components between interception, transpiration, and soil evaporation is divided partitioned in different ecosystems. As you can see here, you can vary from 9 to 24 for interception. And also the relationship between interception and leaf area index. So, but why we still accept this? I mean, first of all, of course, we don't have data to most of the time to validate or improve these models. But also, there is this kind of comfort zone that if your model lies in this area where you have transpiration between 40 and 90%, you know, and you kind of accept automatically the results of the model. But there is a lot of things to investigate in the transaction between these components and different inputs, different ecosystem processes or parameters, they play a role here. But there is a way that we can now, with satellite data, improve this. And at least what I'm doing is focus on transpiration. So transpiration is the process that the plants, they lose water and they simulate carbon. And in vegetation modeling, there are several models that we can use to estimate CO2. And the observations that we have with flux towers, GPP, so gross primary productivity, they measure exactly how much CO2 plants are simulating. So for this example here, I'm using this model here called the P model. So it's a productivity model. It's very simple and entirely based on remote sense data. So the model is basically, we try to get how much energy the plants are absorbing. And then there is a light use efficiency model that optimizes the cost of carbon simulation based on the cost of the plants to evaporate, to transpirate. And in this model, later I'm going to show, and we talk about this better, that basically not all, but most of hydrological models, they have this stress function that usually they use with potential evapotranspiration. So the core of the model is this ratio between internal and external atmospheric carbon concentration. And there is an optimization going on here with several parameters. And so the idea is that the model behaves quite well. And the idea is that, as I said, that water is leaving stomata while CO2 is being assimilated. So if you get GPP, we can trace back then how much transpiration is happening. So in this paper published here this year, so my colleague Tan Shen, and we investigate here how we can use this model to estimate transpiration. So, and we basically get the GPP and the chi with the P model. Then we use the dissipation, so the Fick's law, to get the stomata conductance, apply in the P moment-T equation that you all know very well to estimate transpiration. So we do an empirical calculation of the total evapotranspiration based on the flux tower observations. And we try to validate, to verify these estimates using different scales. So the FluxNet site scale, the Bayesian scale validation, but also global evaluation with other ET products. As you can see here, the points here, the towers and the river basin spread over the world. So what we can see is that these estimates are fairly good. They are not really out of the margins that are acceptable. Here is the first of the sites. Here you can see with the river basin evaluation. And in this case here, we use two different data sets. So this is river discharge, but also kind of reanalysis using runoff. And we see they are reasonably, but the line here, the regression one-to-one falling quite well. And also comparison with other products here that we see here in case of transpiration only, how important is around the world. What we could notice is that, for example, the Amazon forest region and Congo forest as well, the transpiration's a bit higher than the average of the remote sensing, usual remote sensing products. but fairly well distributed and reasonable results. But as if you remember, there is one point in this simple model that's extremely empirical, that is the soil water stress. So we're thinking how we can actually optimize this. And there is a very old concept of water deficit that is from 150 years ago, more or less, and is to design the capacity of reservoirs. And basically, how can you know how much water you should store for supply? Is basically the mass balance. And if you think of for a moment, it's the same principle that plants actually work. If they expand their roots on to store as much as water as possible for transpiration, we can use the same here. And this started to be used just in 2014. And the reason is why, because before we didn't have reliable results in estimates in evapotranspiration. So these started to be in 2014, and later on, a lot of papers published in hydrology using this concept. The problem with this is that all this work here is also related with a lot of calibration of this method. And we realized that actually just needed small correction to the method to make it calibration free. So we have the water deficit, we have the root zone water capacity, which is the maximum water deficit. And just to fix this, we just need to use the seasonality index, which is basically just how the variance of the precipitation around the year. Just to explain a bit more, so the usual method that this model that I'm presenting you, the P model, use is a beta function which use soil moisture and also use a Q that's calibrated with two parameters. So it's a very good method to track soil water stress. So you have double calibration and you also use soil moisture observation. The difference with the water deficit method that I just showed to you is that we need the influxes of water, precipitation, the effluxes, basically evapotranspiration, and then we can calculate the surplus and the deficit of each time step here, which I'm using monthly. And finally, instead of this equation here, we simply use the root zone water stress, which there is no calibration at all. And later on, I compared with the published results from the P model. And what we can see here is that these results using this method here, there's no calibration and use the water deficit method. They're slightly better than the one that was published with calibration and soil moisture observations. But then the question from this point, what I'm going to show you preliminary results is how we implement this. Okay, we're using vegetation modeling. It seems to be a better method, but how we can implement this in a hydrological model. So again, there is an old method that is still widely used, which you have the storage and you have the runoff. So if the storage of the root zone, in this case, is the maximum, the relation between effective precipitation and runoff is linear. Okay? And this is using many hydrological models. And for example, in these ones here, so I took the core of these models here. So the concept of this box-style hydrological model. And instead of using the usual approach that hydrological models have, that they use potential evapotranspiration, we use transpiration from the P model, and also the water deficit instead of the water stress with soil moisture or any other information that they use. And the results are quite interesting because here I compare here, I select few, so in blue are wet regions, and in red are more dry regions. And the results here, you can see if the model used the potential evapotranspiration or they use the GPP outputs converted to transpiration in wet and dry regions. So in wet regions, you see this systematic offset between the results of both, which we can attribute here for interception. So basically here, because if I'm using here GPP, just transpiration, I'm ignoring the other evapotranspiration processes, components. But it's systematic. So you see this offset here. And in the dry regions, this is quite different because different dry regions, they have different soil evaporation contributions. So, so we're still doing this work here, trying to elaborate a hydrological model that is 100% based on remote sense data, as less as parameters that we can use. So trying to do this without calibration and integrated with the carbon cycle using optimality principle of the P model. So basically, this is what I see that remote sensing is allowing us to do now in hydrology, and is an opportunity that we should not miss. And in terms of recommendations, it's not actually based on this work. It's more like what I would like to see in the community. I would like to see actually more data sets, because the advantage of evapotranspiration transpiration is because it's distributed. So you're not calibrating the whole hydrological model using one single observation from the outlet of the catchment. So you're using a distributed information, and then you can validate the model in different regions of the catchment. So I think it would be quite good use this new technology, use new methods, for example, SIF, to derive global data sets on transpiration, not only on GPP, and also take advantage of all these developments. I see here a lot of discussions on the methods to generate better discharge. I know that this is a current challenge for the current observations, but as soon as this progress, I think it would be quite nice to see also take advantage of this technology and data we have now to correct all legacy data we have from the last decades on discharge. So there is a poster there from a student of mine, João, is here. So he's using large sample hydrology with 715 catchments to estimate how the hydrology in South America varies through catchments. And one challenge we have is because this legacy data has a lot of errors. So we are compensating these in the parameters, in the calibration. And it would be quite nice if you can reproduce this legacy data using kind of corrections. We have this altimetry, for example, that is producing. So thanks so much.
Thank you very much. Is there any question? We have time for one or two questions. Yep.
Hi, Rolf. Really interesting stuff. About the SIF, we've done quite a lot on that. I wouldn't put too much hope on it. It actually didn't look too well, but it's published though. But I was wondering about the overestimation of transpiration in the tropics, which is also an issue that we have. Do you consider the fact that you have a suppression of transpiration due to interception, right? Like you have your leaves being wet, not exchanging gases, and also, of course, interception at the same time consuming the energy. So it could be something related to that that is perhaps not in the optimality theory now.
Absolutely. That's a big challenge we have. In the end, most of the time we need to just remove wet days, right? And in these wet days, we don't know actually what's happening, what time the rain happened, how accurate are these global rainfall data sets, if it rained during the night or during the day. And we always need to do some assumptions around that. But yeah, so I believe that that's a gap that we need to work, and mainly the tropical forests, and revisit some experiments that about interception. And there's also a poster that we work in interception. If you want to see later on, Fernanda is right there, so we work with her in this. But yeah, I agree with you totally. Thanks a lot.
Any other question? No. So I guess we can move on. Thank you again.
Thank you so much.
And the next presenter is Jos Brombacher. Sorry for the pronunciation. And the presentation title is Daily Accurate Evapotranspiration from Global to Local Scale.
Yeah, thanks for the introduction and thanks for having me here. My name is Jos Brombacher. I'm a researcher at ELIF, a small company based in Wageningen, the Netherlands. And yeah, today I want to talk to you about the daily accurate evapotranspiration data set we have, which is applicable from global to local scale. Just a short introduction to the company itself. So we have about 20 years of experience in evapotranspiration modeling. And the modeling itself is not our core business, but we use this data to make solutions for the agricultural sector, for the water and environment business, and also for insurance and, well, the insurance sector. And the model we use for this is the ETILOOK model. And ETILOOK is a globally operational evapotranspiration model. And it was developed to be a reliable remote sensing based model to be deployed on a global level at various resolutions, depending on the satellite data that you're using. And ETILOOK is currently also the backbone of the FAO's VAPOR initiative. And there we are providing hundreds of terabytes of data on water productivity for free to the community. The model was developed in 2012 by Bastiaans et al. And it was an improvement upon the original Sable model. And we used the Penman-Monteith equation to model the soil evaporation, the canopy transpiration, and interception on a daily basis. And for the soil moisture stress component, we use a trapezoid model, which combines normalized difference vegetation index data with sharpened land surface temperature data. And this all enables us to produce ET data at resolutions ranging from 300 to 10 meters. So this is how the flowchart of the model looks like. And as inputs, we use optical remote sensing data as well as thermal remote sensing data. We use weather models, and all these data sets combined are used to calculate specific intermediate products. And these intermediate products then gives us the evapotranspiration and the interception as separate modules. So previously, we are quite a small company, so we did it all on our internal hardware. But since the FAO required us or asked us to actually produce a global evapotranspiration data set on a decadal basis, we decided to shift to the cloud. And therefore, we are now using Amazon Web Service. And just an example on the amount of data that we are now processing. So this is for our global and also our regional African product. We use about 2 million Sentinel-2 tiles and 20 million VIIRS observations to produce about 100 million intermediate products, which are then combined into 15 million daily outputs. So it's quite a lot of data, and it takes quite some time to process as well. So since 2016, ELIF is providing the FAO with ET data. And since this year, we are the sole provider of the new VAPOR data components. And this is the VAPOR version 3. And version 3 entails that we provide evapotranspiration data at 3 different levels. So a global data set, which is called level 1 at 300 meter resolution. A data set for Africa and the Middle East, level 2 at 100 meter resolution. And also within the African continent, we provide 20 meter data at 20 different irrigation areas. And we do this all on a decadal time step. So the data is produced daily, but then aggregated to a decadal time step. And we provide data from 2018 till present day. And we have a latency of about 3 days for this data set. So currently the data set of level 1, so the 300 meter data is live. So you can all look at this data at the VAPOR portal. And all the other data sets will come in this portal as well in the next couple of months. And we're also really proud that the FAO won the 2023 GeoSDG Award for their WAPOR initiative. So yeah, that makes us really happy that we're also part of this interesting and important collaboration. So this is just a quick example of an annual sum of the evapotranspiration for 2022 for the globe. So for us, this was also the first time that we actually produced global evapotranspiration data. We have also always been focusing on the African continent. So we're really happy that we are able to provide this data. And here an overview of some of the different levels we have and how that data then looks like. So this is an example for the Bekaa Valley in Lebanon, which is a very heterogeneous irrigation scheme. And as you can see, the level 1 data is capable of detecting some large irrigated fields, but definitely not at very big detail. But then again, level 2 and level 3 are capable of actually observing the evapotranspiration at a better and finer detail. And especially the 20-meter data enables you to really see the small irrigated fields, which is quite interesting in such a heterogeneous area. So in this presentation, I also want to talk to you a little bit about the validation we did for this data set. So the data is only out for a couple of months, maybe 1 or 2 months. So these are just really preliminary validation results. But we did some internal checks to make sure that the data was sound to be able to share it with the FAO. So for level 1 and level 2, we think the data is suitable for catchment hydrology modeling. We did a really simple water balance check just to compare the different evapotranspiration components with the runoff and the precipitation to see if there were any big deviations with these data sets. And we found when combining 4 of these major catchments in Africa, that the total deviation was about minus 1.8%. So we found that quite reasonable. And further validation we did for America. So we used a FluxNet data set and we made a subset of 63 different stations which had sufficient data for this 2018 till 2023 period. And we used our level 1 data, so the 300-meter resolution data. And we did a really simple point to pixel assessment. So we didn't account for any flux sensor footprints. And to the right, you can see the results of this analysis. So the R-square is decent, and if the red line is also quite close to the one-to-one line. So we don't really observe any significant biases. Maybe that at the low evapotranspiration range, we're overestimating a little bit, and at the higher values, we're underestimating a little bit, but in general, it's quite close. And in the next couple of slides, I actually want to discuss 6 different stations in a little bit more detail to let you understand what our data is capable of, but also what are the pitfalls of the way we model ET. And to show you that we didn't really cherry pick, or we tried not to cherry pick as much, the small plot shows the correlation between FluxNet and ETLUC for these 6 stations. So first 2 stations, which we think are really showing quite well examples of our model. The correlation is quite strong for both sides, and especially the amplitude. We think it's quite important to get that amplitude right, and that's also the case in this comparison. And we also don't really see a significant bias between the 2 data sets. But if we zoom in a little bit in the top field, so that's an alfalfa field, especially in 2018, you can see that our data is a little bit delayed and falls behind the actual flux tower observations. And this is potentially caused by cloud cover. So we use a smoothing model, which uses the previously available images to interpolate to the current date. And if there's a lot of cloud cover in the start of the growing season, then we don't pick up that change in crop cover and therefore also don't model any evapotranspiration. So that's definitely a pitfall, but that's something we just have to deal with currently. But if you look at 2021, you, for example, see that there the start of the growing season is captured well. So it really depends on the area and also it really depends on the area, basically, if there's a lot of cloud cover or not, how well the product works in this case. So the second 2 sites are showing quite decent results as well. The top one better than the bottom one. But if you look at the top one in a little bit more detail, you see that the variation of the evapotranspiration is not as well captured as what you would have expected from the flux towers. And for the bottom plot, you see that actually in the start of the growing season, the correlation is quite decent. But then in summer, it really drops. And I'll explain in a minute why that is. So the first example, this is also an alfalfa field. And if you look at the flux tower data, you can see that there are 5 distinct harvest cycles of the alfalfa. And because we use a smoothing algorithm to account for the missed images due to cloud cover, we don't really always see those kind of harvest effects, those really steep changes in vegetation cover. And for this kind of crop, this product would be quite tricky to use. And it more or less shows like an average ET signal for a longer period, I would say. And then for the bottom field, so this is a really heterogeneous area, as you can see in the image on the right. And I've been looking into Google Earth, Google Maps, Google Street View, to see what was going on in this area. And on the left, you can see this result. So in spring, you have trees, both as grass, which is, well, evaporating happily. But then in summer, in this image, you can see that the grass is drying and dying out. And the trees are still green, so there's still transpiration happening in the trees. And because we use a 300-meter pixel and the flux tower has maybe a 100-meter footprint, there's a bigger discrepancy in summer than there is in winter or in spring. So that's something to take into account as well. Then the last 2 examples are from more homogeneous areas, but then in different climate zones. So the top one is a dense forest with little stress. It's in the northern part of the US. And there, the model captures the evapotranspiration quite well. And for the sparsely vegetated area on the bottom, you can see that the correlation is also okay-ish, but it might be that the soil moisture model we use is a little bit overestimating the soil moisture content for such a dry area. So to conclude, we think that ET-Look model is capable of actually accurately estimating the ET on a daily basis. And also the current data factory enables efficient production of global and local data sets. We didn't see any clear signs of a strong bias of the ET in any of the United States biomes we've checked. And although we think that the smoothing algorithm works well to fill no data gaps, and especially for the FAO, this is really important because they want a data set which is clear of any no data values. It can also negatively affect the short-term variability of the ET. So then for the outlook and recommendation, so the decadal level 1 VAPOR data is already available, so you can check that on the portal. Level 2 data is currently ingested by the FAO, so we expect that to be available next month, early 2024. And level 3 data will be delivered in early 2024 as well. So we did this quick validation, and that's just an in-house validation basically, but IHE Delft is actually making a more thorough validation independent from us. So we also expect to have a better validation study available next year or the year after as well. We also think that the model can be improved on specific points. So currently we use quite a simple big leaf model, and we want to convert this to a multi-layer model. We also want to implement either a water balance module or connect with radar-based soil moisture products for improved soil moisture stress coupling. Especially, this is especially important in drier climates. We want to be a little bit less fixated on the NDVI for leaf area index modeling. And also we want to have a flexible user need depending smoothing algorithm. So for the FAO now, smoothing is really important, but maybe for some agricultural clients, they really want to have spot on day-to-day information without any interpolation. So we also want to implement that as well. So I would like to thank you for your attention. I look forward to discussing our results. But also, if you're interested in using our data for scientific research, you can always contact me, and we can have a look, because well, this data is publicly available through the FAO portal, but it's only on a decadal timestamp. So if you're interested in daily data, for example, we can also discuss if that's possible to be delivered to you as well. Thank you.
Thank you very much. Any question? Yeah.
Thank you so much. Very impressive. It's just a very quick question. When is the record starting actually?
Sorry?
When does the record start? Like,
Oh, okay. Yeah, the record started in 2018. Yeah, because we mostly rely on Sentinel-2 data. So yeah, from 2018 onwards, we have quite a good data set.
Yeah.
And do you have plans to extend that back in the past?
Yes. So I think the FAO wants us to also provide data from 2010. So we therefore need different sensors. And that's something we want to investigate in the future as well. So for example, level 1 data is fully reliant on MODIS and VIIRS. So we could go back a bit further than what we could do for the high resolution data sets, which are reliant on Sentinel-1. But for now, it's just 2018 until now for the VAPOR delivery.
Just a small question on, I think it's very, very interesting. Do you check the consistency among the 3 levels you work with? I mean,
yes. Yeah. So that's something we are also looking into currently. So we first have delivered the level 1 data to VAPOR, which is sort of the benchmark data set for us. And the level 2 and level 3 data sets will actually be compared to our level 1 data set to make sure that the different resolutions are not making differences in total evapotranspiration for a catchment, for example.
You have also the plan for making the data operational available for the last 10 days, something like this, in the portal, or I don't know?
Yes, so the data will be updated for every decade, 3 days after the decade has ended.
Ready now?
Not yet. No.
When?
Early next year, I think. Yeah.
Just a small question. So if I understood correctly, you said that you are able to close a water cycle with 1.8% of error?
Yeah, after a really quick assessment. I wouldn't say it's really an accurate comparison, but...
This is very impressive because none of the inputs actually we have with this accuracy. So
yeah, but I think if you look closer to the results themselves, so it's all the 1.8% is all lumped for all these 4 different catchments, and in the catchments themselves you have some discrepancies between the precipitation and the other components.
Okay.
So we use this 1.8% just to make sure that we're not biased towards overestimating or underestimating. But if it's truly that 1.8%, I cannot tell you.
Okay. Maybe we can help you doing this evaluation.
Yeah. Okay. Yeah, would be nice. Yeah.
One more question here. So since you also use MODIS and VIIRS, and there are already MODIS and VIIRS ET product, and apparently there are a lot of other ET products available now. So did you also compare your results with the other ET products?
Yes, so we did a really quick comparison between these data sets. Also OpenET, we did a quick check for some sites. Yeah, I couldn't say what the results of those comparisons were. We didn't really focus on making sure that our data was similar to the other data sets. We just did a comparison to see if there were any big deviations in tropics or in desert-like areas. But we didn't have any clear results on comparing these sites. I think that's also something we want to do in the future.
So you said that the data is available. At which resolution you think you can distribute that at the global scale?
So the global data is at 300 meter resolution. Yeah.
Okay. Good. Thank you.
Okay.
And our next speaker is Wei Liu, pardon, sorry. And his talk is entitled Improving Soil Moisture Simulations Based on Satellite Data Optimized Soil Texture Data.
Okay, thank you, Chairman, and thank you
have this opportunity to share our result about the soil moisture simulation. So this work mainly done by my PhD student, Qin He. She got the degree and now is working as a postdoc under the supervisor of Taikan Oki in University of Tokyo. So yeah, the background for my research is mainly focused on soil moisture, both remote sensing and simulation. So we use the soil moisture remote sensing data as kind of a, how to say, benchmark or kind of a boundary condition for model simulation. And I also have done some kind of data simulation to digest soil moisture into render surface model. But for more than 10 years, such work I found I never improve the model itself. I just improve the performance of estimation. So why then we want to do the work to use the soil moisture to improve model itself? It's included two steps. One is try to use the information of temporal change of soil moisture remote sensing data to identify the model drawbacks. So we use the time series information, not the quantity itself. Another is why we try to use some information derived from this kind of time series to optimize the soil texture, but not only the soil moisture value. So the information, temporal variation information for soil moisture, we call the soil moisture memory. It's mainly, you can derive it from this kind of soil moisture dry down curve. It's a kind of important index to describe the strength of land atmospheric coupling at each pixel. So as we know, for this kind of soil moisture dry down curve, it's controlled by the different period of evapotranspiration. So for example, in the energy limited period, the dry down is very fast, and this only took so long. But for the water limited period, the dry down is slow and mainly look like this red line. So we want to derive this kind of two information to characterize the soil property for at each pixel. So there's two targets of this research. First of all, we want to use the SMAP soil moisture data to derive the soil moisture memory, and then compare with the reanalysis data to say the current reanalysis data have good dry down speed as the SMAP observed one. Because in our past research, we found different reanalysis data have a different dry down period, dry down speed. So it's a kind of, check the performance of currently available reanalysis data. And we also want to find some reason why the model performance is different. Actually, we found there are some kind of key regimes or key characters that control the dry down. So then we think back, can we use such kind of characters as a constraint condition to optimize the soil texture data? So if we can have soil texture data at the same resolution as a model simulation, this will be much help for improving model performance. The work actually done is very simple. So just as we say, we have a SMAP soil moisture like this way, we can identify the dry down curve for each pixels, use this kind of time series data. We can get the dry down curve for each pixel and then derive this dry down into the two period. One is energy controlled one is limited water controlled one, and identify this kind of dry down characters. So actually, we need some kind of mathematics and some kind of analysis. But finally, we can derive the two memory characters. One is so-called longer term memory. It's the dry down period or dry down time during the water limited ET controlled period. Another is shorter term memory, we call the tau S. It's for dry down during the energy limited period. And also we can get the two important index to describe this dry down curve. One is a so-called waiting point. Actually, it's not the waiting point used in agriculture. It's a so-called waiting point in our dry down study. Another one is a critical point. It's just identify the transition from energy limited to the water limited. These are two parameters. We think using these two parameters and expressional function, we can describe the dry down curve at each pixel. So the data used is very simple. We have the SMAP data and use 5 years one. We want to know this kind of dry down curve does they have changed during different year, and because we want to identify the energy limited period, so we should identify first the GPM, the rainfall case. We use the GPM, and we have used analyze this kind of 6 popular analysis data, and all data are merged to the 36 kilometer resolution as SMAP can provide it. So result is showing this slide. First, we show the different dry down time. So for the tau S, it's showed in the upper square and in tau. So from SMAP observation, the tau S and tau L is anti-correlated. And for the different year, this 5-year case, we can find tau S and tau L globally do not have too much change. So because the former work, we just use 1 year data to derive this one. But for the 5 years, for each year, it's almost stable, not too much big. But the model has a different performance. Here we compare the SMAP observation against the model multi-model mean. So we can find for the tau S, the model have kind of underestimation. For the tau, model have the overestimation. But the model have also can reproduce this kind of anti-correlation relationship between tau S and tau L. But the model have a bigger overestimation for this kind of water limited dry down period. And we can also get to detail to see each model's performance globally. And to be clear, we can see this kind of box plot. And the SMAP observation is the gray bar, and the different model is a different color bar. For the tau S or SM again, the SMAP observation is much larger than the analysis data. For the tau and the model have overestimation, and the SMAP observation is small. And we also can find that the different model have different performance. So if we model describe the real world, so model should be converged. But currently, the 6 analysis data popularly used one, they do not converge for describing this dry down. And fortunately, information is in ER5 is most close to SMAP. I think is why this data is much popular in our field. Then we can derive the so-called theta W and theta C, these 2 parameters at the global scale. And also we can find the theta W and theta C value. Yeah, they have different model, also still have a different performance. And especially for this kind of low boundary of this dry down curve, all the model have a kind of overestimation and a large value. And the most important is that we can find this SMAP derived waiting point or theta W value is very small, at around 0.05. It means really dry situation of SMAP C. But for the multi-model mean, it's much larger, maybe kind of 3 or 3 times larger. And you can also find this range is much bigger. So currently, we think this kind of overestimation of the dry down, the boundary, low boundary condition of dry down is a big problem. So we have a theta W and theta C. So we can use it as the condition to control, to constrain the soil texture data. So work is very simple. We have a kind of a baseline data. We just come from a GSDE, some soil data set from a global simulation one. Also have a HWSD. We think this data have a much information. It's very important. So I don't use this one. And we do not want to change it too much. But we think they have some bias because such data come from the institute investigation. It's not intentional to provide the information at a peak size. But for model simulation, we use it for the as a pixel or as some grid. So that's such a kind of information. So we use this two data set as the baseline data set as for the simulation, and we just try to add in some perturbation on the baseline soil mass data, and then we can try to use the soil pattern transfer function to calculate theta W and theta C, and compare with remote sensing observer one to do the optimization to get the final optimized soil texture data, especially sand, clay, and silt content, to fit it with the SMAP derived one at each pixels. And we do it, we also use the different pattern transfer function because we know there are many pattern transfer function to describe the texture relationship, texture and the property relationship. So for example, we have three kind of pattern transfer function and the soil data set composition. So we can use GSDE with different pattern transfer function, especially the case you consider or do not consider the soil organic material. That will be much important for impact the dry down curves. And the work is here, so we just try to increase perturb the original soil texture data as some small value, but we do not do the fully, how to say, optimization one. We just do kind of 3,000 times step increase or decrease and find which one is best in this kind of zone. It's some kind of preliminary result. In future, we'll try to do the global optimization. So the result is like this way. So the soil moisture derived from theta W and theta C shows the left, and the optimized one shows the right, and the middle one is the default one. So you compare the remote sensing derived one with the soil texture default derived one, you can find that have a difference, especially you check the histogram at the global distribution. The pattern is almost different. So after our so-called optimization or such kind of perturbation, the distribution pattern getting from original GSD one, you have a kind of closer to the remote sensing derived one. Especially you can find this kind of histogram is much like the remote sensing one. So this work we can try to improve, or we try to optimize the soil texture data, use remote sensing observer information. Then use such kind of soil texture information, we can try to run the land surface model. For example, here we run the NOVA model of China domain and compare the simulated soil moisture with the remote sensing one, remote sensing observer soil moisture, and also compare with the Chinese kind of land data assimilation output for the soil moisture. So left column is the default case. In this case, we use the default soil texture data. We can find we have some kind of overestimation as show this kind of triangles. But in the case we use optimized soil texture, we can find this kind of overestimation is partly mitigated. But actually, we cannot fully solve this kind of overestimation problem. But use the optimized soil texture data, the improvement of soil simulation is obvious. And again, we can check this kind of histogram distribution map over whole China. So again, left is the remote sensing observed the soil moisture histogram black line in China, and the dashed line is the simulation result. We use the default texture data. It's much high and much much narrow range. And another solid line is the optimized one. So use optimized text data. This kind of narrow distribution can be get wider and get closer to the remote sensing over the run. And the right figure show the observation is coming from a data assimilation case. This distribution is a little different from some remote sensing one, but again, after you use the optimized soil text data, this kind of distribution pattern get closer to the data assimilation. And then we compare the soil moisture, simulated soil moisture against the ground observation over the 700 stations over China. So for the yellow case, yellow triangle, it means use the new text data, the simulation is get improved. So for the monthly and the seasonal scale, bothly, we can find that almost the yellow triangle is much more than the purple one. But we also have some problem we can find in the northwest part. After we change the texture data, the result is not good. But for the mainly part of especially agriculture worker field, when we change the text data, use optimized one, the soil moisture simulation get improved. If we go detail to check this kind of histogram or box plot for the simulation, the observed texture, observed soil moisture box plot is in gray bar. So for the experiment 135, it's the simulation uses default text data, and for the 246, the simulation uses optimized text data. So as shown, this kind of CV and the range, after the soil texture optimization, the range and the variability get improved and get closer to the ground observations. So in today's talk, I gave a report about our research. First, we will use soil moisture remote sensing data to derive the dry down curve and the dry down properties, and compare with the 6 RANDSS data. We found this popular the 6 RANDSS data have a kind of bias compared with the SNAP observation. And we think partly it can be due to the the soil texture data, because it uses soil texture and the pedal transport function. This kind of dry down curve cannot be reproduced. Then we use it, go back, use this kind of remote sensing derived theta W and theta C to optimize the soil texture data, and found that this kind of simulation can be partly improved. So the recommendation, I think, because this talk I have done in different community. So in the remote sensing community, I have such kind of suggestion. So we should have a reliable and consistent soil moisture remote sensing data, because all the work derived the dry down curve, derived the character index, it should be a consistent data set. If the data quality is not consistent, it will make wrong information for our optimization. And currently, when we submit this work to James, and one reviewer challenges us how to validate your soil text data is better than the default one. Because this is a tough one, because we optimize in the 36 kilometer. Observed one do not have 36 kilometer. But I think if one can have soil moisture data in 10 meter or in 30 meter, at that time we can optimize the soil texture at this kind of local scale. It can be compared to the ground observed soil texture data. And also, currently we only have soil moisture information for a surface layer, so we can only optimize the soil texture at the surface layer. But we know soil texture different at a different layer. So we have deeper soil moisture, and we can have deeper soil texture data. And the experience learned from this work is we do not only provide the soil moisture quantity, but we also try to bond some key properties that determine soil moisture information, especially the soil moisture temperature change, like the dry down information. I think this work is simple for remote sensing people. you just try to analyze your data, can get more detailed information. But this information is very important for the model developer. They do not have such information. For example, the text data, the model developer just try to use FIO, use blah, blah, but they know they have some kind of mismatch between the origin data and the grid, but they do not. If we remote sensing people can derive such kind of property, it will be much helpful for model development. So I should stop here. Thank you for your attention.
Maybe just one burning question, to be too late.
Just a small comment. So what do you do in highly vegetated areas? Because we know that the soil moisture estimations are very bad in this case. So how can we improve that?
Which area?
Highly vegetated areas.
Well, yeah. Actually, we do not focus this one. Yeah, maybe we will try to discuss it in detail in future. Yeah.
Okay.
Okay.
Okay, thank you. So let's move on. And our next speaker is Vianney Sivel from Siena ERP, and his talk is entitled New High-Resolution Precipitation and Soil Moisture Earth Observation Data for Hydrological Modeling in the Mediterranean Region.
Okay, hi everybody. Today I will show some results obtained in the 4D Med project. If you have been here since the beginning of the week, maybe you have seen the overall project led by Christian Massari. And today I will show some application of precipitation and soil moisture products that have been produced during this project. As a short introduction, recent development in earth science system offers new high resolution, kilometer and daily data set for various components of the water cycle. And in this study, we try to evaluate the added value of such a product for hydrological modeling in the Mediterranean region. So today I will show the interaction between the selection of hydrological models and the precipitation data set for stream flow prediction. The potential added value of considering soil moisture for hydrological model calibration, and the use of satellite-derived precipitation to calibrate land parameter model within mesoscale catchment in the Mediterranean region. So in this study, we selected 5 catchments which share some common properties. They are precipitation driven, so no influence of snow. And the area are around 100 to 1,000 kilometers square. We are interested in pretty small catchments. And also we are focusing on low inertia of hydro system. So we have here the 5 catchments that have been selected, 3 in the northern part and 2 in the southern part of the Mediterranean, trying to have an ensemble of catchments around the region. In this work, we selected 4 hydrological models, the GR4G, the HBV, EMOD, and Miche model. The idea is to select various models to account for the structural uncertainty and the parametric uncertainty in hydrological modeling. So we are sure that the results are pretty robust when we want to assess the added value of precipitation time series or soil moisture. And so in the methodology, we calibrate the 4 hydrological model with the Schaeffer complex evolutionary algorithm. And then we selected 100 run with the better performance. So at the end, for each precipitation product, we have 400 simulation, allowing to get a distribution of hydrological modeling performance. And also it's allowed to compare the distribution between the use of various products. Here are some just basic information about the various precipitation time series we are using. We selected 5 precipitation time series. The first one is called the reference, shown here in blue. We selected the more suitable data sets computed based on ground station and sometimes with reanalysis product when available, depending on the territories for the catchments. And also we use the CHIRPS, Persian CDR, the eMERG LR, and the new CPC GPM SM Terrain ASCAT that has been developed within the 4DMET project. And so we can compare the performance, or let's say the mean performance that we can get with these various precipitation products. So in this graph, if we look at the first line, we have the distribution of the performance through the Klingupta efficiency computed on the discharge. And on the first line, we can investigate how the hydrological model performs regardless the precipitation time series. So for each box plot, you have the distribution of the model calibrated for the catchments with the 5 precipitation data sets. So we can distinguish the 4 hydrological model. And in the second line, we did the same work, but we discriminate the box plot with the precipitation time series. In the first line, what we can see that the GF4G model pretty perform the other hydrological model, but in fact, there is kind of overlap in terms of performance between the various models. But if we look at the precipitation, it seems that we are more discriminative regarding the selection of the precipitations we want to use for the prediction of discharge. And in this second line, we can see that the reference data set is still the better precipitation time series and offer the better predictive performance for the hydrological modeling. And so it outperforms the precipitation based on satellite products. But one of the main results here is that the new CPC GPM SM Terrain ASCAT allow in some catchment to be very close from the performance that we can get with reference precipitation, which is a pretty nice result. And so if we look in terms of ranking based on the mean KGE value for the various products, we can see that the reference is always first, not on the Mejada River because we don't have reference data sets. But let's say that the reference is the first for all the catchments. And in second, we often have the CPC GM2N ASCAT precipitation product. And also what we can see that the eMERG is always, or most of the time, the worst product for this kind of application. Now we try to investigate a little bit more into detail what is the advantages of using these various precipitation products. So we ran the multi-resolution analysis where we want to decompose the error depending on the scale, on the temporal scale. So we go on the orthogonal projection of the signal in the dyadic scale. So we can decompose in this various temporal scales the error of the modeling. And what we can see is that using the CPC GM Terrain ASCAT precipitation products, it's also to give better consistency regarding the various temporal scales. And also it gets close from what we can expect with the reference precipitation time series. Another point is the use of soil moisture for the calibration of hydrological model. So for each of the 4 catchments here, for Ero, Rio Agua, Santa Lucia, and Wet Tafna, we have a benchmark, which is the calibration with the reference precipitation time series without accounting for soil moisture. And then we have the box plot of the performance criteria with using the various soil moisture products. So we have the 2 Unity ones that have been developed during the 4DMET project. We have the SMAP soil moisture profile and the SMAP Sentinel. And what we can see is that for all the catchments, we have a better performance when we are accounting for soil moisture, which is also a good, let's say, good thing for using such remote sensing data. But one of the questions is, can we improve this model performance for good reason, meaning that maybe we are compensating one process or another just by accounting this soil moisture. So what we did for the Ero basin, because we have most data, we just computed the simulated actual evapotranspiration based on our hydrological modeling, and we just compare with various other sources of estimation of the actual evapotranspiration. So for this, we use the simulated actual evapotranspiration based on the Safran-Isba-Modcou modeling chain. On the left, in the center, we have a flux tower located in Pochabon, which is representative of the main land cover in the area for the Ero River. And also, we have another project based on the TerraNet MODIS estimation of the actual evapotranspiration. And what we can see here again is that we reduce the root mean square error for the evapotranspiration, meaning that even if we don't use this variable for calibration, the fact that we account for the soil moisture allows to better reproduce the actual evapotranspiration, showing that there is a pretty good consistency between the physical processes and what we can obtain with the modeling accounting for lumped parameter models. So as a conclusion, in this work, we show that the new precipitation products allow to get close from predictive performance with a precipitation dataset based on ground station. Also considering soil moisture for run parameter modeling, calibration brings better predictive performance and better model consistency. So we just look with the actual evapotranspiration, but we can also look with other variables. The last generation of satellite observation provide valuable source of information to improve fraud forecasting of conceptual models. So here we are just looking for conceptual lumped parameter models. So it's really specific application in terms of hydrological modeling. Also the remote sensing observation, especially when combined, can offer a way to further constrain simple hydrological model. And it can be a good option to improve the scale for this pretty simple hydrological model. So it's also kind of parsimonious approach because we have few parameters to calibrate and they are pretty easy to calibrate. Then just few outlook. Satellite dataset from different sources are one solution for hydrological modeling in data where we don't have a ground station, which is pretty interesting for some application, especially for the southern part of the Mediterranean region, where there is a really scarce network of meteorological station. The high spatial resolution of the new satellite products open new application. Among other, we can have a better assessment in the precipitation for small catchments, and I'm especially thinking about the catchment lower than 1,000 kilometers square, which correspond to the order of magnitude for karst aquifer. So if we want to better investigate what's happened in groundwater in this type of aquifer, knowing that's pretty close than 10% of the Earth's people depend on this groundwater supply for fresh water, it's really important. But also giving this new high-resolution precipitation allow maybe to better investigate the recharge processes in complex geological feature. And also the high temporal resolution with 1 hour open new application for catchments with infra-daily response, which is also complicated sometimes to model because when we are looking at daily or hourly time step, we don't have the same processes that are at first order. So sometimes it's complicated to go from one temporal resolution to another. And having a good precipitation at this resolution is obviously something which can be very interesting for this application. So it's all for me. Thank you for your attention.
Thank you. And is there any question in the room? Yeah. No?
So maybe just a small question. Is there any plans to have the global scale?
No.
No?
Well, I mean, global scale for this kind of approach means that we have the idea of the distribution for each catchment, but also we need, as we are considering that we will aggregate the precipitation at the catchment scale, we need to understand what is the catchment for each river, and sometimes it's not so easy. So it can be one opportunity to test for, let's say, on a large range of catchments, but not. I don't think we can go for global applications.
Thank you. Thank you. Thank you again. And our last presentation for this session is from Yang Hong from the University of Oklahoma. And his presentation is entitled GPM, HIMERG, and its constellations in capturing extreme events in hydrological utility over the conterminous United States.
Thank you. Hello, everyone. Since this is the last one, so I'm standing in between you and the dinners, the banquet, so I will finish fast, promise you. All right, so I gave this talk in US, which received a very unpopular feedback because it's more criticizing than, compliments to precipitation estimation from satellite. And in this research, we're particularly looking at the extreme events and the long-term. See how this works. Oh, okay. Or the long-term climate trend. All right. Just briefly introduce our research laboratory. We're Hydros Lab, hydrometeorology and remote sensing. We're located in the National Weather Center. It's jointly center sponsored by NOAA and the NASA's. So just a brief background on remote sensing precipitation. About 20 years ago, I did my PhD work. By training, I'm a hydrologist. My degree is hydrology and water resources. But my PhD work is about remote sensing precipitations. So I work with my colleague, my advisor, Suresh, and the colleague, Colin. We develop Persian CCS, global precipitation data. That's 20 years ago. And we use artificial intelligence approach to handle the multi-satellite big data. And we intended to provide kilometer-wise and half-hour global satellite rainfall products. So that's about 20 years ago. Afterwards, I joined the NASA Goddard, working with Bob Adler and George Hoffman, working on the tropical rainfall major missions, which is a trend. So we're looking at the multi-sensor-based precipitation analysis, and we developed the TMPA products. That's the histories. So now we're looking at the new satellite precipitation eras, which is GPM. The state of the art or state of the science products is GPM emerge. Okay, it's presumably the best. Based on multi-sourced satellite observation, providing global data sets to analyze the spatial temporal precipitation distribution. Well, so as I mentioned at the beginning, as a hydrologist, we're very interested in looking into how the latest emerge, how useful and what's the utilities for hydrology, especially on the extreme events like flooding and drought. That's on the hydrometeorological scales. Another scale is the long-term climate scales. So we'd like to know, over the last 20 plus years, can we use satellite-based precipitation products to analyze the climate trend? If not globally, when and where can we use that products? So I have two objectives in this talk. Say how good the GPM emerge capabilities in capturing extreme events are. Then second objective is, can we trust emerge for climate change studies? So that's two kind of provocative questions. So the first one, we're looking at the extreme events, which is a study published last year. So we're looking at the evaluation over the continental United States, over the continents, not global, because we are lacking the global ground observations to validate, to compare with the satellite. And in US, we still trust the radar network for real-time applications. Especially for research, the post-real-time, we trust the gauge-corrected radar network. Originated from the LexRad, now we call MRMS, multi-radar, multi-sensor products. So we think that's the gold standard. We use that to compare against the state of the science emerge products. So we're looking at how we define extreme events. We're looking at three different types. One percentile, like 99 percentile, 95 percentile. Then we also look at the event-based. So you have accumulation of events, extreme. We also look at the, from hydrology perspective, the frequency-based, using intensity, duration, frequency, IDF curves. We look at, three different emerge products. As you might know, we have the, early run, which is near real time. Then we have the later run, it's probably 6 to 24 hours after the real time. Then we have the final run, which is the research products, maybe 1 or 3 months after the events. All right, so as I promised, I'm not going to bother you with a lot of figure and statistics, but for this one, we're looking at 95 percentile and the 99 percentile, and even the 99.9 percentile. That's really extreme events. And looking at the early round, later round, and the final rounds. Well, as you can see, statistically, okay, if you are concerned about long-term average statistic, we would say the final round products is definitely better, okay, according to all the numbers. But another issue is we're looking at extremes, okay? You will see the final round kind of flattened or reduced the extreme values. But the early round, in terms of the extreme events, capturing is the best, and the later rounds kind of in the middles. But the overall evaluation, validation, shows the final round is the best, okay? Similar story here. So we're looking at, we're using the ground, gauge correct radar network to identify the threshold of the 95 percentile, what's the run rates, 99 percentile run rates, and the extreme, like 99.9 percentile run rates. Then we'll compare the ground radar network with the early run, the difference between the later run and the final run. The same stories. You know, the final round give you concentrated or average best numbers, but it doesn't capture a lot of the extreme values. So that's points to the same directions. And we look at the PDF and the CDF of the rainfall. You would see at the lower range, okay, the final round capture, you know, agree with the ground radar network pretty well. But when come down to the higher range, and the later on, the final products just couldn't capture those higher values. Same story for the 95, 99, and the 99.9, those extremes. So that's the rain rates. And another angle we're looking at from the events, okay, from the beginning to the end of the extreme events. And we look at the columns, the radar gauge reported extreme events over the columns. All right, I would say events-based overall it's much better than the hourly rain rates in terms of the extreme value capturing. And same story here, even for the events-based total accumulation, the final products from iMerge showing us slightly better results, but again, just miss some extreme values on both sides here. All right, let me just move on to the sensors. So we compare the iMerge products, but what's behind those discrepancies? So we look into those intermediate sensor or even the level 2 products. We look into the infrared sensor, passive microwave sensor, even the intermorphing level 2 products. So the conclusion, we look at the 3 types extreme events, the deflations, and they all converge towards overall agreement. So the degree of underestimation of high-end extreme precipitation rates increase with data latencies. Final round, less capturing than later round, and less capturing than early rounds. And although the final round products deliver overall statistic performance. Look into the sensors, the passive microwave, in general, better detectability and better quantification of the extreme than the IR estimates, especially in heavy rain rates. And those findings reveal the iMerge is not a homogeneous product when it comes to estimating precipitation extremes. So let's move on to the second objective. Can we trust iMerge for long-term climatologic research? Of course, we like to say, yes, we can, but if not, where and when can we still trust it? So in this study, we just look into the past 20 years iMerge products from 2000 to 2019. We did a lot of trend analysis, statistic analysis, and break down into geography, the continental basins, and we even classify into different clusters, trying to identify the dependence on elevation, on latitude, on temperature, air pressure, and wind patterns. Looking at which factor really impact the climate trend in emerge. So I like to just give you the since this results is not published yet, we just want to give you some early funding here. iMerge may not be suitable, so we say, well, may not be suitable for analyzing climate precipitation change, particularly, especially over Eastern North America and complex mountain regions, okay, where iMerge is more likely to yield opposite or contradiction to the in situ observations. Some recommendation. So there's a good news, bad news, and good, bad, and uglies. But the situation is for extreme flooding research in US, we still use radar network. That's in US. But I would say for other regions, they don't have radar gauge network, such as some emerging country. I would say the early run of iMerge still provide capacities and capabilities in detecting extreme events. For long-term climate trend analysis in US, we still trust the gauge network or gauge corrected radar. Still they preferred for climate and trend studies. I don't know how much time I already used.
That's good. That's good.
So again, my degree, by training, I'm a hydrologist, but my PhD works happen to be remote sensing and precipitations. That's why we, concern or care about the extreme, also concern or care about the, hydroclimatologies, the long-term trend. Okay, I will just stop here. But if you have any question, you can always find me or talk to me while, running this flash flooding project over US, mainly driven by the multi-sensor, multi-radar, but we're also working on project in South America and Africa, driven by early run iMerge products. And hopefully, as the question asked, can we do this globally? For real-time operation, purely based on satellite, I would say, not there yet. But we're optimistic in the futures. All right, that's all I have. Thank you.
Thank you.
Thank you very much. And any question? Yeah.
Hello. Thank you very much too. I liked a lot. We'll focus on the first goal for the extremes. You show some verification for the intensity and then also the accumulation. And you define the events. So how do you define the events? It's a fixed time for accumulation. It varied. How did you solve that?
That's a good question. Yeah, we first we use the NOAA storm report. They give us, when and where extreme events occurred. That's from the ground report. Then we use that information, go back to the 20+ year database. We use, object identification and the tracking So for example, we use like 0.1 millimeter per hour as a threshold to define the rain extents. Then we track the rain systems through the events from beginning to the end. Then we add the total. It's not pixel based. It's more, object or storm system based. We used.
What would be the dimension, the time period from what, a few hours to 24 hours to more than that? What would be the range?
Yes. We have a database of extreme events. We break down into a heavy rainstorm, a hailstorm, and even snowfall events. So, for example, if we only look at the rainstorm events, we have about close to 10,000 events over the 5-year period. I would say time-wise, it's in between 3 hours to 18 hours. That's the 95 percentiles. But there are some exceptions. And the spatial dimension is more mesoscale. It's more from 50 kilometer, and to 100 kilometers. That's their spatial and temporal dimensions. But with that database, we can do more analysis of the storm structure, storm time, and space. That we can do a further work on that. That's a good question. Thank you.
Thank you so much. I have a little question. It's about the second objective, actually. I was more thinking about consistency for the global records prior to GPM, really. And in particular, if we can use it for detecting long-term trends globally, especially with the issue above like 60 North and so on, and presumably also over snow, if that is a problem. So what would you recommend?
So if I understand correctly, your last one is the slow, right?
Yeah, so I guess that prior to GPM, you don't have, other than the infrared, over 60 degrees north, right?
Yeah.
Because of the coverage of trim.
Right.
And I presume that over snow, that can be like really poor quality. So do you think that the data set is still consistent enough to actually have like that trim period included for global studies?
That's a very good question. We let's see, in these studies, we haven't really looked into the the solid precipitation, like snowfall at a higher altitude. We look at the slaughter equivalent. So I couldn't really answer you on the high latitude, but my gut feeling is, iMerge does provide types, tell you, rainfall, snowfall. I don't know if I should say this, but we're still not very confident in snowfall products in terms of the, quantitative values. Maybe the, the type, yes and no, we're kind of confident, but not at the rates. So I would say if you want to look at the types of precipitation, climatology, that might be suitable, okay, but if you look into the rainfall, snowfall rates, I would be, cautious. Thank you.
Okay, thank you. So, thank you so much.
All right, appreciate it. Thank you.
So we are very, very late. We should finish at 6:30, so it will be very fast. Everybody wants to relax before going to the dinner. Okay, so these are some of the seed questions. Let's just go through them just to see if you agree with what we put here or not. Okay, so one first question is how could we use the new satellite data? So I'm thinking, for example, at SWOT to improve historical records because yes, we have a new satellite. We can do a very nice product, but this is not, it's not with this that you're going to do a climate. So I think space agency should have some ideas of impacting this new data into the older time series. It's essential. And for example, I'm thinking about water extent from SWOT. And obviously, SWOT is going to give us very nice products, but we need to capitalize on that and try to impact the long-term time series. So do you think this is something useful? Do you see that happening for other variables? We know that we are going to do that for surface extent, but I don't know, for river discharge, do you think this is critical or not? Any feedback on that?
Or do you have any idea of methodologies to get these new missions to improve whole time series over long periods?
Do you intend to do this kind of exercise or not at all? Are you focusing on the newer products and not looking into the past? Okay.
Thank you for this interesting question. It's too tall for me. I just take it. Yes, of course, it would be cool to improve the historical data sets. Perhaps we have the GRDC data set, which can then be improved via data simulation. Yeah. To your question, I think variational data simulation helps you improve over the entire time series. This is one idea. And to yours, so I do a bunch of things. My name is Antara, and mostly looking at SAR and floods. And so we also plan to do some harmonization across old SAR sensors and new SAR sensors and to build a consistent SAR data set for surface water extent, but more flooding. So not so much surface water, but to look at really flood extent records, because we found that in very cloudy areas, for example, the optical time series is not so great for looking at surface water. So yes, it would be vital to propagate these benefits back into the historical time series.
Okay, thank you. So the second point, and probably we didn't see so much talks mentioning artificial intelligence and or machine learning. And this is something that, okay, he impacted a lot remote sensing more than 20 years ago. And we see in the weather forecasting, he has a huge impact in the last couple of months, I would say a little bit more maybe, but it's a big revolution. So do you think in hydrology, this is going to happen? Has it already happened? Are you scared about that? And do we need to adjust to that? There is always the physical models with respect to the machine learning models. So how do balance these two things? So do you have any ideas about that? Both? You want to?
It's a discussion in every session. Like
Yes,
we have. I already said something about the meteorology part. I'm a meteorologist, so I think even the European Centre, which is clearly being threatened, let's put it in
Yes, yes.
But it's being threatened by itself because the data that is used is from the reanalysis that the European Centre is producing.
Yeah, it's trained on it. Yes.
So it's training, and so it has to keep having the good data to support the artificial intelligence. So I think you have to be worried, but you have to be also looking forward. And clearly it's teamwork. So in my perspective, so being a meteorologist, I'm very excited and worried at the same time with the changes in the numerical weather models. But at this point, and I might be wrong in 1 year, I think that the European Center is still supplying the artificial intelligence with the reanalysis.
Yeah.
So maybe in 1 year, this is not true. I don't know.
Yes, because
we don't know.
Maybe they can just train on observations only.
Observations, and then they overcome what the European Center is doing. So we cannot know. But at this time, today, I still believe this. So I think it's a balance, a mix between the two.
Yeah.
And so keeping the two kind of evolutions, I think, are still.
And what about hydrology? Do you think we are in the same situation?
I'm not an hydrologist, so I'm really seeing it from the outside. But I think it applies to everything. So in the end.
So I've seen some very recent papers about river discharge that are retrieved with some special kind of neural network with short-term and long-term information, as we did see in one of the presentations. And it seems to work. Like people seem to be very enthusiastic about this kind of approach. So probably it's going to change a lot, I believe.
And if the time for running the model, it's even shorter, then it's an advantage. So, again,
yes.
Keep playing in.
Walking.
Yeah.
Any other thoughts on that? No? Okay, so let's go to the third one. In terms of the applications, this is always something that is happening. There are many products we have seen for precipitation, etc., etc. A lot of products for the same water component, and the users, they don't know which one to use. So a lot of times averaging in some way of these data is helping a lot. We have seen some, at least a poster on this. But how can we use a user in this respect? I think like a space agency could really facilitate the work of the end users by providing their own diagnostics and some kind of benchmarks to help to see, okay, I should use this product instead of another one. So I know it's not easy to do these comparisons. It's not really diplomatic and all the time, but do you think this kind of tool will be useful? Yeah?
Friendly for short people.
Sorry.
So just I think maybe to connect to your previous question, so the same group, I imagine you're talking about the same papers from Freddy Kratzert's group, JKU, Austria.
Yeah.
And now they are at Google. So the Google Flood Forecasting Initiative is very much live, and they are very much beating every hydrological model.
Yes.
Also in ungauged basins. And they also show that it's possible to leverage the synergies between these different products. So soon we will be in a space where there is no need to choose between the different products. Each product has its strengths and limitations, and we can leverage the synergy between the different products using AI. So the model internally, if you think about this convolutional LSTM type of models, it can internally infer which data set is better where, and it focuses on this data set in its prediction.
Okay.
And so we could do this exercise, but this exercise might become obsolete.
Yes. Okay.
Very fast.
So you are very enthusiastic with the new approaches, and you think Google Forecast will be dominating the community?
That is what I do, because their goal at the moment is to show that you don't need domain expertise for this. I don't think that's accurate. That's their own language. I'm not making this up. But it is a revolution, as you already said. ECMWF is scared. They have put out their ML models on their website. There is a reason that they are putting their weight behind GraphCast and Pangu weather and all of that. And so I don't think we can ignore it. It's no longer possible that we stand in the corner and say, no, we don't look at this. But to work with them, to bring the domain expertise on the table and to see what we can achieve together. And sure, it's scary, but I mean, we are scientists. This is a paradigm shift. We should be ready for this. And
But do you think like space agencies could help you?
They are at the moment. There are multiple downscale products you can see in Nature Scientific Data. And I think one of the presentations showed like 4 different soil moisture products at 1 kilometer using AI. They are not yet consistent, but they will be as we go forward. And so I think it's really, I mean, so also in data assimilation, there have been some key papers in the last few years talking, again, from ECMWF, Alan Gear in particular, talking about how we could learn from the deviation between model and data going forward in time. So this learning capability of the deep learning algorithms, it's really great to also for data assimilation. And the fight between AI and physics-based, I also don't get it, because the model, the AI model is deriving equations. That's what it's doing in the background. So how do we know that it's not deriving the physics equations? What we need to do is really invest in understanding what the model is doing. So more explainability, more trustworthy AI. I think Guy talked about being able to detect what data went into the model. These kind of things will become much more important going forward. And I think Guy would like to add stuff.
But only if you're done. So thank you. I think you said something at the end. It's very important. I think, you know, about Google. It's a long story, but maybe I can tell people over dinner. I work a lot with Google. I don't get money, but I know a lot of people at Google. And I can tell you right now, the situation we have now in Israel, Gaza, is slowing them down a little bit because they are all in that region for the flood hub. People that are employed by Google all are Israel, like position, but they're not all Israelis. But I think I have trouble reaching them for a month now.
Oh.
And I think it's due to this situation a little bit, but they also are very, very open. So that's another thing, right? That's a real world situation that they're also not too happy with at Google, because it slows down their engagement, because they do engage with the community, especially on the flood hub. One main reason is because they're struggling to get to where they want to go, which is informing everybody with a Google phone, with a handheld device, to say, here's a flood alert, do you accept it or not? And then you click yes, and then you get the flood alert where you are. They're struggling getting this. There are several reasons for this, and they want to work with the community. So all you need to do is tell Google where they go wrong, and then they're very interested to understand how they can do it right. And I think they have, of course, their own goal. They have their own agenda. But for example, they're working with me now on a product I developed with the help of ESA, FloodSense. They want me to validate some of their flood inundation maps, because I told them their flood inundation maps are not really great, because they are derived on high resolution DM everywhere. They could be much better than they are. So they've asked me to validate some of the events using optical data. And they struggle really with SAR data, for example. And I asked them, why don't you hire SAR people? You Google. You know, you can offer 3 times the salary that any ESA or university can offer. Why don't you? And they said that that's not their goal. Their goal is to really get this flood alerting to everybody. It's not to hire teams of SAR experts. They would rather work with scientists. But I also told them they should go more to meetings like this. But they are at the GFP, Global Flood Partnership, very often. They run their own flood forecasting workshop where they invite people. But they also apparently have a hard time reaching us as scientists. So maybe there's a way we should collaborate more, because they are also scared about ML themselves. Funnily enough, I think a lot of you have seen Google CEO getting really scared about ML. Elon Musk is the scariest. You know, he's the most scared about ML. He wants to go to Mars because of that. So he wants to leave this planet. Anyway, so that's what I have to say. I think we can work with them.
Thank you. Just to be clear, I have nothing against Google. Actually, we are using tools from them. It's very convenient, and they provide some facilities for data volume and computation that might, I don't know, like for SWOT data. I don't know if they will get it, but yeah, it's a very practical solution sometimes. And about the physics and the machine learning, I think, yes, it's not fighting between the two. You could actually have a physical model that depends on parameters, and you use a capability of the learning, of the machine learning, to estimate these parameters. So in this case, you are just using the best of the two. Yeah.
I just made the comment because I think they want to work with us as well.
Yeah, yeah.
And actually, they are the first ones to grab the Sentinel data and make it available to everybody.
Yeah, yeah.
Better than ESA can do it, no offense, but they grab all the publicly available science data and make it accessible to everybody to produce a map.
Yeah, it's great.
Yeah.
Yeah, well, I think it's really nice that the Sentinel data is being distributed all over the world, free and open access and so on. So we're happy, and we have, yeah, we work with Google as well. What I wanted to say is that Google wants to put information on everybody's cell phone, but let's think of adding into the discussion, let's see questions and so on, if everybody's cell phone can contribute to something that can be used to predict floods or drought and so on. Like, so the word is a fashion word is citizen science. And maybe in some ungauged basin, if you get a picture sent over the network of a ruler that sits in the water, and because nobody comes and reads it, but citizens walking by can send pictures of the ruler. And in fact, even in Bentiu, I was discussing with Médecins Sans Frontières and UN MISS, United Nations Mission in South Sudan. They are so busy with the hospital and with the infrastructure and the logistics that they don't even time to go to the river Bahr el Ghazal, where there is a ruler, but there's nobody to read it at least once a day. And so citizen science could be one of the bullets of the seed questions, and see how we could eventually set up something to recuperate.
I think OpenStreetMap is one data set like this. And it seems to be quite precise over Japan. I don't know why, but people say it's a very interesting data set over Japan.
But if people take a picture of their boots, we can see the height of the flood, at least in real time. The idea would be to predict, but...
Maybe a quick plug here. There is a very good app called Crowdwater. It's run by Jan Seibert of ETH Zurich. And they do exactly this. You can put a virtual gauge wherever you want, wherever you are. You see a river, the phone camera will develop the virtual gauge, and you can measure the water height, and it's uploaded directly to the Crowdwater platform. It's presented at EGU every year. They've been doing it for 7-ish years now. The citizen science community is super active at EGU. Feel free to drop by. Would be awesome. They're associated, but kind of. Please, so shameless plug, any of you who are here, live near a river, please download the Crowdwater app. You can make a virtual gauge wherever you are. That would be super awesome and help the community.
Okay.
Thank you.
Okay, thank you. And just maybe the last bullet, how to integrate the data sets to obtain a current water cycle analysis. So we have seen some presentations where there is an integration. You can do a simulation. There is a machine learning. So there are different ways to put together the data sets that describe the water cycle. we think that this is really important because by putting together these data sets, you get more information in each one of the products. So for example, if you put GRACE with Precip, EVAP, etc., then you will get more information than GRACE alone in terms of groundwater storage. So there is a true benefit in putting these data sets together. You can downscale some of the products. You can reduce the uncertainties that you have by using the complementarity of information. There is a different kind of synergies that you can exploit into that. And often it's not the case. Space agencies, they found people and projects to retrieve one variable, and we don't focus too much on how to put them together. So any remarks on that? Do you agree with this? Should we emphasize that? So I don't know actually the status of the water cycle ECV. What is happening with that? Nobody has any feedback on the ECV water cycle? What is the status? You don't know?
As you've seen yesterday, we have launched an ECV that I've been fighting for a long time, that it could be done in the climate change initiative. It's a river discharge. What is the water cycle ECV?
I think I've seen in some ESA project that there was a ECV about water cycle was considered.
It's like the human impact on the water cycle or something like that?
No, really water cycle.
Yeah. It's a bit late in the day for me to think of the things that we have in store in the climate change initiative. I could look it up.
Okay.
In the documents I have. But water cycle is a complex suite of variables.
Yeah.
And so it should be a cross ECV activity on the water cycle. Yeah. Yeah, good point. Sorry, I'm trying to get my neurons together. We have, from the CCI building individual ECVs, we have launched a certain number of things about the going into the cycles, energy cycle, water cycle, and so on.
But you see, if you have a ECV for each one of the components and you put them together and you don't close the water budget, there is an issue. Yeah.
Yeah, we did that for the sea level budget closure. All the components of sea level go into a cross ECV activity, which I launched in 2015 and I relaunched recently, and second phase called the sea level budget closure. So again, yeah, the idea is to do a cross ECV activity on the water cycle. Now you ask me where it is. Right now, I have no knowledge that it's been kicked off, because then I would know more about it, and it's maybe in the oven to be cooked for an ITT. But I'll check my ultimate slide from the last co-location meeting, and I'll tell you tomorrow.
Perfect.
But if you want to make a recommendation that the CCI should push and get this cross ECV water cycle activity launched as soon as possible, that would be a good recommendation.
You agree with that?
Yeah, of course I agree. If we can launch activities for the advancement of science, that's our job.
Okay. So any other remarks and comments that you would like to be put into the recommendations? Nothing? Okay, so thank you so much to stay until that time. You are very courageous and professional. Thank you so much.
Thank you, and thanks again for our speakers. Thanks.
Thank you.